अगर was it
This
I think slow.
this
Just a
judging
moment.
Team 2, please confirm if they can present right now.
this judging parameters in the Excel sheet, is that like what is?
Rama,
Yeah, tell me.
we are already in the main thing.
Oh,
So,
sorry.
yeah.
Team 2 can begin that presentation. Uh, when they share the screen, I'll just start the timer. So you can present your skills right away now. Yeah, so your timer starts now. You can begin.
Hello and welcome to our presentation for the ISRO problem statement. I'm Arvind and I'll be presenting today for Team 2, introducing you all to Surya Drishti, a web-based application to automatically identify solar flares in X-ray light curves. On July 3rd, 2021, a solar flare, the most intensive one in the last 5 years, erupted from the surface of the sun and smacked right into the Earth's atmosphere. This caused a shortwave radio blackout that created transmission problems over the Atlantic Ocean. It has been remarked that the solar flare appeared suddenly, highlighting the unpredictability of solar activity. But the more we understand it, the more prepared we can be. And one step towards predicting its understanding is understanding the morphology of the burst. And we seek to identify the characteristic features from the available input, which is a light curve in this case. And this is where our application comes in. So what's in a light curve? Just a time series data of a bunch of photons falling on a detector, just happening to be in the X-ray regime in this case. But like I mentioned earlier, we need to extract something, information that will aid scientific research. Before we work with it, one might wonder why this would be a hard task. You have some well-formed curves, and you just need to pick them out automatically. But what if these curves span over a bad time interval, like in the diagram shown here? What if they are not actually solar flares but random spikes in the data? Or what if the signal to noise ratio is so small? These are some realistic conditions that we will have to deal with. But our model still transforms this to this, where we have isolated and captured only the regions of interest and additionally extracted the characteristic features from it. But how did we do this? We followed a simple three-step approach to tackle the problem at hand. First, the pipeline pre-processes the data to remove noise and searches for major disturbances in the background radiation. The image on the left shows raw data, while the image on the right shows the same after some pre-processing. Pre-processing includes data smoothing using the boxcar method and data resampling using binning. On our front-end application, the user may adjust the bin size that is to be used. We then move on to the burst detection step. Two methods have been employed here, the more robust n sigma algorithm and the more sensitive local maxima algorithm. The former classifies any region that differs from the background by at least 2, 3, or n sigma as a possible burst. Through careful analysis, we have fine-tuned the value of n to be 2.8. Although this method is very robust and provides very few false positives, the main disadvantage is its inability to detect very small bursts in the presence of a larger burst. The latter method searches for a sequence of steeply increasing points and classifies the region as a burst if it satisfies a preset criteria. Its increased sensitivity is also its drawback, as it may classify a seemingly unlikely region as a burst. The best part is that on our application, the user can choose to view the burst identified by either method. We then fit the region classified as a burst to a convolution of a Gaussian and an exponential decay, and verify if it is a burst by calculating the goodness of fit using the chi-square measure. In the literature, this convol function is referred to as an elementary flare profile. The initial parameter values have been carefully fine-tuned to obtain maximum precision. The start time of the burst is defined as the time when the fitted function rises one standard deviation above the background. Similarly, the end time is defined as the time when the curve fit falls below the one standard deviation point. Not surprisingly, the peak time is when the EFP fit attains its maximum value. This flowchart captures the exact sequence of implemented pipeline. We have the two-step pre-processing of the data, the burst detection step, and the burst fit/verification step. This allows us to satisfy the requirements of the problem statement. But can we go further? If we want to extract more features, we might want to convert the photon count rate to energy flux received at the detector. Here, we calibrate the XSM count rate to the GOES energy flux with the help of the graph on the left. And as a notational shorthand, we use the popular soft X-ray classification scheme as depicted in the table. Besides event timing, temperature and emission measure are some of the fundamental characteristics of importance for flare physics. As the flare progresses, the average temperature and emission measure increases to a certain maximum level and then declines during the decay phase, and this general trend is independent of flare strength. The temperature function was originally approximated as a cubic polynomial of the flux. Further, the emission measure and total radiative loss typically require spectroscopic information to be accurately determined. Citing a paper from 2012, we have statistically fitted the exponential of the flux to obtain these values. Once we have met the basic requirements, we can tread further and build on this model. Putting all our extra features together on a single page, here's our final statistical model. We read some more properties from the curve fit, we calculate the energy flux from the photon count rate, we obtain the characteristic features such as temperature and emission measure, and we also classify the data. On our front-end application, the burst can be sorted according to the peak time, the peak flux, or the peak temperature. And all the analyzed properties can be downloaded as a report with a simple click of a button. But classical algorithms may not be very robust. What do we do about the false positives that may creep in? Here's a solution. By using visual inspection and properties of the burst, the user will be able to classify false positives and then dynamically train a machine learning model to remove them. If provided with a validation dataset, we can train this model to high accuracies. On this slide, we have highlighted one such burst rejected based on visual inspection. Clearly, the data points do not fit a curve, and our local maxima algorithm also thinks so. We start out with an untrained machine learning model. The machine learning confidence level reports the predicted probability of the identified burst being a true positive. Now that we have rejected this burst, we can retrain our model and see how it updates its confidence level. We see that it falls sharply from the initial value of 99% to a confidence level of 3%. A machine learning model is adaptive and can be trained sequentially along the way. We finally arrive at our results section. The input file can be uploaded using the upload file button or by a simple drag and drop action.
Sorry to interrupt. Are you changing the slide? At least I'm not seeing the change. Others are able to see change in the slides?
I can see it.
Okay, fine. Then I'll relog in again.
So once the file has been submitted into our application, you will see the screen. Here, you can change the bin size, the detection method to be used, or play around with the interactive time series plot. Points in blue denote the identified peaks in the data. You can zoom into any region in the plot to get a closer look. Notice that this plot has one peak, which is in fact over a bad time interval, but our model still manages to successfully isolate it. When you scroll down, you will find that the report section of our model. Here, you can sort the identified burst based on the peak time, peak flux, or peak temperature. The default mode for sorting is the chronological appearance of peak time. The first column shows the peak time of the burst with respect to the beginning of the day. The second column presents some important flare characteristics, which include the peak count rate and the class of the solar flare. The third and the fourth column represent the two aforementioned algorithms used to identify bursts from the light curve data. Here, A, B, C, D are the curve fit parameters, and in our live demo, these will be shown in real time. As for our future work, we are aware of some directions we want to expand on. We wish to improve the reliability of detecting multi-bursts or bursts at the edge of the light curve files, that is, at the start or the end of the day. We try to introduce a hybrid burst detection method that incorporates the best of both worlds of the two algorithms, making a robust as well as a sensitive algorithm, which will increase the detection of smaller bursts in the presence of large bursts. We also wish to increase the precision of our estimates for the emission measure and total radiative loss estimates for high-intensity bursts by incorporating information from the short flux channels and other spectroscopic information. We also wish to incorporate a temperature and emission measure-based background subtraction, which remains a hot field of research till today. To summarize, we have presented Surya Drishti, its key features, and some results. The Python-based statistical model works on a simple three-step approach: detection, verification, and analysis. The application can be deployed on any modern Linux-based operating system and supports a wide range of input file types such as ASCII, CSV, HDF5, and FITS. It also supports a machine learning model that can be dynamically trained to reject false positives. And finally, we note that the inclusion of interactive plots are not only useful to researchers, but are also very useful for outreach purposes for the Chandrayaan-2 orbiter, its payload, and all the scientific instruments involved. With that, we would like to conclude our presentation and open up to questions.
I request Rama and other team members, maybe each one of you can go through.
May I ask a question, Shankar?
Go ahead. I think Rama is the moderator. Go ahead.
Okay, I do. Actually, I have two questions. You mentioned that in the presence of large burst, you cannot actually detect a smaller burst. So that's a dynamic range. Can you put a number on that? Like what will be the minimum dynamic range over which you can detect this?
So the n-sigma algorithm basically works by calculating the entire mean over the data and taking the standard deviation away from that mean. So because we are taking a sigma n value of 2.8, the 2.8 sigma is the cutoff period. So any flare that's smaller or like the peak count rate is below that will not be detected by this algorithm.
No. I meant dynamic range, large versus small, if they're very close by. So what is the minimum ratios over which you can actually detect a smaller flare? Maybe that I'll come to later. Then you mentioned that you are planning to get the temperature and emission measurements. So with a light curve, how do you get temperature and emission measures? You need spectral information for that, right?
Yes, that is correct. So there was a paper by Rayan published in 2012, which is actually a follow-up from White, which was published in 2005, which estimate or statistically fit all these values to the past observations using the GOES flux information. And considering we have calibrated the XSM count rate to the GOES flux data, this has been a quite established couple of constant values for these expressions listed on this slide.
May I ask how is the calibration done for XSM and GOES?
XSM count rate and GOES count flux measure, energy flux measure have been taken from the website on PRL, Physics Research Laboratory. And because none of our light curves in our analysis period exceeded the 80,000 count rate mark for the beryllium detector to come into place, we have gone ahead by saying that the beryllium detector is not in action. So the green plot out there will be the calibration line.
Have you verified this calibration with GOES data? Have you, I mean, for the same time, have you checked the XSM light curve as well as GOES light curve?
So we have been presented with XSM light curve, and those have been calibrated to this GOES energy flux, but a corresponding measure of the same observation has not been measured.
Okay, sure, thanks. Can you elaborate on the temperature calculation as well?
So if we go to the last slide or the slide prior to this, we would see that in White 2005, they have measured temperature using this expression out here. Here, R stands for the ratio between the short flux to the long flux. However, the short flux information is not provided to us. So we have gone with a more recent paper where they have converted, or rather assumed that the short flux range is quite minimal and that it won't vary as much when the long flux value is varying. So in that case, they have just statistically fitted the data. And if you look at these plots, even from NAMA 2021, which is a poster presentation, they have fitted these to actually linear plots on the log scale for flux versus temperature, flux versus count rate or energy flux. Yeah.
Okay, yeah.
Sorry, I take my word back, like flux versus temperature, but temperature in the linear scale.
Yeah, one question similar to the thresholds which you put on the count rate and the intensity. Is there a limitation on the time bin, like shorter duration flares? How do you judge? Is there can it? How robust is your method to detect that?
Devansh, can you take this question?
Yes. So like the bin size is actually can be set by the user. So like on the interface there is a bin selection. So what we observe that if we have a if we want to detect smaller bursts like or the bursts which have smaller duration, in that case having a small bin size is useful. So like we went with 50 like a size of 50. So 50 is around 1 minute of span. If we go with high bin size, say 200, 250, then the bursts which range from around 16 to 20 minutes, those usually don't have enough data points to be actually characterized as a flare. So for usually high bin size is useful for getting high like long range flares, and small bin size is useful for small ones. And like moderate ones are capable of detecting both of them, like a condition that they are not overlapping.
Okay, so your minimum bin size is 50 seconds.
Yes.
Okay, okay.
Can you make this decision intelligently, or does it require manual intervention?
So
How do
like
you optimize
we
this bin size basically?
Right. So for that we went through the so like we used the bin size 20, 70. Like we went through some major like values, and then we were able to get an approximate range of the size of the flares, which lied from around half an hour, which was a bit common, to say around 2 or 3 hours, which we found cases of 2 to 3 hours. If we went with bin size of 50, then the processing of 3 hours flares was not well, and because the slope was slow, it was not being detected by local maximum algorithm. So like we modified so like we tested from 50 to 500, and the optimal range of the optimal bin size which we got was 200. So the interface by default opens up at 200, and if we want to only select one side of the flare, one type of flare, then we can accordingly change the bin size. Bin size 150 and 200, those are more robust to detecting both type of flares.
Uh, okay, are there any more questions?
Yeah, Rama, I have a question.
Yeah, yeah.
You people in this n sigma algorithm, you are taking the whole light curve and then calculating the sigma, right? So obviously, you know, if there are big flares, your sigma value is going to be very high. Isn't it logical to take the sigma only from the background? Maybe using one of the local maximum algorithm, you first identify the peaks and remove those region and only then take a sigma. Wouldn't that have been much better than taking a sigma of the whole data? Because you know that it is not really, see, when you take a sigma standard deviation, you are trying to characterize the noise, whereas you very well know that you are taking the signal as well when you take the whole thing. So you are really not really calculating the noise here, you are calculating some strange value because it's a signal plus noise.
So this is something that we are aware of, and that is why we wanted to try out a hybrid method, burst detection method, incorporating the advantages like the local maxima has identified some. It is sensitive to even small increases, so it identifies the peak. So it kind of gets eliminated, and really the remaining part is put into the n sigma function. But we have not implemented it as of the moment.
Yeah, so when you say this n sigma union local maxima, you had an option like that, right? So in that, what are you basically? What is the union here then? If you are not implemented this, just
So actually, so both the algorithms detect like a set of flares. So a lot of times, what we saw that if there are a mixture of small short flares and long flares, then both the algorithms will give a different set, which may be like they have a lot of intersection, but the set difference might not be null. So like there are some flares which are only detected by n sigma, and some flares which are only detected by local maxima. So union
okay.
is like pointing out all
Only
the
the
flares. Yeah.
so only the list
You,
is the union basically.
Yes, it's a union of the list.
Okay, okay, fine. Yeah, one more question. This machine learning seems to be when we tried running this, the machine learning seems to be the poorest way of doing it. Whereas n sigma versus local maxima, the union seems to be the best way. to get the maximum numbers. Is it because of the lack of training, or you think the N sigma method is better than the machine learning method?
So actually, like the machine learning model which we submitted was not trained. So for that, we require a differentiation between false positives and true positives, which we did manually. And so like we didn't have the label data. So the given LC files, we worked on them. We worked on around 10, 12 of them, and we trained it based on that. And then we tried it on say 2 or 3 others, and that was working good. But if we try some other ones which have a lot of bad intervals, because the ones which we trained on had relatively around 10 to 20% of bad intervals. Like this one has around 22. And if we go with some other funds which have say 30 to 40% bad interval, in that case the ML model was not working great. So I mean, we need to train it on based on different patches. So like we have, I think, around 400 to 500 good light curves. So if we train it on all of them, then it will be more robust to such things. The point of like the ML algorithm takes the input of n sigma and local maxima. So like the ML algorithm doesn't directly detect the flares. It classifies whether the detected flare by n sigma and local maxima is actually a false positive or a true positive. So we give a ML confidence based on that, and then the user can accordingly sort based on the confidence and accordingly choose whether the ones which have low confidence are actually false positives or not.
Okay, thanks.
Rama, can I?
If the questions are over, we can begin with the live demonstration of the code. So whoever are the presentations from you can present the screens for live demo.
Thank you.
Ada itu mesti kali.
Thank you.
Rama, can I ask something?
Yes, please.
Okay. Okay. This may not be a kind of a question for anything related to marks. Just to understand how much you guys have learned it. So whatever data processing which you have done, I just want to ask you two things. One is you have some numbers on how many of false positive you have detected and how many of false negative you have detected for the data whatever you have run. That is one question. Second thing is, have you noticed anything unusual which made you more curious to see or learn what it is about? Can you answer these two?
So for the first question,
Yeah, can I just make a suggestion? While actually you're doing it, you can actually run the demo also parallelly.
okay. Okay. So maybe the demo. So this was drag and drop, and click submit. So regarding the false positives and false negatives, we didn't have any data on false negatives. I mean, we had the interactive plot, and based on that, we saw that there were a few false negatives. So over in this case, we can see that we have a false negative. That's because of bin size 200. So if we look next to it, we have a longer burst and then a shorter burst. So because of this, this one has a high peak value. That's why this is being detected even though it's thin. If we reduce the binning a lot, and sigma will actually even detect the last one. But if we look closely, it's only a rise and not a fall. So by default, we have agreed to not consider this as a flare because we don't have a fall and we can classify it properly. Local maxima is robust to such outliers. In this case, we have the bin size as 200. So the union gives thing. And then we have a false positive like this. This is actually a micro flare. If we look at the graph, this will be considered as a sub-A class flare, which can be considered as false positive or not. Like that depends on whether we consider sub-A as, because I think this lies in the noise region. So it can be considered as false positive or a sub-A flare. And then again, over here, we have an overlapping of two flares, which are pretty short. Again, I think the noise level, so this is a clean file. So like this is a processed light curve after denoising, like deturning and binning. So this is one. And if you look at just local maxima detects these two, whereas and sigma will be detecting this one. So, so yeah, for bin size 200, we are getting this one as common in both of them. This is because compared to its background, like the background noise level around it is pretty low. So this is actually classified. So this is so okay. Going by the if we sort the interface by Flux, we see that we detect a B1 class flare, which is actually this major flare, which is B1 because I think the range is around pretty short. So this is around 300 count rate. Then we also detect a A4, which is again these two are not detected by local maxima because so if we look at it, local maxima goes with so like in our local maxima algorithm which we implemented, we go with four consecutive points and we look at the point and see the slope. Over here, the number of samples are pretty low, so the slope is not that good, and that's why it's not detected by local maxima. Whereas N sigma detects it, and even the fit is like the decay rate is getting proper. This is one. This is the A4 curve. Again, the decay part is like the exponential decay is being fit properly. Then this is the one where we have two bursts overlapping, which kind of throws off local maximum because we have a steep rise in some points. Again, the problem is that the noise level is so like these values are pretty close to noise level. So like noise usually lies in around 10 to 20 range, and the height is 40. This is A1 burst only, and then we have one sub A burst, which like so this is the one which is being detected by both of them. So we can see there is a minor like a small rise and fall, and both of them are able to fit the TK properly. So this can be considered as a false positive if we consider because the noise level is again in the range of 10, and we have a curve which has a variation of around less than 10. But again, because we have a proper fit, we can again classify this as true positive as well. So this is one ambiguity which we can work on. Then apart from this, so this is so if we reduce the bin size, I think yeah, if we go to 100, so this will reanalyze the entire thing with bin size 100.
Okay, I think that we got it. So you can go to the next one. Is anything interesting which you thought, would be useful to go into more details? You don't have to go into too detailed, but you can just indicate which was giving you a more interesting idea.
Arvind, would you like to take the question?
Sure. So, as pointed out in our future work, we are aware of some directions we wish to expand on, and one of the key points, which was also pointed out here, was the hybrid methodology, so that we take advantage of the sensitiveness and the robustness. That is one thing that we are very keen on. The other thing is this popular method of temperature and emission measure-based background subtraction, where if given the spectroscopic information, we can calculate this and more effectively remove the background radiation. So these two have been very actively researched areas as of the moment. In our machine learning, in our demo, we can also show you the machine learning aspect of it and how it works. If you could point out that this burst is actually not a burst, and we'll be able to retrain our machine learning model in lifetime.
Okay, thank you. I think we can go into that demo mode. Is that okay, Rama?
Yes, yes.
Devansh, can you pull up the demo again? Panel members, if you could point out that a certain burst is false positive in our identification scheme, then that can be added into our classified into our false positive list, and the model can be retained in real time.
Can I ask a small question? So this data was given a little early to you. So I hope that you have actually running this program on that from last 10-20 minutes. I just wanted to know how many total number of players or bursts you have detected with all these exercise, varying the bin size and others. What's the maximum number of bursts you have detected?
I think for that, the bin size 100 value would be better because we had a larger.
No, I'm not saying that. just by varying it, what is the total number?
10. We were so like 100 was giving 9, and if we go back, so like if we go back 250 binning, we were detecting one additional burst. So that is a total of 10. 10
Okay,
unique
thank you.
bursts.
Yeah, thank you.
And do you also keep this sigma value, the threshold value variation, as an option?
No. We tuned. So like we went through the K1 LC files and we tuned it to 2.8. We initially tried 1, 3, and 5, which are the common numbers, and then we fine tuned it to 2.8, which was giving very few false positives, and it was not giving any false negatives either.
Okay, in this attempt, have you tried varying that and checked for false positives?
So
No,
yeah,
in your
that's the
previous initial trials, you have done that, like varying it and fixing it to 2.8. But would it be worth having that also an option to check for lower thresholds for smaller flares, and then see how it works?
uh, Yes, so the reason we didn't, so that we had a thought of putting it. The reason we didn't do it because we wanted to make the pen size is something which a normal user who doesn't have the prerequisites of what n sigma algorithm is would be able to use. But for the with the constant to understand, they will have to understand how n sigma works. So that's why we didn't keep that option. We can definitely add, so that is just one single parameter in the function which can be manipulated, like which can be easily added to the front end and manipulated in the back end.
Okay. Okay. Any further questions from members?
Were you able to run on the code on all the three data format which was supplied to you, FITS, NetCDF, as well as an ASCII file?
Right. So the ASCII file, the time format was different from the one. So the time format which was given to us was different. So that was not working. And we don't have the support for CDF. We have support for CSV, HDF5, and ASCII along with FITS.
Okay, so you could only in the out of the three files you could only run the FITS file, right?
So actually, I generated the other three formats of the same LC file as well. I can show them if needed. So this is the same LC file, just that we had a script to convert all the LC file into CSV, ASCII, and HDF5, and this is the input as ASCII file.
Okay, thank you.
Okay. Shankar, should we go further, like close this presentation and take the next?
Yeah, I think if other review members doesn't have any other queries, probably we can move on.
Yeah.
No more
Yeah,
queries
I'm
from my
good. Yeah.
Okay then. So thank you so much. Yeah, it was a very good presentation. And yeah,
Yeah. Thank you so much, team two. You can just leave the stage. Yeah.
Thank you.
Yeah. Team two can leave the stage, right?
so can we have the next presentation or?
Judges, we next have, yeah, next we have team 16. I'll just make the team members as attendees.
Hello?
Yes, ma'am. We have two presenters right now. Team 16, please confirm if you can present.
Uh, Good morning, everyone. Uh, we'll be able to present. Actually, we have our mid-semester examination. So one of our presenters are on the way. Like he is here. He's just logging in. It will take just 30 seconds.
Just to confirm, Team 16, right?
Yes, sir. It's Team 16. Okay. One of our teammates is here. He has joined the meet. Kindly make him the.
Yeah, the concerned speaker is advised to raise his hand so we can make him presenter. Yeah, okay. The invitation is sent. Kindly check. Yeah, I think all the members are on here on the stage. You can begin your presentation. Hello, Team 16, please confirm.
Yes, everyone has joined. We are starting presenting.
Um, Team 16, your screen is not visible to me.
Hello, am I audible?
Yeah, yeah, you're audible.
Hello.
Yeah, hello, you're audible. You can begin your presentation.
All right. Just give me 1 second. The presentation is opening.
You can begin your presentation. Actually, it's take. Yeah. Is there any issue you're facing?
Actually, the it's still loading. So like we have actually clicked on the share screen option, but like it's still loading. So that's why we are waiting.
Any other member can present their screens if he is
Yeah,
taking time.
yeah.
Yes, we are trying.
Okay, your screen is visible. You can.
All right. This is the solar burst ray detection portal from team number 16. We basically created a standalone and a web application. The structure of the application is basically divided into two parts. One is the front end, that is the interface and the UI and all. And then there's a back end which does all the processing and the data input and the application of transformations and the classification. So first, we will look at some of the challenges which were faced by our backend and front-end team. In terms of machine learning, we had particular difficulty in fitting the curves to the peaks. So what we were basically doing is that we were using a certain function to fit them on the peak, and therefore taking out the decay rate, the peak count, and all using the parameters from the curve. So we had difficulty in fitting all that. We had difficulty in working with multiple peaks. We had to basically differentiate all of those. So we had difficulty with that. Working with missing data was
I'm sorry to interrupt. Is the presentation still visible? Hello.
No, the presentation is not visible right now. Can you please try again? I would like to confirm with judges if they can see the presentation.
No, we are not able to.
Okay.
Others?
No, not able to see.
Okay. We are seeing if we can like present as using a stronger network. There is some network issue.
So, Avanti, since we have the PDF file, why don't you actually share that unless they have some animation or videos?
Okay, I'll just do that.
Yeah. And while they are loading, the other team members can start describing so that it saves some time.
Yeah, someone can continue speaking about the project while the PDF is loaded.
okay. So for the project, right? Yeah. So we basically faced these challenges for machine learning that we had to work with missing data. So what we did was we basically extrapolated like the already existing curves to basically find the missing data and fill in. Then we had to like cluster and do the analysis of those clusters. We basically use clustering algorithms for the classification of these peaks. Um, So working with them was a bit difficult because there were a lot of outliers, and it used to like classify them in different categories. So we had a lot of different categories. We worked around this by limiting the number of categories and selecting certain metrics which were more useful than the other. Working with peaks that spread over multiple files was difficult. So basically, you had a very large solar flare, which starts on day one and ends on day 2 or 3. So there was basically an entire data set that was like that, and we basically had a difficulty because it was cut into portions. So we had to work with that missing peak. We worked around that by using all of this extrapolation and all, right?
Yeah, the PDF is visible now. You can talk on that.
Yes, ma'am. I think it was.
Yes. We have lost connection of the person who was speaking.
Okay, I see. If that's the case, I'll do it.
Yeah, please continue.
I guess he's facing some issues. I'm so sorry for that. So, okay, so as he was elaborating, the challenges that we faced in machine learning were basically fitting the curves to the peaks, which was basically we used a curve function which we fitted on the peaks that were already available. The challenges were in setting the hyperparameters for a perfect fit. Then, of course, as he elaborated further, I won't elaborate further because he already did. Okay, so moving on to the next slide. The pipeline, basically what we did in order to achieve this. So basically the input is basically a .lc file which we read using astropy table. The astropy table is then converted into PD data frame, which we can further use for processing. The second thing that we did was convolve the data to reduce the noise using a Gaussian kernel. We then fitted using an equation which was actually the integration of a Gaussian function and an exponential decay function. It was actually a convolution of them, which we actually took from a curve which we actually took from a paper that we'll cite at the end of it. Now, extracting the details. So basically, we use this fitted curve to extract various details that we did that we'll show you later on. Now, stitching the curves together, this is also a main feature of our this is so sorry for the background noise. Stitching the curves together, so this is also a main feature of our data, of our model, that we, in order to make it presentable, we stitch the overlap curves of two different peaks together in order to make it presentable. We used extracted files, then the parameters that we extracted using a model to classify. Present test connection is now available, so he'll continue now.
All right. Yeah. So here we have an example of a curve that is fitted over the function. Our function, we basically referred to a paper that was talking about how peaks are basically a integration of a Gaussian function along with an exponential decay function. We ourselves calculated the decay and the exponential function and its integration. We also did this scaling. We added a scaling factor for all this, and
I guess he is disconnected again.
I interrupt here. I need to remind that you are given just 10 minutes, so please check to see to it that.
Yes, just
I'll
2
complete it
minutes
within
are
2 minutes.
left.
Yeah, I'll complete
So,
it within 2 minutes.
please.
I'll complete the ML part here. So just this is our just clustering results that we clustered. We clustered it using a k-means algorithm, and we got these clusters. And then we used the standard procedure for clustering, that is on the basis of peak flux, and we also got the same results. So this indicates that clustering based on k-means and the other thing gives the same result. Now the WebD guys will tell you about the front end.
Hello. So now we'll continue with the front end. So basically, we faced some challenges regarding the front end part. So main thing was to take the perfect tech stack so that we can make both the website and standalone on the same front end, so that we don't have to make the front end different for
Hello,
both of them.
is the
So
presentation?
Yes, the presentation.
Presentation is visible. Please go ahead.
yes, so making the chart interactive as much as possible was a main motto. And since there were so many, around 80,000 points for a single LC file, so we tried to make it as interactive possible, so that there is the lag is as less as possible. And so some of the features for our were like custom file input, zooming the curve, raw and convol, peaks and fit. We can download the data which we get from the chart, and the documentation part also was also well written. And this is the link to the UI video. We'll be showing the live presentation, so we'll not be doing it now. This is a tech stack for machine learning and server, and this is for website and standalone. So one of our future plan was to make a feature like date picker, where one can select a date, and then he will be shown the date corresponding to that particular curve from the directly from the Pradhan website. So we can do this like from web scraping and all. So this was one of our plans, and these are the papers which we used for our project. And so thank you. This was for our presentation.
Okay, let's have the questions.
Rama, shall we go to the demo and then we take the question?
That should be fine. Yeah. So please go ahead. You can. I hope you have got the link for the data.
Yes, we are showing.
Okay. Go ahead with the demo. Yeah.
Team can begin their live demo presentations. Kindly avoid any delay.
Is I am audible?
Yes, please go ahead.
Okay, I am sharing the screen.
Yeah, you're audible.
This screen is visible?
Yes.
Yes.
Let me start it. This is what our standalone part, Linux-based desktop application. Currently, we are running this desktop application in Linux machine, and the UI it goes like there is input data and open manual. Open manual is the link to the our GitHub repo README file, and input data. Upon clicking on input data, there is an option for uploading file. We can drag and drop a file. Either we can select also upon clicking. So now we will go through the provided test data. First, we will go through the .lc file. After submitting, it will analyze the curve, and it will take some seconds because it is the curve. Let me show you the web part till now. For web part, this how our web application looks like. Let me reload it. This is how our web application looks like. UI is same for desktop part and web part both. Similarly, we can also select the files there. Okay, let me move to the standalone part. Okay, this is the standalone part, and here result of the here is the result of the analyzed curve, and here is the table of the peaks detected. There is the 6 peaks that we have detected, and there is a raw data. This is the raw data, that time and rate graph, and this is the concolor data after smoothing the curve. There is a sliding we can, so that we can we can bigger the graph, and there is toggling option, and we can zoom the graph, span the graph, and there is a reset button, so that graph can be resetted to original standard. Here we have called, and here we have the toggle fit curve that basically fits the curve. This is the fitted curve, and we can also indicate the peaks by clicking on toggle peaks. Okay, this is the our peaks. Let me reset the view. Okay, we can zoom and see peak 1, peak. These are labeled as peak 1, peak 2, peak 3, peak 4. And we can again reset it. And we can, if we want to see only rate curve, we can just remove the fit curve. Now fit curve is removed. And just if we want to see the only fit curve, we can remove the rate curve. We can toggle the peaks, and below there is some remarks that regarding the category and peak counts. And here there is table. In table we can slide it, and there is parameters like peak, category, decay time, rise time, peak flux, peak time, start time, end time. All the parameters that we have deduced from the graph given data. Now we can download these all data in a .txt format upon clicking on download the logs. Upon clicking on download the logs, here we can save it in form of solar.log.txt. Let me save it on desktop. Okay, it is saved. Now let me go on desktop, so we can see where is solar.txt. Here. This is the analysis of the whole data. That is the background flux that was 6.74 peak in peak 1, peak 2, peak 3, peak 4. Every peak has its details, category, decay time, rise time, peak flux, peak time, and that's all. And this, let me show you the website. In the website there is a similar UI. Just there is also the table, and
Yeah. Can I interrupt? Yeah, we will move on to the questions. Yeah, the demo is clear. So can we have the questions from the members?
Yes.
May I ask a question, Rama?
Yeah, please.
Okay, so during your presentation, you mentioned something about clustering. So why exactly you need clustering in a two-dimensional data analysis?
Hello?
Hello, anybody from the group?
Yes, just a minute.
Yeah. So we weren't working with two-dimensional data. We basically had 3 hyperparameters. Yeah. Yeah. So regarding the question, we were basically extracted 3 parameters, hyperparameters, that included decay rate, rise time, and peak count, which we used to classify the peaks. So we were not classifying them into 2 dimensions or anything. We were basically classifying them on the basis of these 3 parameters. So you could say that we were using 3-dimensional data for this.
Can you expound on what was the rise time and decay time?
Hello?
So the rise time that we calculated. Hello.
Yeah, you're audible. Please go ahead.
The rise time that we calculated was basically we calculated the time for peak flux, and then the start time which we got from our curve, we subtracted the peak time from the start time, and we got the rise time. We got the start time by extrapolating the fitted curves and the point where it meets where the background flux plus standard deviation meet the start time. The background flux plus standard deviation, where the point where it meets the extended curve, that points were taken as start time and the end time respectively, and we subtracted the peak time from the start time to get the rise time, and the end time from the start time to get the decay time.
How was the background estimated?
I'm sorry, are you asking how was the background calculated?
Yeah.
The background was calculated. So basically, we used a SciPy peak width function to get an approx estimate of that is just the approx estimate. We didn't use the peak width to calculate the start and end time. We just used the peak width to get the approx estimate around the peak. Once we got the approx estimate around the peak, we removed that peak width from the light curve data. So for all the peaks, we removed the peak width, like the portion of the peak width from the entire data. And for the rest of the data, we calculated the median. The median was found to be a better approximate of the background. And the standard flux was calculated from the removed data, from the data which we removed. And using the removed data and the background flux that we got, we calculated the standard deviation from that.
So your background can be, meaning if there are some peaks which are not removed by the SciPy, the peak finding algorithm, then the smaller flares can also be counted as background in your data. So did you attempt for not missing the smaller flares? Like, were there any thresholds which you could play
Yeah,
around with?
there was a threshold for peak detection. We used 40 counts per second as the threshold because in a lot of data we actually saw a lot higher peak counts, and also whatever information we could receive and whatever data which we observed, we saw that the appropriate amount for the peak flux count. So we took the threshold to be 40. And regarding background data, yeah, this is one issue that we wanted to do it, that we wanted to make a background data variable, because like we mentioned in our challenges, one of the problems is like if suppose like I still remember a file. There was a file in which 25,000 accounts per second was there at the end of the file, and for the next file, the entire flux was decaying from 5,000 to around 500 for the entire file. So for that kinds of file, it was really tough to calculate background data, or we can say that our algorithm will actually not be able to detect, because like in such curves where the entire curve is formed by a decay function of very super flare, I can say, then in that case, we were thinking to make the background data variable, but that is what we will do in the future. We have to calculate accurate background data, but calculating the background data as median, actually, if even if we detect the smaller peaks, because we are calculating median, not mean, so we found that the shift from the actual background flux is not too much, just because we are calculating the median and not mean.
Okay. So if there is an option, can it be provided, like if you include varying the threshold from 40 to lower values and allow the peak to detect more shorter flares, then would it be because now out of the given the from the demo you were able to pick just 6. So varying the threshold, could it have resulted in picking up the smaller flares and also give a better estimate of the rise and decay?
Regarding smaller flares, yeah, I think that reducing the flare counts would be able to detect smaller flares. But we have one condition that, for example, if that is the basic condition for a flare, that it should rise steeply and fall because in order for our curve to fit to the peaks, the peak should be like the peak should be at least similar to a flare, or maybe it can be a overlap of multiple flares. That is also fine with us. But what we want that it should be a peak, because if it is a background data, then the curve that we are fitting won't be able to fit, and in that case we remove those peaks. So there is two criteria for removal of peaks. One is the threshold, and the second criteria is if the peak flux is above is sorry the peak flux is below our f threshold, which is f background, the background flux, the background count plus the standard deviation. So if it happens that your peak count is 25, but what we observe, but your peak count is 25, but what we observe in the light curve is that most of the data is around 25, or the most of the data, the background data is around 25, then in that case there will be a problem. So, but if the data is like it starts from around 10, then we have a peak of 20, and you set the background to the threshold to 20, then it will be able to detect that 20 peaks, and it will also be able to perfectly detect the start and the end time. But if the background is around 10 and you're trying to detect something like 12 or 13, then there will be a problem.
Did you also run all three files? I mean, is your front end can take care of both CDF, ASCII, as well as the pitch files?
Okay, so someone else was speaking, but I guess he's not audible, so I'll speak on his behalf. Hello, am I audible?
Yes, please.
Oh, okay. So like we were able to detect, we were able to work on .lc files, but it's not like that we cannot work on .txt and .nc files. The only reason that those files will not be, we are not able to run those files is because actually we actually need the format beforehand. Like we saw the .txt file, like it didn't contain headers. So like we can modify our code to input multiple files, but we need to be provided with the format of the files beforehand. Only then we can do it, or else like it will throw an exception.
Okay, so CDF also you are not able to run.
So we were able to use .lc files, but we were not able to use .txt and .nc files.
Okay, thank you.
Just to confirm, 6 flares were detected. Right?
Sir, like we can .csv we would be able to detect, because if .csv is provided and the columns are like capital time and capital rate, then we would be able to work with it.
Okay, so what I understand, current configurations can input the .lc file and the .csv file, right?
Yeah, any files which consist of a table, it can input it.
Okay.
Are there any other questions?
Yeah. Shall I ask, Rama?
Yes, Srijit.
Yeah, I'm going by your document which you are in your Git repository. So what I understand from that is that you are basically first using SciPy to find the peak, and then using some function to find a peak width. So how do they find the peak width? Because I find if you look at your own fitting curves also, the width you chose seems to be a little wrong. So you have any idea how do they find the peak width, or is it just black box for you?
So the SciPy functions that we used, sir, we got the peak width using that, but that peak width is not the start time and end time that we reported.
No. Wait, that I'll come to that in a moment. But do you know how they find the peak width?
So the SciPy functions, so there are parameters that we can tune to get a better peak width, but actually we don't know the internal procedure.
Okay, why I'm saying is because you are saying you are not using that for fitting. I understand that, because you are using, when you calculate the median, you are removing only the data above or in that region within peak width, right? So if your peak width is not rightly chosen, if it is choosing if it is very small, for example, then a lot of signal, the actual flare data will come to your median, which is going to will get you a large value for your median, right? And then you are removing the median to find the background. So it is affecting your whole analysis from that point onwards. That's why I asked you why.
I would like to say something on this.
Yeah.
There is the SciPy peak width function. We input a parameter known as prominence. Sorry, relative height. So we take the relative height to be 0.63 as in our hyperparameter tuning. So what that does is that it takes your height from the baseline and takes the 0.63 portion of it, cuts the peak at that particular part, and the point where it cuts the peak, it reports that difference between those points as peak widths. So upon tuning those parameters, like we tried tuning it to the like most of the curves. So tuning those parameters, we can like improve the efficiency of a model. So we basically the two things which our model depends upon a lot is find peak function and the peak width function. So the main importance is to find the right peaks, and to get the once we find the right peaks, we will be able to get the right width by adjusting the relative height.
Yeah, so since that option is not given to the user, you have fixed it at 0.63, which means that if there's a big flare, 60% of that is almost taken as considered as a background, basically when you calculate your median. And then you subtract median to get the background, right? So it may be good if you could have made it, let's say, 30%, 20%, or if you could have given that option to the user to choose what they want to decide where the background is in a way. That is point one. Second point is then you are fitting with something, some function. Neither in your document nor in your presentation, you didn't say what function you're fitting, because you need a theoretical model to fit, right? So what function are you fitting?
Actually, we used, if I could share my screen right now, I could show you the function. We used an exponential function.
Exponential function?
Sorry. There was some background, so I just got it. We used a Gaussian function and an exponential function. Can I share my screen again to show you the exact function? We mentioned it in our presentation, but we mentioned it like we took it from the paper, and we mentioned it orally that we.
Okay, I understood. Gaussian plus exponential with a negative
exponential decay
index,
yes,
right?
with a negative index. Yes, we integrated it.
I know from which paper you got it. It's okay. No need to share.
It was from the paper that you cited in the problem statement.
Okay, understood.
Can I ask one question?
Yeah.
Yeah. So for the clustering, you used only time starting time scales and end time scales. But in the fit equation, you had more fit parameters as well. Why didn't you choose those parameters for the classification clustering?
Like we used peak flux, the rise time, and the decay time for clustering. Those were the three parameters. The rest of parameters that are given in the table are start time and end time. Am I not audible?
Yeah, you are audible.
Yeah, you're audible.
So the rise time, end time were so basically the start time and end time basically depend upon when you start. What is your starting time for the day? So we thought that would not be a right measure. So we took the difference, that is the peak time minus start time, and the end time minus the peak time, that is the rise time and decay time, as the parameter. So we use those three parameters.
Okay.
I think just to clarify, I think Abhilash asked is, in your fit function, there is A, B, C, D, right? 4 parameters. It's not directly start time or end time or anything. I think what he was asking is why you didn't use that for your clustering.
Yeah, that's right.
Yeah.
We initially used like ABCDE. One of our teammates did that, but he did not find any presentable results.
Okay.
Basically, the XDB clustering. Lot of the fitted curves in which the data is missing, that was being classified as an outlier. So at the end, when we saw the clusters, it was not very presentable. We used A, B, C, D, and E. The parameters that we got using the curve fit, we actually used them, but there were no presentable result. Plus, we couldn't tell them what they physically mean. So we thought that even if we present them, there would be no physical meaning like that we can interpret from those A, B, C, D, E. So we thought of presenting it using that, physical parameters.
Yeah, thank you.
Okay then. Thank you. We'll move on to the next presentation.
I'm sending now.
Thank you. Thank you.
Thank you.
Team 17, I have granted you the stage access. You can go on with your presentations.
Akshay. अरे should I send mail to team 9? Team 8.
A very good morning to one and all
Team 8
present
को भेजूं
here.
मैं?
This is Team 17, and we are going to present our approach for resource problem statement involving identification, characterization, and classification of X-ray bursts and provided light curve files. So the problem statement involves using a pipeline to process noisy light curves obtained from observations made by Chandrayaan's XSN and identifying the flare candidates. We will be estimating the flare characteristics such as rise and decay times, peak flare, peak count, and then pre-flare background and decay rates, things like that. And then we'll be developing a statistical and machine learning model to classify the X-ray bursts into clusters. And after that, we will be deploying our solution in a standalone application or a web-based tool. So this is the flow chart of our approach. We start by importing the data. We handle some of the formats like text and ASCII, and we proceed to pre-processing, after which we extract the features and combine the results in a CSV file. A part thereof is used in model training, and the ML model is imported in and then is used to generate a new class, a new column in which we present the classes of the identified X-ray bursts. So once this thing is done, we can deploy it as a web app and as a standalone application where the user can provide an input and an interactive output would be generated. So the first task is identification and characterization of the X-ray flares. So the first thing is pre-processing the noisy light curves. What we do is, first of all, we identify continuous stretches of data and then resample them to ensure uniform sampling durations. After that, we apply a Savgol filter for reducing the noise. Next, we proceed to downsample the data. So downsampling is going to reduce the noise further. And then we do random forest regression to kind of get an average trend of the data. This helps us in avoiding getting a lot of maximas in our data, because finding the maxima is what our flare identification depends upon. Next, we use cubic line interpolation because the results obtained by random forest regression are a bit rough. So we can generate a smoother curve by using cubic line interpolation. Next thing is identifying the flares. For identifying the flares, we use a smoothen light curve and then identify the peaks, uh, which are basically local maximas in a certain neighborhood. So once that is done, we adjust them depending upon whether we find more suitable maximas. By which I mean to say, let's say we have two identified maximas, but there is another maxima whose value is higher than the two, then that is also added. And then once this is done, we can proceed to fitting. So for fitting, we are using the elementary flare profile as specified in the following reference. So once that is used for fitting, we can identify parameters such as decay rate, rise time, decay time, peak flux, and peak flux over the pre-flare background. At this stage, we are eliminating some of the flare candidates which have a signal to noise ratio of less than 0 decibels, and which are giving us non-physical estimates of flare characteristics. For instance, let's say the rise and stop times are becoming really, really huge. So they are not actually flares, but they are artifacts of our light curve processing stages. So this is our first level of outlier detection. The next thing is comparison of light curves. So we have our raw data provided over here, and this is what we find as the final interpolated result, final light curve. And the crosses specify the identified flares. So an advantage of this kind of process is that we don't need to have the record of all the peaks available. If we find a increasing and decreasing trend on the left and right sides of a particular peak, we would be to certain extent identify the peaks even in that circumstance. The next task is classification of the flares. For this, we are using a k-means clustering algorithm. We are training the model over 141 days out of 713 days of provided data. The small amount of data is used in order to meet the requirement of using only 20% of the available data set. The clusters represent the categorization of the flares based on the flare shape, because we are using parameters like the rise time, decay rate, and the peak flux in our clustering algorithm. So the flare shape is a signature of the physical processes which are occurring, and that is why we are using all these parameters. We can do further investigation into the identified clusters to find if there are any physical differences between those flares. So we have identified the following flare candidates, and I'll be going into a brief description of them. So the first kind of flares are identified as fast bursts or F bursts, which have a rise and decay time of less than 5,000 seconds. The next group shown in yellow over here is the slow symmetric bursts. You can see that the rise and decay time are roughly of the same order, and they are also really huge. So it is a slow rise and decay process. Then we have the slow asymmetric bursts, which are shown in blue over here. So for them, the decay times are huge, but the rise times are of the same magnitude as for the intermediate classes shown in green and teal. The green one is intermediate type A, and teal is intermediate type B. Further details on these are provided in these slides, which I'll be skipping. We'll be going over visualizing these clusters. So the first plot over here shows decay rate on the x-axis and decay time on the y-axis. So for most of the classes, there is not much variation in the decay rate, but for the fast burst, there is a significant considerable variation in the decay rate. Also, the decay rates are lower than 0.005 per second for the other four classes apart from the F bursts. Additionally, we can see that if we are plotting rise time on the y-axis and then plotting the clusters, we'll see that the slow symmetric bursts have huge variation in terms of their rise times. Now we have, let's say, plotted the clusters based on decay time on the x-axis and peak hour background on the y-axis. So here you would see that the differences between the green and teal clusters, which are intermediate type A and intermediate type B respectively, become more palpable. So for the decay time of intermediate type B clusters, we have it lying from 5,000 to 10,000 seconds, and for type A, it is from 10,000 to 20,000 seconds. Additionally, we see that peak hour background does not help us uh, classify these clusters in a very meaningful way, because only some of the peaks are large, but most of them are of intermediate values. So just using the peak above background or the peak count of the fluxes is not going to give us enough information about the physical process which are causing the flares, because informations like decay rate, decay time, and rise time are not being counted for. So this is what we have done in our clustering. Now the third task is the deployment of the model. So we have deployed the model as a standalone application as well as a web-based tool. So for initializing this, we'll need to run the XSM modgen code uh, to generate the pickle file. So this is done so that the pickle file is generated locally and there are no inconsistencies within the Python versions from one device to another. And it doesn't take a lot of time. So the initial setup takes like 2 to 3 seconds only. So it is convenient to do it locally. And then we proceed onwards to the FITS and ASCII file handling stages, and we can specify whether we want to save the images. The CSV files get saved by default, and we can also specify whether we want to interactively view the images. The web-based tool is a Django-based application, and the front page gives you an option to input the files, and multiple files can be inputted at this stage. And then once you press enter, you'll be redirected to the next page where you can see the interpolated output for the light curves, and you can zoom in into individual sections and view them more clearly. The CSV files can also be downloaded from here. Now, what are the caveats and possible improvements? So, first of all, for handling the ASCII data, we need to manually add time and flux headers on the ASCII file, and additionally the time variable needs to be perfectly numeric so that the tool works. Also, we have used data only from June 2020 onwards, and that consisted of a lot of data which had a lot of non-continuous data. So the model is relying on having non-continuous stretches of data and then fitting and smoothing them individually and separately. So it is possible that if we get a large stretch of continuous data, the model might not be able to work very well. The next thing is we are using some fitting and SNR based criteria to reduce the list of flare candidates in suitable flares. And this is not a very perfect method because we might have some false positives and false negatives. We might have some artifacts of light curve crossing stages get classified as actual flares, and there might be some nano flares which might not get detected. And this is why we need to do further work in refining the light curve processing stages. We need to be able to handle continuous stretches of data. Additionally, we also need to be able to like work over the numerical methods, smoothing filters, and regression techniques so as to perfect them further. Additionally, for reducing the number of false positives, we can use machine learning and statistical methods for detecting outliers in vector distribution. So whatever the vector of features we have, we can find outliers in them, and then we can see if they are actual, if they are false positives or not, and we can try and see if that method works. So this is an example where we are getting some false positives. You'll be able to see that here we are getting a green cross, but this is not actually one of the peaks. So that is all from my side. Uh, Now we can proceed on to question and answers.
You can go ahead with the demo. The data file is shared with you, right?
Yes,
So can you please go ahead with the demo?
over to you, Sagar.
Hello. So can you stop sharing your screen?
Sure.
I hope my screen is visible.
Yes.
Okay, sure. So this is our web application. So I'll first upload the files here. So here we get the results for all the three files. So first of all, before we delve into it, I would just like to say that the first and the third light curve is something we have taken directly from the Pradhan website. And the second light curve file is what we have received just now as to show in the demo. But the thing is that we are not getting good enough results in this because our code at the present assumes that we'll get disjoint data, so that we willingly tuned our random regression that way. So it will require some small changes, but this we are any ad not going to get useful like inference from what data we received. But for example, this is a sample light curve that we had received a few days ago, and it was in ASCII. So this is somewhat. So from here, we can observe the detected flares and their peaks. And this one is taken from the Pradhan website. Even here, we can see the smaller intensity flares and this big flare. And then, of course, the one shows the entire light curve shows there when the right pane shows the zoomed in version of where I'm hovering my mouse. And accordingly, for each and every flare, we can download a CSV file for which we'll get the parameters. So, for example, if we download the CSV file for this, we'll get the peak time, peak flux, decay rate, and all, and even the category of flare as how Daniel had just made the presentation. So the web application. Now I can name the standalone. So basically, our input in the files directly here. Files are LCM, so cool. We can directly go ahead with running this script. It basically first detects that yes, we have 3 input files. Now I'll go ahead with saving and viewing the images. So basically, and here you can zoom in according for zooming in and recapping this and uh, for which we not getting. So this is the file we have
Here,
presenting results.
I have a question in the previous slide, the previous plot which you showed. So the previous plot,
Yes.
although there were many flares, it was putting it like a continuous rise, right? So why is that happening? In the this one,
This one.
this plot here on
Uh,
the left. Yeah, this is like your fit to the data is like all flares smoothed out and it's a continuous fit, right? So hello, am I audible?
Yes, ma'am. Yes, ma'am. So, for this particular, this is a limitation of because of what data we had considered while creating this model. So we had taken the data only from 6 June 2020 onwards, and we found out that most of them were discontinuous, and so we assumed that it was the same for all of them. So all discontinuous stretches of data are fitted with a random forest regression model. So in this case, what is happening is the regression is happening over the entire stretch of the data. Instead of identifying the peaks, it is rejecting everything. So uh, that is a serious limitation and an oversight.
While for the other shorter spans of the data, it is able to do the fit for the peaks. So what is the difference? What's
Uh,
happening in that?
Ma'am, what is actually happening is we are doing something to identify where we have continuous stretches of data. So, if there is any duration of data where, let's say, the difference between 2 points is greater than 100 seconds, then it is treated as a separate stretch of data. So, the smoothing and regression is done separately for all the separate stretches. But since we have this entire light curve as a single stretch, so the smoothing and regression is happening all at once. So the intermediate like layers are getting rejected, but this is happening because of random forest regression. We'll need to change some of the parameters here, and maybe we'll be able to handle it better.
Okay, your screen is not visible now. Can you project it?
oh, okay. Sorry.
Sorry.
Is it visible now?
Yes, yeah. Yeah, so in your first plot up there, how, meaning what is happening that you're detecting these shorter flares as well as the peak?
Ma'am, what the thing is happening is that we are using a separate curve, a separate cubic curve for each of those small sections.
So it's basically a
Because all the
smoothing which is happening there.
Yes, ma'am.
So
The individual continuous stretches of data are first being smoothed, and then random forest regression is being done to find kind of the trend of the data, whether it is increasing or decreasing. So let's say we have some increasing stretch of data, and then it is discontinuous for a while, and then there is a decreasing stretch of data. So the code is going to identify that as a peak over there and estimate what roughly the peak is going to be in those regions as well.
in and around that 85,000 seconds, actually it's a data gap wherein the algorithm is finding it as a peak, isn't it?
Yes. See, actually, zoom in that region, there was a bit of increasing trend over there after the first peak. The major peak over here, and then there was a little bit of increasing trend of data. Yes, we can zoom in. Yeah, after that,
So
move a little bit to the
yeah,
right.
basically it's a data gap, but it has picked it up as a rising trend there, which is not
Yes,
correct. Yeah.
yes.
Yeah, so this is happening because this data smoothing is done along with the data gaps, and the rising trend is picked up as a flare. Yeah, which is it's not the right thing to do. Correct?
May I ask how was the data interpolated for the data gaps?
Yes. So first of all, like I said, we are trying to find continuous stretches of data. So for each continuous stretch, we are doing smoothing and regression. And once that regression is done, we are resampling the entire data at 1 second sampling intervals, and then we are using cubic splines. Uh,
So
in a
what
cubic
kind of
polynomial.
can you expound on the regression? How are you? I mean, have you trained the regression data set? What is the model
Uh,
you are using?
it is random forest regression, and there are some parameters like number of trees we are
So
using.
what was your training data?
There is no training data. It is happening
Just
individually
on
for
that.
each of the. No, sir. For
Okay.
instance, we can think of linear regression. So some data is given, we are finding the best fit plot. So random forest regression is doing the same thing. It is finding a best fit over there for that continuous stretch.
So like we are training it for each of these curves. Every time we are feeding it the data, we are training it to find the best regression
So
model.
training data is the given data itself, right? There is no pretend some model is there.
Yes, it is kind of finding the best fit after the smoothing is done.
Do you think it's doing good job of finding the trends?
Uh, for some cases, it is good, but for especially for small peak count flares, it is not performing really well because it is not able to identify. Sorry, it is not able to distinguish non-flares from artifact from actual small peak flares.
Maybe instead of splines, why don't you actually try a running average? That may be a better actually smoothing algorithm. And also, is it possible to plot the smoothing like on this? So that might actually tell us why this is picking these peaks.
Smoothened light curve, yes, the red one is the final interpolated result. Uh, but we should be able to make a small change in the code and get to print it. So can we do that now?
Maybe you can share later.
Okay.
Are there any questions?
Just a question. So how many data set you could run and how many of false positive and true negative?
Uh, we haven't actually found out the exact numbers for this. But like in particular in like 10 to 20 data sets that we ran just for verifying it, uh, we were able to see like 3 to 4 false positives. We didn't actually saw any false negatives. We didn't actually see any false negative, except in the cases where the two flares are very close to one another, and thus it is not able to resolve those two separately.
Okay, thank you.
See, as Rama already pointed out, in your what you are doing, I think the problem is you are believing that by smoothing you can identify the flare peaks. In your document also, you wrote that exact sentence that as it is evident from figure, smoothened light curve can be used to identify the flares, which is not a correct statement. I think that's where you went wrong, because when you smoothen, unless it's a proper smoothing, you may miss many of the flares. Even in this case, why your algorithm failed to detect any flares is because of power smoothing. I think you would have understood that problem.
Yes, sir.
And second thing is, you are saying that you are fitting it with the same whatever given in that paper, which is Gaussian plus exponential decay, and then you are using clustering algorithm. So it is not clear. So is it? Are you using this smoothened data points for clustering, or are you using the fit parameters for clustering?
Using the fit parameters.
So we are using the fitted parameters.
Okay. So you're using all that A, B, C, D, E for clustering, right?
Yes, sir.
Okay.
Not actually, sir. I mean, for instance, the peak time and rise time and decay time, those are absolute numbers. But we are actually trying to find durations and then using them to train the classification.
But that parameters, whichever that function, it may not be exactly give you start time and all, no?
Yes, sir. Yeah, that is true.
So are you finding it separately, or you're just assuming one of the parameters start time and no, I didn't get.
Yes, sir. So whenever we have fitted it, we are getting the continuous stretch of, whenever we are fitting the elementary player profile to
Yeah.
one of the identified player candidates, we can get the parameters. And from the parameters, we are trying to find whether it is intersecting the pre-player background plus the noise level, plus like sigma of the noise level, within a certain 40,000 seconds on each side noise duration. So the rise time cannot be greater than 40,000 seconds and the fall time cannot be greater than 40,000 seconds.
Yeah, another mistake you're doing is here is you are fitting the whole day function, whole day data with one function. Whereas in reality, each flare is individual events. So maybe you'll have to find some way of individualizing or choosing certain time slots and then fit only those data with this function.
No, sir. Actually, what we are doing earlier is we are trying to find the peaks, and then between each peak we find a minima. So
Okay, you're
between
looking
two
for a
minima,
minima.
that is one stretch.
Okay, okay, fine, fine. So while smoothing, you are missing the minima. That's what is happening. Okay,
Yes, sir. That is a severe issue.
yeah, yeah. Okay.
Okay then. Any more questions? Or if not, shall we move on to the next presentation? Yeah. Thank you so much.
Thank you.
We will have the next presentation.
Next team 8, I'm making you the attendance kindly. I am not. Team 8 can now begin their presentation.
Sure thing. Just give me 1 minute. Oh, 5 seconds.
Sure. Okay. Sure. Good morning, everyone. We are Team 8. We are Team 8, and Project Heimdall is our solution to Isro's web-based automatic identification of solar bursts in X-ray light curves. Project Heimdall is our standalone web application using Streamlit.io to identify and categorize X-ray bursts. Why call it Heimdall? Well, Heimdall is a mythical figure in the Norse mythology who is all-seeing and nothing escapes his observations, even light. He is also a popular character in the Marvel Cinematic Universe. Thus, we named our project after this geeky fact. This is the thought process behind our solution, Heimdall. The idea is to perform automatic identification of solar bursts in X-ray light curves. First, we deal with the data. As input, Heimdall asks you to upload the relevant light curve file, and the output is time and rate values, which are generated. In the next section, Heimdall analyzes the wavelets obtained from the previous values and extracts further derivative properties. The detected peaks are visualized separately, and their properties are then tabulated. Finally, the solar flares are classified using soft X-ray classification method, and this results in Project Heimdall.
Okay, so let's now talk about the raw data. The zip folder provided on the website contains FITS, HK, and SA raw files, and LC, GTI, and PHA as calibrated files. We use the LC files as input to our app. Before diving into the software, let's briefly discuss each file type. The FITS file is the standard in storing and analyzing astronomical data, while the GTI file is generated using the HK and SA files in the XSM data analysis software. The LC and PHA files are generated from XSM Level 1 science data for the desired good time interval, that is GTI, with the required set of parameters using different modules of XSM software, which are XSM Gen LC and XSM Gen Spec. The following flowchart shows the calibrated data generation. So once the app is up and running, you will be greeted with a very simple upload feature to choose the desired file type. Now, one of the important features regarding data input is the file type compatibility. Heimdall supports the following file types, that is LC, CSV, ASCII, TXT, and various other file types that are visible to you. The data from these files is extracted using a Python library called AstroPy. The time and rate arrays taken from the previously mentioned files have been plotted. The graphs are interactive, thus providing the user the ability to scroll and zoom through the values. The next section introduces noise reduction. Output files generated by the last section have certain background noise. Thus, to remove the fast oscillations and low-scale features which amount to unnecessary noise, we apply time averaging techniques with a window length of 500. A code snippet has also been provided, which shows that we take the mean of 500 samples and to average out and reduce the noise. The filter data has also been plotted as an interactive graph. Okay, so once we have the filtered rate values, we get into the detailed analysis of the data, which starts with peak detection facilitated by find peaks and peak prominence methods. These detected peaks needs to be segregated, and finally, the wavelet analysis of each peak concludes the process. So as mentioned, the initial step is peak detection. Here, find peaks and peak prominence are inbuilt methods in the SciPy library. Find peaks takes a input a 1D rate arrays and finds the local maximas by comparing neighborhood values, while peak prominence measures how much a peak stand out from the surrounding baseline of the signal, which takes us to peak segregation. So in peak segregation, for each peak, the minimum value is identified before and after the peak value to isolate the burst. The rate and time values for each wavelet are stored for further analysis. For example, in the plot, you can see two peaks segregated by the above defined algorithm. Finally, dealing from all of this, we are now ready to get desired properties from each of the wavelet, which are number one, peak flux, that is the maximum rate value for each wavelet. Next, the rise and decay time, which are where the rise time is defined as the time a signal takes to go from 10% of the peak to 90% of the peak, and decay time, which is the time a signal takes to go from 90% of the peak to 10% of the peak. The next is total flux, which is calculated by integrating between the start and end points of each wavelet using the Simpson's method, which is already implemented in SciPy. Being equipped with all these properties, we can now classify the flares. This classification was performed using the soft X-ray classification system. The reason being, it is based on the same parameters that we followed in the analysis. In this system, the flares are classified into A, B, C, M, and X classes according to the peak flux of the flare. A class being the smallest, followed by B, C, M, and X. Each of these letters represents a tenfold increase in the energy output. Ahead lies the development part of the web app, which will be presented by Nishant.
The tech stack for Heimdall is simple and elegant. We use Streamlit, an open source Python application framework that helps us build data visualization scripts into web applications. We then use Python-based libraries like NumPy, Pandas, Matplotlib, and SciPy to aid in the data analysis. Finally, we use Nativefire, an open source command line tool used to create a wrapper around hosted web applications. Apps are exported via Electron into an OS executable that's compatible on Windows, macOS, and various Linux distributions. Deployment. For local deployment, 2 commands is all you need. You need a pip install that installs the required dependencies in your virtual environment, and you need Streamlit run app.py to start the application itself. After the above steps, you can easily deploy the project on any server. For our showcase, we deployed Heimdall on a service called Heroku and linked the same in our documentation. We've also provided standalone executables to increase accessibility. We use Nativefire to wrap a Heroku deployed app into an easy to distribute standalone app compatible with macOS, Windows, and Linux distributions. What makes Heimdall stand out? We have performed our analysis on the light curve using statistical inferences. The second part is it's easily deployable. In just 2 steps, Heimdall is up and running. It's lightweight and scalable. The executables provided is around 50 MB, while the repository itself is around 740 MB, and there are minimum third-party dependencies. The application itself is not that resource intensive. You don't need any computing overheads like load balancers, routers, databases, etc. And given how easy it is for the scientific community to use our application, it's easily distributable. As you said before, we can distribute it over Windows, Linux, and macOS. Potential enhancements. Well, the first thing is curve fitting. A characteristic solar flare equation with 4 tunable parameters can be used to fit every flare curve. They will enable us to create a mathematical model for the equation, which will improve the accuracy of the parameters defined. The second part is separation of superimposed solar flares. This will help in separating overlapping peaks in the data, which is possible using the generated mathematical model. These are our references that we've used for your perusal. Thank you for your time.
Okay, can you please go ahead with the demo? Hope the data files are shared with you.
Yeah, sure thing. Just one moment. Is my screen visible?
Yes, please go ahead.
Yeah, so like I said before, all you need to run is Streamlit run. Since we've already installed the dependencies, we don't need to pip install. So we run Streamlit run app.py. And it gives us a URL. As you can see here, we're greeted with a very simple interface where we click on browse files, and then we select our the test data that they've given us. Here, I choose an LC file, and then it's processed. As you can see up in the upper right corner, we actually have a running status here that tells you the status of our application. So if you need to know if the application is running or not, you can actually look up here. So in our first section, we visualize the raw data input here, and we present it as a graph, where the x-axis is the time and the y-axis is the rate. Also note that our applications have several features where you can save these graphs as SVGs, PNGs, and source files. You can also expand the graph individually in order to display it better. And even since it's interactive, you can actually zoom in and out and even look at particular points. In second section, we visualize the data after noise reduction. Here you can see the visualization, but again, the x-axis is the time, y-axis is the rate. And as I mentioned before, you can even save this graph in various formats. In the third section, we have peak detection, where we use the previous methods discussed in the slides. And here we visualize the three different peaks after segregation. Finally, we have wavelet analysis, where we tabulate all of the properties of the detected peaks in order to display it. Finally, we have the LC solar flare classification, where we use using the soft X-ray classifications parameters, we classify the peaks into their respective classes. As I mentioned before, another fundamental advantage of our app is the fact that we actually have an executable ready. Since I'm on Linux, all I need to do is run the executable itself, which is just /Heimdall, and it opens up an Electron application, which directs me to the same website that we've seen up and now. Here, once we once I choose the same LC file, it loads it up into our servers, and then the same you can see it process. The same executables are available for Windows and Mac OS, where all you need to do is actually click on the executable, and you don't need to run it on the command line. Okay. With that, we end our presentation. Thank you.
Thank you. So the peak detection which you showed as in parts, can you go back to your, can you show the slide?
The slide with the demo?
The peak were shown like in segregate separate windows. So do you search for the peak in, so what is exactly happening there? How is that detected?
This one, right?
Yeah, yes.
Okay, so for peak detection, we are using the find peaks and peak prominence methods already implemented in SciPy, right? So what find peaks does is it basically finds the local maxima, right? And what peak prominence does is using all those peaks detected by find peaks, it basically finds all the peaks that are above a certain threshold, which depends on the data, and like basically returns the maxima for that peaks.
And how is the threshold defined?
So currently we are defining the threshold as like half of the sum of minimum and maximum of the data.
Can you take us through one example? One you had found 3 flares, right? Can you just take us through one example? Say second example where you found actually 2 peaks in one peak. Can you go to the second one? Second flare. Can you just tell us what is happening here?
Okay, so what we basically did is using the find peaks method and the peak prominence method, we found the peak, right?
So there are multiple local maximas here. So which peak exactly did you find?
The maximum value towards the left. So basically what it does is like find the local maxima in a certain region, like a local region, right? And then what peak prominence does is it like basically filters out all the peaks below a certain threshold, right? And
We don't hear you.
I believe Simardeep got disconnected. He'll just be joining back. Simardeep?
Nishant Arya, I have a question. Instead of actually fixing the peak value, whatever the peak values you are saying, why don't you actually identify the peaks and try to see whether the flares are real or not. Because if you see the plot, just the light curve plot, you can see that the number of peaks the number of bursts seems to be more than whatever the number of bursts you are detecting.
Sorry, can you repeat the question?
See, looks like you are missing lot many bursts because you are showing only 3 bursts. Your algorithm has detected only 3 bursts, maybe because, and I don't even know which are those 3 bursts, because hence I can't say whether it is because of the peak value or whatever the number you are fixing. You mentioned something like you take the average and put it at a half or something like that. Instead of that, there are many algorithms which can easily find the peaks. And why don't you try and see whether they are real bursts or not? That might increase your chances of success, right?
Yeah. But as far as like we tested on different like data files, for us it was giving us pretty accurate results. Like we like played around with different thresholds and different window lengths and all, and once we found the best fit for us, it was giving us like pretty accurate results.
Yeah, the problem is, then again it depends on the entire data set, as Srijit mentioned in our earlier this one. So we are the solar burst can be a local phenomena, whereas you are if you take the entire data set, it might be day or 1 hour or 2 hours. So that binning or splitting of the data also will be a problem for you, or it will also have some effect on the identification of the burst, right? So how do you remove that bias?
We can like uh, change our algorithm to like basically search in a local area, right? And um, so like that could work, like I think local, like finding local peaks, that would be I think my solution.
Yes.
Shall I ask Rama?
Yes, go ahead.
Just first question is, why do you think you got only 3 peaks in this test data? What is your immediate judgment? What would have gone wrong?
Yeah, can you just plot that? Can you just plot that test data when you are answering that question?
They don't want to.
Hello, is anyone from
Excuse me.
team 8?
Yeah, could you repeat that again, please?
Yeah, I was asking the test data, you could identify only 3 flares, right?
Yes.
What is your immediate judgment why it detected only 3? When there is obviously many more flares. If you look at, can you show that screen in your whoever was
Sure thing, just
showing?
1 second. I think you can see my screen now.
Yeah, go to that first plot, the smooth and okay, fine, yeah. So see, after the noise reduction also, you can see there are, yeah, even if this plot, you see even after you did the noise reduction, clearly there are many flares. And whereas your peak detection identifies only 3. What is your immediate judgment? What was the problem with your code? What was the limitations?
So one thing that like clearly mentioned as earlier, like uh, we are finding peaks in like basically all of the data, right? So if we change our code to find the peaks in local, like a local region, like we can maybe set a window length, and our algorithm like just goes over that window length and finds all the peaks, right? That would enable us to find more peaks.
But your documentation, you say that the peak dit function identifies local maximas, right?
Yeah, but
So you're doing some localization somewhere, I
yeah,
guess.
yeah. The like all these smaller peaks are basically removed because of the thresholds. Like we are defining a threshold, right? A certain threshold above which it is classified as a peak, or it is classified like, okay, it is a noise. So uh, yeah, that threshold can be worked around and changed.
And yeah, and I find that you are using a lot of hard coded limits, like for example 2 minute for smoothing and 10 minutes the window of the flare, 10 plus 10 maybe 20 minutes. You're assuming the flare time is 20 minutes. uh, why don't make that all variable rather than hard coding those numbers?
Yeah, that could be that could be a future, uh, like an enhancement to like basically give a slider to change all the window length that we are currently using. And
Because just you can see here itself there are flares of different time scales.
right.
Time scales is not 20 minutes
Yeah.
by default, so if you hardcore that things, obviously you will miss many of the flares.
So basically, what we did was we like just played around with different window lengths, right? And we chose the one that was best suited for like on the data set that we used, various different files that we used. So yeah, like that slider for variable window lengths that can be implemented very easily.
Yeah,
What
just
is the
one
wavelet
last.
you have used?
Yeah,
Sorry.
What is the wavelet you have used? The shape.
Um, like we are not using any wavelet. Here the wavelet means basically the segregated peak that exists. So like
But I heard the wavelet analysis is.
wavelet analysis means that we are finding all the like parameters using the segregated peaks and all. So like curve
but
fitting, for curve fitting, we like that's a potential enhancement. We like tried curve fitting, but because it was not up to the mark according to us, we did not include that in the final presentation. Yeah.
yeah, but when you say wavelet analysis, there should be a particular kernel wavelet. That's what
Oh,
Girish was asking.
okay. Like here, wavelet means for us, like from our side, wavelet means just the
No.
segregated peak.
Okay, and the k-means clustering you are using, which parameters are you using for clustering? Is that fitted parameters?
We are not using any like clustering or anything. We are just using statistical model.
Because you have a clustering.python py code which uses some k-means, machine learning clustering and all in your,
No, we don't have any of that.
but your document says that.
Um,
The readme.md, you are saying that there is a clustering.py which do all those k-means machine learning clustering model. I guess.
We haven't actually mentioned that in our documentation. I think there's an issue with
Oh,
that.
is it? Oh, sorry. Maybe it's a wrong.
Yeah,
Sorry,
that
sorry.
Just to reiterate, we only use statistical inferences for our model. Yeah. Maybe Nishant, you can show the repository itself, just the README.
No, it's okay. It's okay. It's okay.
It's okay.
No need. Yeah,
Okay.
yeah, I opened the right. Yeah.
All right. Okay.
Okay, if are there any questions? Can we move on to the next if not? Yeah, thank you so much.
Thank you.
Thank you.
Yeah. We'll have the next presentation.
Next, next we have a Scheme 9. So I'll
Yes, so shall we start?
Yes, please.
Sure. Okay. So, hello everyone. This is Team 9, and we are here to present our solution to the problem of automatic identification and categorization of X-ray bursts. Now, let's begin with the very basics, like what are solar flares, what is XSM, and how everything is connected in the problem statement. So, the XSM is a scientific instrument on the orbiter of Chandrayaan 2 mission, and it keeps us sending on the data of major space weather events like solar flare and coronal mass ejection. And the event of relevance here are solar flares, which are sudden explosions of energy caused by twisted magnetic field near sunspots. So they produce a burst of radiation across the electromagnetic spectrum, right from your radio waves to X-rays and gamma rays. Now, before using any software, you must know why do we need such a tool. So the first on the list of need has already been covered, that is extracting the essential parameters, which will help us in gaining a better insight to what all is happening out there. And the second is presenting data in a useful format. We have to make sense out of the data which SXM is providing us and make it more human readable so that anyone without any knowledge of computational aspect might be able to read and understand it. As you will see, our web app is quite simple to use and with a user-friendly UI best suited for beginners. Now let's talk about the vision and limitations. Of course, we have one for our web app too. So though our application currently works on the .lc files as the input, we seek to expand it to accept multiple input file formats like ASCII, TXT, and CDF. Also, for classifying the burst, our model needs the range for classification in count per second as the rate is given in the same units. And talking about the detection limit, all the bursts which lie in the range 0 to 350 haven't been considered due to noise in that area. The average background flux is around 350. And the peaks, which are at least 500 units apart on the unprocessed data, are detected. Now my other team member will take you forward with the presentation on code explanation and other explanations. Thank you. Vaibhav?
Yeah. Like first of all, let me give a brief introduction of what all the flow of data is happening. As usual, we'll get the data like from whatever it is, like text file or a CSV file. We will do a pre-processing. In this pre-processing, what I meant here is smoothing of curve and like filling up the missing data points. Like I was really happy to see one of the suggestions to be like taking the average value, which is exactly what we have done. After that, we have used Skipify to find the peaks. If you have the indices of which at which points the peaks are there, we can obviously find the time at which it is occurring and what is the rate happening there, right? That's what these two like outlets are happening. After that, what we did is finding the corners of these peaks using this. Like if we find the left corner and the point at which we are having the peak, we'll be able to find the rise time as the difference between these two. Similarly, decay time will be a right side point, right end of that peak. Total time would be taking the difference of left corner and right corner. Finally, what we did was finding the prominence or relative importance of the peaks here. Next slide, please. Here I'm just taking a small example of what we did to find the peaks. In this example, like we are taking that average background radiation would be 350. Then we will ignore all of the things that are below it. And this is saying that the distance between the peaks should be around 500. This is just for example here. Next slide, please. And while we are finding the corners, we are just going from point to point, right? For this, we are accepting a tolerance of 0.5. Next. Here you can see the prominence values. This black line represents how important it is. Next. Okay. How we did this? We have used the React.js for front-end components for having a natural look and elegance. Flash for backend, and Python for doing the model and all the related stuff. Some of the dependencies for this Python were AstroPy, SkippyPy, and NumPy. Next. Like this small step-by-step guide will be uploading the file, interpreting the graphs. We can see the data analysis. If we are interested, we can download the data also. Some of the screenshot we can see here. Say this is the graph, and you can see the orange dots here and there, right? Those are the peaks which it is finding. The peak value would be something like this. The corresponding y value would be the peak value detected, and the x coordinate would be at the which point of time it is happening. Next. As you can see, this is how the UI looks. In this, we can upload the desired file and upload it. We have a nav bar in which you can further see user manual and other things. This is the navigation. We can directly go to home or user manual, whatever desired may be. And we have split the output data into a small tabs so that people can see more easily. Next. This is how the output looks like. It's a table of all the things that are needed. Any question?
Yes, so that was our solution to the problem. Thanks.
Just before going ahead, your GitHub repository don't have any documents. Have you, or is it like I'm missing it? Your README file says that it is there attached PDF document, but I couldn't find a PDF document.
Yes, sir. In the app itself, there is an option user manual, so we can get the PDF right from there. We'll show it in the live demo part too.
But I have to run the app to get the document, right?
Yes, that we might have missed, but it's attached there in user manual.
So now what I'm asking is, if it is coming in the user manual, is there some directory where you would have kept this particular manual so that I can take it out? Some repository or something. In this, you don't know that, no? Okay, go ahead.
Okay, we shall move to the live demo part. You can share your screen, Web.
Excuse me. Okay. This is how it looks like. This is a home, and user manual can be seen here. Contents of this file, introduction, installation process, and everything can be seen in this user manual itself. Let me upload the file. Uh, I think there is some problem in the backend file. Let me quickly show you in my Colab how it is getting done. Yes, like as you can see, I will be taking the data from here. The in this Colab, I'm taking the from it from my drive. First, I am reducing the data to half of the size and then pre-processing it. Uh, this is where we find the peaks. Like the peak, we are taking anything below the average value of the peak will be ignored. That's what we are doing, and following a minimum distance between the peaks of 150. This is how it initially looks like. Like if you don't do any processing and directly find the peaks, this is how it looks. As we can see, like we can't even find where the graph is. Everything is peak here. That's why we did some pre-processing, and after pre-processing, these are the peaks that you can find. The same one with unprocessed data and following the measures of ignoring anything below average and stuff like that. These are the time of occurrences at which it's happening. The corresponding peak values. Uh, the max peak flux which we are having is this much. Average times. Rise time here it will be the start point to the peak. Uh, as you can see in here, we can see that. Uh, Similarly, we did the decay time. Here, X mark is the peak, and the green dots would be the right side corners. The total time series will be this. Prominences, these are the prominences. Uh, the graph is too crowded, so maybe you are not able to see the lines. Here it is there, right? The black lines, it represent the counter heights. Uh, yeah, that's all.
Sorry, I missed. So, how many flares did you find?
Sir?
Yeah, how many total flares did you find in the sample data, the sample test data?
Okay. Let me show.
I think do shape rather than shape to shape.
So all those orange points in the bottom ones are flares as per your thing, no?
Yes, sir.
The bottom
This
one,
is
the bottom one,
if
the one below.
yes, sir.
So you count each orange point as one flare, right? As per this,
Yes, sir.
there are a lot, maybe 50 or something, 25.
So flare, I mean, which part of flare are you detecting? Are you detecting peak of the flare?
Yes, sir. Peak of the flare in that neighborhood.
But in some of them, you can see even the valley they are finding as flare only.
Yeah.
You can see orange points there.
Can you zoom
Are
in
you
to the
saying something like this position, sir?
No, no, no. At the end of the day,
There are
This
so many flares you find.
yeah, which are not actually peak of the flare.
So you have a lot of false positives actually.
Yeah.
we can actually minimize it using the just like changing the distance values. Uh,
Yeah, it may not be a good idea to do live editing of the code because it will take a lot of time.
yes, sir. Actually, like for some reason, the website broke just now, so I had to change. Like this was the prototype that we were using, so that's why we are causing a lot of problems. Like from before, you can see, right? We have removed all of this extra points which were there. uh, in actual side, it adjusts accordingly to remove all these things. Uh,
So can you print the start, end, or peak time of the flare in some table format?
like here, I'm not able to print, but we can find the time of occurrences which it is happening. Like individually, we have it in
So can
this
you just
solar nodes.
okay? What is the length of this particular array? So these are all your peak times, right?
Yes, sir.
Can you just do length of that, length of or shape of?
Okay.
No, you don't do parentheses. You need, okay, anyway.
Yeah, 40 peaks are there. Uh, like this was the actually prototype model. I don't know why it's happening right now.
Does your software take other inputs like ASCII or CDF, or only LC you have used?
Yes, sir. It can even take the FITS file. Let me.
.lc is a FITS file. Did you try on CDF file, whichever it was shared?
Yes, sir. Like we are taking the data which we are given, right?
Whatever shared today, no, with you.
Yeah. Uh,
So
it is.
some 3 data files are shared right today. So one of them is .lc, another one is .nc, which is a net CDF file. Another one is an ASCII file. Did you try on the other files?
Well, I don't know. Like in this prototype model, it will work. Let me see. I think I only downloaded the LC file in my laptop.
Okay.
Like I'm extremely sorry, sir. Like I didn't expect to have so many problems on this day.
No, so can you run your own test data on your website? We just want to look at your website.
Yes, that's good. Yeah. Excuse me. Soham, are you there?
So meanwhile, you fix your front end, the broken front end. Shall I ask something on the back end? If somebody can answer.
Uh,
Yeah, can you make participant team 9 as the presenter? Organizers.
yes, sir. This is how it looks, sir. Uh, Let me show you for one already the data which we had. Uh, yeah, I'm like the same problem is happening for US files also. I think it's not able to show.
Okay, Vaibhav, I think front end, you got.
Like if
I think
it
live fixing is not a good idea. We don't have time for that. In your backend, I will just ask. I had some confusion because you are using fine peaks algorithm, getting lot of peaks, like hundreds of them. Then you're using some peak distribution unprocessed to reduce the number, right?
Yes, sir.
So you use something called 350 as a hard-coded value again there. Is it you're hard-coded that value because 350 seems to be for a particular particular day's data?
No, sir. It's we have kept average, right?
Average of the whole data?
Yes, sir. Like here you can see height is kept as this NP dot average data.
It's okay. I didn't go through the code. In your documents, it is written 350 is the cutoff.
Yeah, like the reason why we kept 350 instead of writing NP dot average of data would be like I thought like understanding that thing would be difficult without any context, like what is data or rate and like what is NP. Generally, NumPys are imported as a NP, right? Like I didn't want to complicate things. That's why I've kept the hard coded ones for the images.
Okay. And you didn't try any fitting and all, no? You just using this method, you are just finding the peaks.
Uh, like one of the like you remember one of the suggestions were taking the running average and smoothing it, right? That's exactly what we have done in this one.
What I'm asking is, did you fit any model or anything?
No, just
No, right?
directly smoothing only.
Okay. Okay, that's all from me.
Thank you, sir.
Okay, any further questions?
Can we move on to next
Yeah,
presentation?
yes, please.
Yeah, sure. Yeah, one second. Team 1 members are requested to raise their hands. Team 1. Team 1, is there only one presenter who's presenting the bill? Okay, we have another.
Hello?
Hello, yeah, hello, Team 1. Three of the presenters are currently enabled as speakers, so you may kindly proceed with your presentation, Team 1. Please confirm, Team 1.
लैपटॉप पे जाना चाहता है तो मेरे पे
Excuse me, ma'am.
Yes.
Ma'am, not getting. Oh, got it.
Oh,
Got
okay,
it.
okay, sorry.
Thanks. Ma'am, just a second.
Are there some issues? I'm not able to hear anybody.
I'm also not able to hear.
No, they
Team
told
1,
they'll
please
take some time.
confirm.
Sir, actually, yes, we can hear you, but we are not able to present that PPT. Just a second, we are trying it.
You want somebody else to share the PDF? If the PPT is same as PDF, you can share it.
Yes, sir, if it is possible, then you can share that PPT.
I can share it. Just 1 second.
Okay.
Oh, thank you, ma'am.
I'm also trying. It's taking some time. So.
Hello?
Yes, you're trying to share.
Yes, is the presentation visible?
Yes. Yeah. Team 1, you can go ahead.
Thank you, ma'am. Hello, good morning, everyone. We, the students of IIT Jammu, are prepared for the mid-prep statement, Isro web-based automatic identification of solar burst in X-ray light curves, Team ID 1. So, Solar X-ray Monitor, abbreviated as XSM, is a scientific instrument on board the orbiter of Chandrayaan-2 mission. XSM, along with another instrument class, comprise a scientific experiment known as remote X-ray fluorescence spectroscopy. Ma'am, can you please move to the next slide?
Actually, the PDF is presenting, so I uploaded the PDF on Airmeet. Uh, yeah, just give me a second.
Meanwhile, if team 1, anybody can hear me, can you tell whether you have any documentation kept somewhere in the repository, in any folders?
Sir, can you please pardon?
I was just asking, in your repository, is there any documentation, details of the code, etc.? Do you have any such document uploaded anywhere in the repository?
Sir, I would like to know you that the code upon which we worked on, like my team worked on from 7 to 8 days, we stored that whole code in one folder, and we were till like the very last moment were working on it. Eventually successful in finding all the parameters, but like at the time of submission, just 2 minutes before the deadline, in hustle that folder was deleted, which contains all the code, leaving us with not a single thing to submit. But now we worked on that code again, and we are ready with that. So it's a due request from our side. If you can give us the permission to present that code, then we can present you that once.
Yeah. Is the screen visible now? Like I'm scrolling through it. Just
Yes,
confirm.
Yes, ma'am.
Okay, so the team can start.
And I
the
think it is for the
presentation.
organizers to decide whether the submitted code or the new code you are presenting.
Yes, sir. So could you please give us the permission to present that?
Shankar, I don't know. That's what the organizers can say.
What is that?
What he's saying is what the code they submitted, they were late or just 2 minutes before, but they have worked on that further on that code, and what they're presenting is a updated code, not the submitted code.
No. This PDF is the one which they have submitted, right, Avanti?
Actually, in the demo, they can show that.
Yes, sir. This PDF we have submitted, but in the GitHub repo, there is nothing. There's no code. Like the code which we developed, that folder was deleted, so we don't have any code to submit at that time. But now we have again prepared a new.
Yeah, just to make sure, you don't get any advantage of extra time. You just present this PDF, and in the demo, you can demonstrate what we were able to do correctly.
Okay, sir. Okay. Thank you, sir. So could I go on with the presentation?
Yes, please go ahead.
Yes. So this was the problem statement. Ma'am, could you please scroll down?
Avanti, it looks like your screen is out.
Yes. Yeah, it's visible now.
Ma'am,
could you just scroll it down?
Yeah, we can see the screen. Please go ahead. Team 1, we are not able to hear you.
Yes. Okay. So first I would like you to know that what we have done was just a basic overview to it. Okay, so first we are converting LC file to .csv file. Then we'll open the new terminal, assuming the virtual environments which are not activated, assuming. So with the help of these commands, virtual environments will be activated. Then we downloaded Django, scikit-learn, scipy, numpy, pandas. Then further, with the help of the command python manager.py run server, we started the server. This command will probably run the most of all the commands. It means to run an emulated server on your local computer. So after running it, it will take us to the local host. Then link is now available in the terminal. Since all the main thing was available in the suradut directory, we changed the address to suradut. Our data specifically was from 7th November to 11th November 2021. So we can take the start and stop time of somewhere between these dates. And also the point to be noted is that the data we'll import will be to the nearest integer. Then after clicking on the submit button, all the parameters like rise time, decay time, peak flux, number of burst, duration of burst, average flux are displayed in our interface, finally with all the values found out. This is how our interface will work. Ma'am, could you just scroll it down? Data. In the data, we from .gti and .lc files, using the astropy library, we converted the given files to .csv file, which had rate, error, start time, stop time, fc. Then final is lc.csv, which is present in the backend directory. The code for the same can be found in the given directory, that backend suradut utils.py. And next. So this was our web app front end. The given interface has rise time, decay time, flux, duration of burst, peak flux, with an option to upload the files. Next. And yes, this is how our interface will look like. With all the data, rise time, decay, peak flux, duration of burst, peak flux, and number of burst also. So next. Our backend, given time, will have the radiation as a function of a time. So input time is the time from the starting of the Isro project. And this is what we were actually doing, which submit that at the very much deadline. So that was postponed, but now we have completed that. So thanks for all this presentation. Thanks to hear us. Thanks.
Okay, can you go ahead with the demo?
Yes, ma'am. Ma'am, could you please just make Kshitij Gera as a host?
Yes, he is now host. Just check once.
Ma'am, actually there is some problem in his browser, so can he just rejoin this meet?
Yeah, sure, but just make it quick.
Yeah, sure.
Meanwhile, can you talk about the algorithm a little bit? How are you detecting the flares?
Sir, he will brief you with this Kshitij Gera when he'll join. Ma'am, he joined the meet. Can you please make him a host?
Yeah, he is now host. Kshitij, go on.
Yeah. Thank you.
Is Shijit speaking or somebody else is speaking?
No, sir, he isn't speaking.
Yeah, I mean, all of them are
What
muted.
about Kshitij?
Ma'am, actually, I'm not able to share my screen, so I'm just trying.
Yeah, in the meantime, I think.
You can go.
Yeah, in the meantime, I think there were. I mean, you can discuss about the code. I think Sabilas was mentioning.
Sir, in the code, we basically just did some statistics, like we calculated decay time, uh, rise time from the classical algorithms. We used SciPy signal library to calculate where are peaks in the data, and all this data was shown in the interface.
How many flares you were able to detect in the given data set?
Sir, pardon, can you repeat what you just asked?
No, the given data set, how many flares you were able to detect?
Sir, for different times we had different peaks. Wait, I will just share the once I will be able to share the screen. I will show what we have
Sure,
done.
sure.
Ma'am, I guess I again have to join the meet. I have to just turn the browser off and again join the meet. So will you just give me a permission again?
Okay, just try once and be quick. Like for sharing, you can go on to that share window and then.
Yes, ma'am. But like my browser is not permitting, so it is that kind of problem. So I'm just trying
Like
to open with the
Chrome.
another. Yeah, I'm trying to open with another browser now. Yes, ma'am.
Hello?
I think team one, we have to move forward because there is a huge delay. So I'll just remove team one members from the stage, and next is team 10. So making them the presenters. So just one second. Yeah. Team 10, please confirm if you can present your PPTs. Team 10, please confirm if you can present.
Yes, ma'am.
Okay.
Excuse me, ma'am, can we start?
Yes. Yes.
Yes. You can start.
A very good afternoon to one and all present here. We, the members of Team 10, are here to present our web tool, JUX, the Solar Flare Analyzer. We got the opportunity to brainstorm upon this year's problem statement, web-based automatic identification of solar bursts in X-ray light curves. It was an honor to get the privilege to directly contribute to ISRO. We aim to bring a change in the workflow of researchers in India and abroad via our tool, which is based upon the XSM data from the Chandrayaan-2 mission. Our tool is scalable, which allows us to implement it in future missions and reach out to a wider audience. The development of a web tool was done in three major steps. Firstly, pre-processing of the XSM data was done. Secondly, data analysis methods were used to create a Python package. Finally, in the third step, the package was deployed as a web tool.
Okay, so the pre-processing procedure is necessary for any kind of signal analysis, and ours is no different. We got the training data from XSM about the Chandrayaan-2 orbiter, which we obtained from the Pradhan site. It then underwent noise reduction followed by interpolation, which was necessary to make a continuous curve out of the discontinuous segments of the raw data given to us. Smoothing was tried out through various ways, including windowing followed by moving averaging or moving median. And we also tried low-pass filtering technique, which actually did not need interpolation anymore, but had higher time complexity, so we ditched it. The smoothened but time-contracted signal was interpolated back to the original timescale via linear interpolation. Now this slide shows one of the raw light curve plotted with discontinuous segments, which are the good time intervals for which data points were given to us. This is the result of moving mean smoothing followed by linear interpolation, giving us a single continuous curve that retains the characteristic of the original light curve. Now coming to the crux of our problem statement, the feature extraction phase from light curves. For this, we first went through the literature, which led us to a deterministic algorithm that did a decent job in identification of temporal durations of flares. We followed this with flare profile fitting to estimate how each predicted flare deviated from the optimum shape, and the error obtained was used further in the anomaly detection. Literature review consisted of developing an understanding about flare detection algorithms and adopting as well as adapting one of them. The papers also helped us define features like start time, end time, peak count rate, background count rate, and the classification criteria. Now coming to the algorithm itself, we opted for a modular filtering approach that refined spikes that resembled a burst at each stage. The first filter picked out local maximas and minimas throughout the signal. Second filter matched those maxima minima into peak start timestamps. The third filter was slope thresholding for choosing only those start peak time with a fast rise.
while the fourth filter being height thresholding to ignore spikes induced by noise. The fifth filter removed the possibility of two flares being too close to each other, and the sixth filter considered only those flares with low mean square error during flare profile fitting. The algorithm can be better visualized by this slide, and you can see that each step refined the output of the previous step, giving better results.
Yeah. So in this slide, we've presented a clear overview of the results obtained. Our algorithm was able to capture certain essential parameters like start time, end time, the peak intensity, and the duration of each flare from the light curve file. Here we've presented a screenshot of the filtered light curve data, and we've also provided with some markers in order to locate the start times, end times, and peak in each flare. After an extensive literature review, we have arrived at an exponentially decaking function that with two tunable parameters A and B that could efficiently model the decay of a solar flare. And this flare profile was applied on the data and extrapolated, which gave us the end time of a flux and the error value that was calculated by taking the mean square value of the data points of the actual flare and the modeled flare. Here is the classification criteria that we've used among the flares. We have also calculated the logarithm of the count rates in order to compensate for the uncertainties in the values present in each class, and also in order to incorporate subclassification within each class of solar flares. Finally, for the outlier detection part, we have used isolation forest, which is an ensemble tree-based machine learning model. We have also used grid search cross-validation for searching optimal hyperparameters for the model in order to produce better and accurate predictions.
Moving on to the web tool that we have developed and deployed, we have used the best stack available for fast and reliable execution, using React.js as the front end, incorporating Chart.js to render out the light curve in a graphical format. The backend or the server-side application is written in Python using Flask as the API library. The tech stack we have used to build the application is an industry-leading one, primarily due to its performance, simplicity, deployability, and developer-friendly experience. Even though it can be extensively used as a web tool, we have also provided a Python package that can be used as a command line interface, which can further be built upon for maximum efficiency and huge dataset processing. Since we've built our application using React.js, just like Spotify or Discord, it is ready to be deployed as a standalone application using the Electron.js framework. Running on the backend, we have made industry-level APIs that are very easy to work with. No external APIs were used during the making of the web tool. Some of the salient features include one-click download of the data in the user's choice, be it CSV or PDF, including the obtained graph. The user also has the option to sort the columns for easier reading of the obtained result. Speaking of results, we've also added a feature to be able to view previously uploaded files and the data extracted from it. The user also has the freedom to upload the file in multiple accepted formats. As soon as you open the website, you are greeted with a banner letting you know its purpose as well as giving a brief introduction. On scrolling down, one can read about the solar flares, why it is necessary to study them, and hence the birth of this app. On clicking the question mark right here, you can access the user manual as well as the key features that we have implemented. As you can see, after passing in a random light curve in a .lc format file, we are able to see the plot of the solar activity in the form of a graph between the count rate and time. The buttons to download the extracted data in CSV or PDF format are also visible here. On scrolling down just a little, we can see the details of each individual flare presented before us in a tabular format. On clicking on any of the headers, the information can then be sorted according to the chosen column. A critical aspect of our tool is to be able to view the history of the uploaded files. Here, we have displayed the list of the previously uploaded files by the current user. On clicking the View Data button, the data is retrieved and the graph is plotted again.
So we've also presented a simple demo of the deployed web app, that is Zux. We've also deployed our overall application on Heroku, and the application also contains a loaded instruction manual. This slide also contains a demo of the command line interface of the overall package that was created by us. We've also shown the working of a script in a sample.lc file, which provided us with proper results.
So why us? What makes a web tool stand out among others? It is easy to use and has a user-friendly GUI. It is compatible and can be run on different OS with minimum system requirements. It executes quite fast. Thanks to the industry-level Flask REST framework, the tool is extendable as well, which allows it to be easily built upon for major dataset handling. This problem statement just doesn't end with the inter-IIT tech meet for us. We aim to improve our tool with time in a lot of ways. Right now, the tool only uses light curve files to detect and analyze solar flares. We can use other files from the XSM observations like the sun angle files, spectrum files, etc. as well, and thus try to dive into parameters like temperature and emission measure as well. We also aim to improve our outlier detection algorithm to further reduce the number of false detections. We can use an even more extensive dataset to identify trends better and predict the occurrence of solar flares. Some changes to the functioning of UI can also be made. Experience is less relevant than knowledge and the ability to learn and to innovate. This is what motivated us when we began working on the problem statement. It was an honor to get the opportunity to contribute a little part to ISRO. Thank you.
You can go ahead with the demo.
Yes, ma'am. Please allow me to share my screen.
Sure.
Is my screen visible?
Yes, it's visible.
Sure. So let me just reload it here. So as you can see, here's the pop-up that we have also displayed in our presentation. It is a very user-friendly graphics user interface. So here we have the option of uploading files, and as you can see, this is the light curve file provided in the zip file. On opening it, we have some animation to let you know that the file is being processed, and when the file is being sent to the backend, Flask is used to communicate between the APIs. And as you can see, we have generated the light curve, and on hovering, we can see the light curve count rate, that is the intensity of any point in the light curve. On scrolling down, we have also listed all the detected flares in their order of the start time. But as you can see, on clicking them, we can we can sort it according to the column, and the information can also be downloaded as a CSV, as you can see, or it can also be printed, as you can see here. More importantly, allow me to demonstrate using another LC file.
Now, before that, can you just show which are the flares identified on that graph? You have identified some 10 numbers, no?
Yes, sir.
So which are they?
So for picking out the flares itself, our command line tool is more apt for that. So can I share that instead of this?
No, in this, is it possible to show in this graph which are the, because I don't, you are showing 10, I don't know whether it is a right flare, is there a false positives, unless you do some line or some marking on the
Yes,
graph.
sir. In the command line tool, we have implemented the marking annotation, but we were not able to do that in the web tool in time.
So actually, I would like to, sorry to interrupt, but this thing also we can implement in our web tool as well. The chart.js library which we are using, it has a feature to basically change the color of that flare in that particular duration of the flare. So we'll try to implement it in the future as well. So that it can be shown in the graph as well.
Sir, so for now, can I show that on the command line tool?
I mean, whichever way you want to, or if you want to
Okay.
complete this thing first and then you want to show, that's also okay.
Yes, sir. So, allow me to demonstrate another feature. For example, just a second, sir. As you can see, I have uploaded a random LC file in here, which is being processed by sent to the backend, and then the information is being sent again to the front end, and the chart is being displayed as previously demonstrated. So one of the crucial features that we have implemented is the history option. So on clicking here, after the light curve processing, on clicking here, we can see the history of the file. For example, if we click here, the data
can be shown. Pardon me. So as you can see, I just refreshed. So there is currently no history, but on uploading, we can click here to view the data of that file. So Anshuman, please go ahead with the command line tool.
Yeah, can you stop sharing?
Sure.
My screen should be visible, right? Is the screen visible?
Yes.
Okay. Yeah, so inside the test data file, we have the test LC file. So I'll run it. So this was the file given to us right now. And if we run this, yeah, so these are the flares detected on the file. This is the start time denoted by the cross and peak times.
Okay.
Yeah, and for the end time duration, this is the end time capture.
So how are you finding the start time and end time? It was not very clear.
So actually, okay, actually we have implemented a modular approach to just keep on refining the flares which our algorithm detects. Like, can you present this presentation again, Rajesh?
Okay, now, so you're saying start time is the minima before the peak, right?
Yeah, not just the minimum. I'll show you again. Wait a minute. So the start time is not just the minimum, actually.
So here it found 7 flares or what? That, can you just show the terminal ones?
Yeah.
7
it has found
flares.
8 flares. So 8 flares actually.
0 to 7. Okay.
Yeah.
Okay.
So for picking out start time, we actually use slope thresholding. We picked out the local minima, which is just before the peak and has the highest slope to the peak. That we demarcated as the start time. Like, if there were other minimas in between due to noise, it would be removed as the start time, and instead the highest peak would be chosen as the start time. The highest rise, actually, not peak.
What are those crosses? That red crosses there?
The red crosses were the end times for that graph. I'll show you again. In this, the red crosses are the start time durations, and the blue dots are the peak time.
Okay.
And how is the background assessed here?
For the background, Athar can say something about it.
Yeah. So basically, as we are talking about the start time and end time as well. So for the end time also, we have defined 2 particular end times, which is one is the observed end time and one is the calculated one. So the observed time is via which we have defined via extensive literature review, in which we decided that not all the flares are able to come back to the base level, and that's why it was defined as the time which, for which the peak the intensity is somewhere between the peak value and the initial value. And the calculated time, which we are determining via the curve fitting, it is basically defined as a time which is actually obtained when the flare profile decay profile actually hits the base level. So this is about the time. And the next thing about the background counts. So for this thing as well, we went through several research papers, and via that we came to know, and we agreed on the fact that the background counts are not always the same because of these several activities taking place on the surface of the sun, and that's why it's not that fair to define one.
Can I break here? Just looking at your numbers.
Yeah.
For example, if you look at that first 2 or 3 numbers, You see that the background counts are higher than your start intensity.
Sir, it
Yes.
is. Sir, yeah, Anshuman.
So when the background is higher, how do you define start intensity which is lower than the background?
Sir, it is based on the averaging method that basically via the review of research papers, we agreed upon the fact that the background count should be taken as a linear plot between the start time and the start intensity and the peak intensity, and as it is a linear plot, we can take it to be an average value somewhere at the middle, and that is why the whole calculation process which is to be done at the end will kind of average out.
How do you define your start time? I mean, what is the definition for your start time?
Sir, as Anshuman right now had quoted that particular thing about the minimas, that once we get that minima, we have further refined it using our algorithm and the way it measures the sharp price. Anshuman, can you take it up?
Actually, I got disconnected. Can you explain what you were explaining?
Yeah, basically, sir is asking about the start time which we have defined.
No, the background counts and the start intensity. Actually, the start intensity is lesser than the background counts for a particular flare which is detected. Can you explain it with one flare?
See, I mean, typically, I mean, as a layman, if you look at it, a flare is defined as a brightening which is higher than the background. Now, in your detector flares, your background counts are always higher compared to your start intensity. So, depending, I mean, that's why I asked how the definition of start intensity is done.
Yeah, so actually, Athar went through a lot of papers and he found out that because background counts can't be constant for every flare throughout the day, the paper recommended to take the average of the start and the end time as the background count value. So we took the average of the start intensity and the end intensity of a flare as the background value.
Sir, also we also went through some research papers which were like a bit old, and they defined a background count as a value which is somewhere below the base flux value in the whole plot. So it was like ventured, and we also agreed upon that fact that it's not possible that the background count remains constant throughout the whole solar flare emission, and this is why we changed our definition of background counts than what it was a constant value which is the line parallel to the time axis.
Okay, so what you mean by background intensity is the background intensity during the peak of the flare, not
Yes, sir.
during the
Yes, sir.
start.
Yes, sir. Yes, sir. We are not defining background counts for the whole emission as a whole. We are defining it for that each isolated flare.
Okay, okay.
Can you just explain what is happening in case of double flare features? Can you just go back to your demo and?
Okay. Should I share the screen?
Yeah.
Oh, 1 second. No, the screen is visible, right? Yeah, it is. So let's run this for some other file. Saw it for this file. So this is another LC file which was in the package itself. Yeah, so the question, can you repeat?
Yeah, no. In the previous test data, there were some double flare features. But
Okay.
yeah. Can you just run the same for them?
Yeah.
Yeah.
Double
So
flares
there are,
like
yeah,
this.
one. Yeah.
Yeah, so actually we took account of such. Wait a second. Let me zoom in. Yeah. So we considered only maxima of maximas. Like in a range, we went. We only considered in a particular threshold, like the LC files provided to us had error rates given in them. on average the error in observation was 20. So we took a threshold of 30. Like if flares are near to each other, more than but less than 30, and less than 30 value, then one of the lower one would be ignored. So that's why this is not detected.
Okay, but the errors in the count rate are also provided for each time. So have
Yeah.
you hard coded the 30 value somewhere?
Actually, we in each of the LC file it was given. We considered many LC files, and the average was around 30 or least was around 20. So that's why we kind of hard coded 30 value.
Okay.
And also to remove this as a detection, we considered only the lower start time. And if another start time was coming near to the previous week, which is higher than the next week, we remove this as the uh, flare. Like we did not consider the next week as a flare. That's why this and this are not considered. Even though the gap between these are more than 30, this is still not considered as a flare.
And one more thing I would like to add here is that, like in a lot of light curve files, the count rates were not that significantly high. So due to that as well, so some files which are having low count rates are having a lot of flares being detected. So it was also a part of the question that we should consider them as double flares or even as a flare or not, as they would lie in a very low range of count rates.
One more question. In your documentation, you have talked about anomaly detection systems and everything. Can you elaborate on that?
Rajesh, can you explain?
Yeah, so am I audible?
Yes.
Yes.
So after performing a multi-filter based approach, we have obtained some important parameters and we have constructed a data frame consisting of those features. And these parameters are further fed to the isolation forest model. And the isolation forest model is based on the concept that since the outliers are a bit differently distributed than the original predictions, so in the tree based, while constructing the decision tree, the outliers are separated much earlier than the original observations. So yeah, and decision tree models are much more robust to the outlier to data sets. So we have used this model for detection of outliers. And we've also passed an initial contamination level of 2.5% to the model.
No. So what are the features you are considering for the outlier?
So for outlier, we are actually considering the time ratio, like the end time minus the start time divided by peak time minus start time. This is one of the features. The second feature is peak intensity minus start intensity divided by peak time minus start time. Essentially, the bandwidth of the rise of the flare. And another feature was the decay bandwidth. And the last feature used was the intensity ratio, like peak time minus start time divided by start time. So these are the features used for anomaly detection, which were inputted in the model.
So is that deployed in this model? I mean, do you online do this anomaly detection and reject some of the flares?
Actually, it is deployed in the package, and we did plan to do that on the web tool itself, but we were not able to do it on time. But
Sure.
the package does have it. Like I can show you right.
No, that's fine.
Should I present? Okay.
No, that's fine. That's fine.
Did you also try other formats like CDF or ASCII files format?
Yeah. Actually, the problem with the us we we encountered a problem. Someone's speaking. Okay. So we actually encountered a problem with the ASCII file. The time given to us in normal LC files were in Unix time, but the test file given to us right now is in UTC. So the input is not compatible. with our package.
Yeah, maybe we can show the output which was with the file which was shared on the Slack previously. So if you can show with ASCII file of that.
What about the CDF? That CDF?
Yes, sir. So in the CDF format, we observed that the on a single time rate, for example, at 0 seconds, there were multiple points of intensity. Like for example, on 0 seconds, there were uh, 4 to 5 points, probably more, each having different intensity. So it would be impossible to filter them out, like which point to be chosen in order to construct the graph.
Adit, can you just share your screen and show the TXT files?
Yeah, let me share my screen.
What is the time resolution considered in the code? I mean, is it seconds or minutes or milliseconds?
The time given to us was in seconds, and we bend it to 10 seconds. Like our time resolution is actually 10 seconds, and we interpolated it back to 1 second only. So essentially, the time resolution is 1 second.
Okay, and your code takes the time resolution of the input data, or you guys have your own time resolution?
So can you repeat your question?
No, I mean I'm coming to this because the time resolution of XSM data and the time resolution of the net CDF data, what is given, very different. So if your code is doing some, I mean, some kind of averaging or some kind of interpolation, then the error what Adit Jain is telling may happen in the CDF file.
Oh, okay. So the time resolution in the CDF file was different than the LC file. That's what you are saying.
Yeah, so when you're reading the CDF file, you would be reading with certain resolution. That may change the number of time points what you get.
Okay.
Anyway, I think that is, I mean, that can be sorted out. I mean, it's not a major issue as such. But you are able to read CDF file, right?
Yes,
Yes, sir.
we are able to read CDF files.
And as you can see on your screen, sir, here is the result of the sample txt file provided over the Slack. So here are the 3 peaks detected, as you can see, sir.
Okay, cool. Thank you.
This uncertainty is whatever you quote in the parameters. Is it, how do you obtain? Is it from the fit parameters?
Yeah, we actually try to fit the analytical function, which we explain in the presentation itself. And the deviation from the analytical function is what the uncertainty column was for each flare.
Okay. So the goodness of the fit, did you have a look at it? Like when you fit different flares, how does it compare with each other?
So the error value itself shows the goodness of the fit. So our sixth filter was actually one of the filter which used that error value, which filtered out the flares which had high error. So
Can you please show that the list of the flares detected in the parameter, that table?
which table?
The parameters of of all the flares detected.
Okay,
Are you-
I'll share this.
Are you fitting the whole curve? I thought you were fitting only the decay part. When you
No,
Yeah,
actually,
we are
we are doing that only.
only you're doing an exponential decay. That's all, right? You're using.
Yes, sir. Yes, sir.
So you're not fitting the full flare. I think only decay part you're fitting, right?
So we tried to fit the actual flare profile, but the output was not that good. Like we were not able to fit it well enough.
Yeah.
But the analytical function we got from another paper fitted well, so we used that.
So that other whatever analytical function you use is only an exponential decay function, right?
Yeah. Regarding the rise time, we
Yeah.
only considered those with fast rise. So that's why it always is kind of a flare only from the start point of view.
Sir, one more thing I would like to add is the flare profile function is usually a 6-parameter function which consists of a linear background value at the end as well. So basically, we have accommodated the exponential decay and the background count, which is a linear plot. Both of these things we have accommodated in our algorithm, and only the fast rise part in the flare has not been interpolated or fitted during the curve fitting process.
Not fitted, right? Rise time.
Yes, sir. We have taken it as a fast rise, and then subsequently we have fitted the decay time, and the background counts the background count, which is a linear plot, which is in the flare profile function, the 6-parameter function. That part also we have incorporated in our tool.
So the error here is in which parameter?
It's just the difference, like it's just the MSE of the analytical function and the decay part of the flare detector. So it doesn't have a unit. Like
No, I didn't understand.
I think there are two errors here. You earlier talked about an error where you took 30 as the value, and Abhilash asked why you took 30. I think that error is different from this.
Yes, sir. That was not an error actually. That was that was error. So it was given the LC files. There was a separate error column.
Yeah. So
that
you
is
use
different.
that. Okay.
Yeah.
How did you get the class of the flare? Or, I mean, what logic you have used to define the class like B1.8, B3.0?
Athar?
Yeah, I will take it up. So basically, as it has been already categorized in several research papers based on the flux values in watt per meter square. So one limitation which we faced was that the data given to us was in count rate, which is counts per second. So the first task was to convert the count rate into flux values in the units of watt per meter square. So as the each and every observer has different parameters, so based on that we tried to approximate the conversion of count rate into the flux value of watt per meter square for the XSM only, using the parameters like the aperture area and several other things. We would have been able to get a more accurate value for flux if you would have used other files like the sun angles files and the spectrum files as well. So based on that, we got a rough idea for the flux values in watt per meter square, and then basically as several classifications in the form of A, B, C, M, and X are in terms of flux in watt per meter square. We use that only for us, and then for subclasses we basically took as it is in the form of basically in the form of exponential. Like it has an exponential ratio, so that's why we took the logarithm of the flux value upon the number, which was 25, which was the. Can you show the slide for that?
Yeah.
So what is your error in converting from counts to flux?
Sir,
You have some number?
Sir, we did not actually get a complete number for the percentage error in that, but we have mentioned it in our documentation that what process we have adopted in converting the count rate into the flux value in watt per meter square, like using the parameters of aperture area and all of the XSM monitor.
Now, why I ask this is you have defined it up to first decimal, 5.1, 1.8 and all. So your error should be less than that, right?
Yes, sir. Yes, sir. The subclasses further reduce the error because we can say if the value, if the subclass is something like point 6, then we can say that the flare might have come into the B class due to some error in the conversion factor. So we can estimate that if the value is somewhat close to 5, say somewhat close to 5, then we can say that it lies in that particular classification only. But if it is something like 8.9 or 0.6, then we can say that the error can be there in classifying that particular flare. So it might belong to the next class or the previous class.
Yeah, maybe I just let you go back and look at it. For a 0.1 difference in the flare for a B class and C class flare, what should be your flux accuracies? You back calculate and see whether that accuracy is achieved with the data provided in XSM. Okay, just back calculate and see.
Yes, sir. Yes, sir. We'll go on to it.
Okay, then. So, are there any questions? Should we stop? Thank you. Thank
Okay,
you for the
thank you.
Thank you.
Yeah.
So maybe
All the panelists will be continuing for from 1:30 p.m. So yeah, like all the judges can go on for lunch break.
okay. So
We'll be continuing with team 11 and at 1:30 p.m.
okay. Okay. Thank you. Yeah.
ಅಂತ ಹೇಳಿದ್ರು.
ನಮ್ಗೆ ಏನು ಕ್ವಶನ್ ಪೇಪರ್ ಆಗಿರುತ್ತೋ
Avanti, I think you can start. Avanti is not there. Just a minute.
Hello, am I audible?
Yeah, now you're audible. So you can ask the next team to present.
Hello.
Yeah, you can ask the next team to present. You can hear me?
Yes, sir. Yes, sir, we are on the stage. Shireen, will you just present your screen? Yes, your screen is visible. We'll just do a quick mic check. Shireen?
Hello.
Yes, you're audible. Siddharth?
Hi.
Yes, you're audible. Snigdha?
Hello.
Yes, you're audible. Okay, we'll start. So, greetings everyone. We present to you our identification and visualization tool for solar burst in Chandrayaan 2 X-ray light curve data. With this tool, we can detect, visualize, and extract important features from light curve. This tool helps in extraction of relevant files from different input file formats, identification of peak burst, flux, and important feature extraction, upon which bursts are classified into different categories based on different parameters and are represented in a concise tabular format. We have developed a user-friendly and seamless GUI for visualization majorly using JavaScript libraries and frameworks, namely React.js and Recharts. These are used for user interface, and Electron library to support our standalone application, and Python-based Flask framework for backend purposes. Shrin, will you switch to the website? As you can see here, we can upload zip files as well as single LC file directly as input in ASCII, FITS, CSV, XLS, and CDF format. On uploading zip files, we use XSM GenSpec software to generate flux files from the other given files other than the LC file in the zip format, and it usually takes around 30-40 seconds for processing. And when single LC files is uploaded, only rate versus time graph is generated, which is generated instantly. Shane, move to the Shane, your screen is not visible. Just a second, sir. I think there is some network issues. Siddharth, will you present the screen? I think there is some network issues. Yes, I hope it is visible. Okay. Okay, so we'll switch to the output of the website. Shireen?
Yeah, just
Okay, so here in the visualization curve, we have plotted rate versus time. Shireen, please mute the mic. Okay, so here in the visualization curve, we have plotted race versus time as well as flux versus time graph with detected solar bursts labeled with their respective start and end time. As depicted in the legend, you can see peak bursts are shown with cross and start and end shown with blue and red marks respectively. Please move on to the table. Relevant features. Shireen, please move on to the table. Yes. So as you can see, relevant features extracted from the solar burst had been shown in tabular representation. Here we have calculated start time, end time, duration, rise time, decay time, background count, peak flux, and classification has been done on basis of 4 parameters, namely area, duration. These are done from rate versus time curve, and peak flux and ratio of flux peak by background count. And this has been done classification from flux versus time curve. Snigdha, on to you. Please switch back to the presentation.
yeah. So the next thing that we will look at is classification of the solar flares obtained. So we have classified a burst into various classes based on different parameters. The first classification is based on the peak flux. So flux of the solar flare basically gives us the amount of energy which is received per unit area, and solar flares are classified here on the basis of soft X-ray classification as A, B, C, M, and X according to the peak flux as shown in the table below. The next classification that we have done is based on the duration of the burst. So duration of the burst is basically the total time for which the burst lasts. It is calculated by first finding the peak time, the start and the end times, and then finding the corresponding rise and decay times. The summation of the rise time and the end time gives us the duration of the burst. This parameter has a very great impact on the burst strength because it affects the amount of energy which is released during the burst. So on the basis of duration of the burst, the solar flares are classified as long duration and the short duration burst, as can be seen in the table. The third classification is based on the area under the curve. Area under the curve is important as it gives information of the number of photons which are released during the burst. So on the basis of the area under the curve by observation, we have classified as bright, normal, and faint, which can again be seen in the table. And the last classification that we have done is based on the peak flux by background count. So we calculated the peak flux from the flux curve and the background count, and we found that the background count is affected by the varying time scales and therefore finding the ratio gives us a better indication of how the flux changes due to the presence of the flares. So based on the peak flux by background count, we have classified as type 1, type 2 and type 3.
It's like the okay, Siddharth, you can continue. I think presentation is not visible. Wait, I'll just present.
Yeah. All right. We're really sorry about the delay, but there seems to be some sort of an internet issue.
I hope it is visible. Siddharth, you can continue.
Yeah, it's visible. All right. So moving on to the next stage of our presentation, we've implemented a statistical model over a machine learning model in our approach, and there was one major reason for this. A machine learning model would require annotated data, or basically we would require the peak values, the start time and the end time of the light curve data beforehand, which we did not have. Hence, we use a statistical model which uses a technique that is comparable to that of a human. We first look for potential peaks by identifying prominent local peaks in the curve, and then from each peak, we calculate the peak start time and end time. The other features are subsequently used to. Varenya, can you please mute yourself? The other features we utilize to categorize the peaks, such as area, rise time, duration, etc., are subsequently computed. Now, let's move on to a brief overview of our statistical model, and we'll understand what we're really doing. So first, the input file. Okay, so there's two formats for the input file. We can either give a zip file containing the data given us on the Pradhan website, or we can provide the individual light curve files in the different file formats already mentioned. So we work on two major files in our model: light curve files and the flux files. The light curve files are already present in the zip file. We just extract the data from them. We generate the flux file using the utilities provided by the Pradhan website. We first generate the spectrum file using the XSM GenSpec utility, and then further generate the flux file using the XSM compute flux utility in the energy range of 1 to 8 angstroms. The data tends to be very noisy, so we move on to the next state, which is noise reduction. We use a very simple basic moving average with a window width of 60, which we have fixed based on our observations, such that it reduces the noise but still maintains the general trend of the curve. Then we move on to the major part, which is detecting the peaks. So we use the SciPy signal library to detect the peaks. Now that we have detected the peaks, we have to filter the peaks such that we need only the prominent, we identify only the major bursts and not every single small peak in the curve, right? So we filter out based on two parameters. Can we move to the next slide? Yeah. So basically, in the light curves, we set a minimum threshold of 600 counts per second. But if there is no peak greater than that threshold, we reduce the threshold to about 70 counts per second. So then we move on to detecting the start points and the end points. We filter the peaks in the flux curve by and start points and end points, and then we move on to calculating the features we require. Basically, the area, rise time, decay time. Moving on to the flux curves. Since our classification in the flux peaks starts from 10 to the power minus 7 watts per meter square, we basically filter out every peak with a lower flux, and then we calculate the background count, which is basically the average flux except where there is a burst. And then now that we've got all the data, we move on to the classification. As mentioned already, we classifying based on peak flux duration, ratio of flux peak by background count and area. Can we move to the next slide? Yeah. Moving on to our limitations and our scope for improvement. First major problem was XSM compatibility. Our standalone web application will only be supported on Linux-based systems because we compute the flux using the utilities provided to us. However, it would still be able to compute the light curve files. Only the flux file would not be generated. Twin peaks, sometimes happens that two bursts tend to merge into one unified burst, and although our model tends to work on the general average data, it might not always work on twin peaks data. And the noise reduction, we have set a standard window width of 60, which might not always be accurate. So we can actually change the window width depending on the given example. Thank you.
Okay, so now we are open to questions and discussion.
Yeah.
The team can go on with live demonstration of the code.
Okay.
Shankar sir, is that okay
Yes.
if
Please.
they carry out the?
All right.
Yes.
I will be sharing my screen. Varanya, can you please move your mic? Yes. I hope my screen is visible. Give me a second here. All right. Backend is running.
Yes, it is visible.
All right. All right. So this is basically our home page, and then moving on to the inputs. So we can take multiple file formats, and I will be showing you what happens. So first, let's take a zip format. We've just picked one of the data from the Pradhan website. So basically, this contains all the different files, such as the sun angle file, etc., etc. If I'm going to upload, I'll show you what's happening on the back end simultaneously. On being uploaded, we just unzip, as you can see, and then we run the Flux file generation here. So the Flux file generation uses the XSM software, and it's being run here, as you can see. This is what is limiting our speed. If we were to submit individual LC files, the results would be almost instantaneous. So it is now generating the spectrum file, and then that spectrum file will be further used to generate the Flux file. Meanwhile, we support different kinds of formats. Basically, FITS, XLS, ASCII is given here, and then we also support CDF and CSV formats while that runs. Yeah, we'll just give it a few seconds to run. All right, so you can see that the spectrum file has been computed. Now we should be looking at the data in a few seconds. Yeah. All right, so here we have it. Yeah, so you can see that the data has been plotted as well. So we have identified multiple peaks here, and we've also generated the Flux file, which you give it a second. Yeah, this is basically the Flux file that has been generated based on the utilities given to us. And basically, this is the tabular data that we have generated. You can see the different data that we have been able to extract from each individual peak. And moving on, there is a lot of data that we have extracted, and then this is our classification. As you can see, there's multiple types of classifications that we have used, and then this is the data we've extracted for the Flux versus time graph. All right, moving on, I can also
how many totally how many bursts could you actually
yeah, sir, 1 second. Yeah,
no, this is a different data, not the data we sent.
Yeah, yes, sir.
Yes, sir.
I will be using your data next. Give me a second. I will be showing this data for now. All right. Yeah. Your data will be uploaded next, and that should run almost instantaneously because we do not have the rest of the files that were calibrated, right? So you can see that all these bursts have been detected here. Almost every single burst, even the smaller bursts, have been detected, such as this one, and the predictions tend to be accurate in general. Here, even multiple peaks were very close to each other, and they have all been individually detected, as you can see. All right, I will now run one of the input files that you have given to us as test data. All right. So you see that it almost instantaneously ran, and yeah. So these are the bursts that we have predicted in this. Now, if in case you feel that the number of bursts that are being detected is very low according to your estimate, we actually we are able to detect all the peaks. It's just that we have set a minimum threshold, right? So that is something that we can change easily and should not be a major concern. So if you want us to detect these minor peaks here as well, we can just change the threshold according to the requirement, and all those peaks would be detected.
Can you do that?
I would have to change the source code
Okay.
and restart the server. Yeah. But if you want to look at the data that's been extracted, it's right here.
So that we can change the threshold. If it won't take long, I guess.
Yeah, all right. Give me a few seconds. I'll just stop my presentation for a second here. I'll be back.
Ma'am, meanwhile, we can continue with the questions.
Yes.
I have one question. Can you elaborate upon your classification schemes? What are the type 1 and ABCD types?
No, yes, sir. Snigdha, you can continue.
Yes, sir. So we have them.
Snigdha, you can share screen and demonstrate with it. Or Varini, you can share screen and Snigdha can demonstrate. Can speak.
Okay, just a second.
Yeah, it's visible. Thank you, Varenium. So now the classification we have done into 4 types. We have done on the basis of 4 types of classification. The first classification we have done is on the basis of peak flux. So peak flux, the classification that we have generated is from the flux versus time graph. So from the XSM GenSpec utility, we first plotted this flux curve, and then this is on the basis of a soft X-ray classification. So we have classified as A, B, C, M, and X on the basis of the flux curve. So if the flux on the basis of the peak flux. So if the peak flux is less than 10 to the power minus 7, then the classification is A, and so on. The next classification that we have done is on the basis of duration of burst. So duration of burst we calculated from the rate versus time.
Sorry, can you go back to the previous slide? Is the marking on the right hand side is fine, because I see B is having more flux than the C. And according to your table, C should have more flux than B.
Sir, I guess that must be an editing issue.
Okay.
Okay. But you can see in the tabular format, the C is the higher peak will be treated as P.
Okay, so this is actually edited by you. This is not the plot coming from your system.
No, sir. We have added B and C. The plot is generated. The B and C we have added for easy visualization.
Okay.
If you would like to view the new plot generated, I could show it anytime.
Yes, Siddharth. Sir, we can continue, or you want to go with the classification?
Let's finish this particular question.
Okay. Snigdha, please continue.
Yeah, so the second classification that we have done is on the basis of duration of burst. So we plotted the rate versus time graphs of multiple the data sets that we obtained from that Pradhan website, and from we calculated the duration of burst for all of them, and then we found that based on the duration, we can classify them as short or impulsive bursts with duration of less than 1 hour, and long and gradual bursts which have a duration of several hours. So based on that, we classified them on duration of bursts. Moving on the basis of area under the light curve, we calculated the rate versus time curve, and then we calculated the area under the curve, because it gives important information about the number of photons which are released during the burst. And we observed from all the data sets that we loaded and found the area under the curve by observation. We classified them as bright, normal, and faint. So if the area is greater than 10 to the power 6, then the classification is bright, and so on. the last classification that we did was on the basis of peak flux by background count. So we calculated the peak flux and we also calculated the background count, and we observed that if we find the ratio between the peak flux and the background count, then it will give us a better indication of how much the change would have occurred in the flux if a solar flare has been observed. So based on that, we observed for multiple data sets, and then we classified them as type 1, type 2, and type 3 on the basis of this ratio.
Okay, same editing error also is here. This is the ratio of, in the plot, I think it's wrongly mentioned. Just one information, not a question. The previous one where you talk about the area, people also use a name called fluence. Fluence is nothing but the time versus time multiplied by the intensity. That's called the fluence. People classify according to the fluence.
Okay, sir.
Yeah, Abhilash, your question is answered.
Yes, sir. Yes.
Okay, then probably we can go back to that running, no?
Okay, Siddharth, you can share screen.
Yeah, all right. Give me a second there. I hope my screen should be visible by now. Is it visible now?
Yes, it is visible.
Yeah, can you please mute yourselves? Thank you. Yeah. All right. So you can see now that just by changing the threshold, many more peaks are being detected here. If you'd like to see the tabular data as well, we have it here. Basically, we've calculated all the required parameters that we are using in our classification. Basically, multiple types, and then the classification based on area duration here. Since we only have the LC file, the flux file data does not matter in this case. Any questions? Any clarifications?
Can you go to the curve once again? No,
Yeah,
that plot.
sure, sir. Yes, sir.
So
I
how
hope
many
it's
are there
visible
total?
now. 1, 2, 3, 4, 5, 6, 7. 7 of them have been detected here, sir.
Okay.
Can you expand around the double peak? Somewhere around just after 8
Sure.
Yeah. Can you just expand that reason?
Sir, when actually the library that we use does not allow expansion, but if you want, I can tell you it might be possible that due to the streaming, your quality might not be as great as I can see in my screen right now. But the purple and the red seems to overlap there, because as soon as one ends, the other seems to begin.
Just show the tabular data, Siddharth.
Yeah. All right. So that
Or
would
those
be
two.
Yeah.
For the third and fourth peak.
Yeah. Third, 1, 2, 3. Yes, sir. Third and fourth peak. So you can.
The time is in seconds or milliseconds?
So the time is in form of the data that we've been given, like basically exactly the same data that we have been
Seconds. Seconds, I think, right, Abhilash?
I just wanted to see
Yeah,
that.
seconds after some 2017 epoch or something.
Yeah, the third and fourth peak, what is the time difference I wanted to see?
Oh, okay, sir. 1 second. That would be the end coordinate of the third, that is 20, and that would be the start coordinate of that would be 320, and that would be 30. It's almost the exactly same, sir. It's almost exactly same. Yeah, it's exactly the same point.
Okay.
So that is why you can see an overlap over here.
Yeah, that's because you are taking the minima, right? That's what you're doing.
Yeah, sir. Exactly right.
So your threshold you changed is that value 600, right? Is that the one you
Sir,
changed?
yeah. First, see, sir, what happens is generally the data tends to have values that are much over 600. So we initially thought that since it was given to us that not a lot of bursts might be detected in one day, so we set the threshold to 600 in general, so that not a lot of minor bursts when there are a lot of major bursts must be detected. But if you guys want us to detect, I have changed that to a lower and have increased the sensitivity of the peak finding algorithm as well.
So what
so
is the
that
number
even a
now?
small. Now I've kept it at about 20.
Okay.
Any clarification that you would like? I could explain anything more. Any confusions that you have?
So what you're doing is basically you're not doing any fitting or anything here. No, you're basically running a
No.
window
Yeah.
algorithm, taking 4 points, comparing the 4 points one after the other. If it is increasing, to find the start and end time, basically.
Right.
And in that
Yes,
also
sir.
you have used some standard numbers like 0.00014 for finding the end time and
Uh,
1
no,
point
sir.
or
We have
5 for.
optimized. If you don't mind, I'm really sorry to interrupt, sir. Yes, sir. We read that paper and we saw the method that the scientists were using. We went ahead and optimized that value that it gave better results than were being obtained with the numbers they gave. Also, we did not actually fit a model because there was no requirement of fitting a model, as there is no predictions that we can use to actually train the model, because a machine learning model requires the true values to be fed into it, and we didn't have them. So we used just plain maths, and our results are actually good enough that I don't think the method should matter here, because the results are what matter at the end of the day, right?
Now, if you see the near your just a blue, just no, you're just near your mouse icon. There was a blue, no?
This,
Yeah.
sir?
So you consider that as the start time,
Yeah.
right? But clearly that is not the start time. Start time after
Right, sir. I
comes little
agree. I agree.
later. That is why
Yeah.
that the difference between when you look at the minimas, no, this problem can come because local
All right.
minima can be little away from that.
Correct.
Yeah,
And
Correct.
even
the first,
even there is some
even the first
in
one you
between.
see, for example, the first flare you detected, you see the
This, right?
blue, yeah, the
Yeah, yeah,
start
yeah.
time is really off written, right?
Yes, sir. I understand this problem, and
Yeah,
it's
it's okay, no
extremely
problem.
hard for. Yeah.
Yeah, understood. No, I'm just saying that's why people went ahead of this and started looking for functions and all. Even I'm not saying
Mhm.
functions will exactly get you or anything. That's why this whole challenge is right. This is a challenging problem
Yeah.
because of that.
Agreed, sir.
Yeah. And so what I'm asking is that 0.0001 or something
Yeah.
as the delta flux you are using for, or delta rate you are using
Ratio.
for finding the
Yeah.
minimum.
Right.
Similarly, some 1.005 which you are using to find the starting point as a
Yeah.
rate of the delta rate.
Yeah.
But these numbers are why you are hard coding those numbers, because it's something.
Sure.
If
I
you
can
keep that as a
totally say
buttons
that.
here and people can
Yeah.
tune that little bit,
All right.
it might be
Yeah.
different from case to case.
Right, sir. That we can see that as something that we can improve upon. This, there can be a few features that can be added, such as we can give more computability to the user. He can choose the filters he would like, such as the threshold he wants to keep, the let's say even the ratio that where he wants to find the start time. I agree, sir. Those are some things that we can implement.
And between these two trials, before changing the threshold versus now, how many were detected earlier? And
All
are
right, ma'am.
those
All these peaks on the right side were being detected. These smaller peaks on the left were not being detected.
okay? So if you further go down in threshold, would it? What would be the thing? Will the other two flares, smaller ones, be detected, or
These.
in addition will you have false
Uh,
detected?
the I could see them being detected, but we would have more false negatives as well, because they can be peaks like these that are being detected. But that is up to the user, depending on what the user wants from the algorithm. We could try that out as well, yeah.
Can you attempt it now? How long would it take?
Give me
In
1
case you
minute, ma'am. I'll
reduce
just.
yeah, if you go
Yeah.
further down in threshold, would it
Uh,
just out
uh,
of just to see that how many false
do you want me
detections?
to edit the code right now?
Yeah, like how you did it right away.
Yeah. Give me a second, ma'am. I'll just stop sharing my screen.
Oh, don't stop, Siddharth. That's fine.
All right. All right. I'm sharing my screen.
So, and for the background, how is that estimated?
Ma'am,
Somebody
we
else can
take.
answer.
All
While
right. Yeah.
you do this, somebody else can answer that.
Snigdha, you can continue.
Sorry, can you repeat the question again?
How is the background estimated in this?
Ma'am, I can take that question. I can take
the
that question.
background count.
Yeah. So
Background.
background count. So what we've assumed is the background count is basically the average flux except where there is a burst that has been detected. So we take the average and we take all the data and we remove the places where there's a burst that has been detected, and we take the average of the rest.
So that is again done in a windowed fashion within a certain time range. Is that so? Or
I didn't get your question, ma'am.
that background thing is done for a certain time window within the plus minus duration of the flare?
Yeah. No. I 1 second, ma'am. So we take the entire data of that has been given to us for that day, and we run the background count on that. So you can see all the peaks have been detected now, every single peak, and there has been no false detection as well.
So totally, how many are there?
1, 2, 3, 4, 5.
Just count from
6,
table,
7,
Siddharth.
8. Oh, right. I'm so sorry. 9, 10 peaks, ma'am. Ma'am, moving on, is there any clarification you require on the background counts? So basically, let's say we have the entire day's data, right? So what I'm going to do is I identify that there's a peak from here to here, right? So I'll remove that part from the data and I'll take the average of the rest.
Okay.
Basically, wherever there's a burst, I'm removing that data, and so that it doesn't skew it. Because if, let's say, there's a very big burst, that will tend to skew the background counts, because a burst is a singular occurrence, but a background count is generally what is the trend that is being observed, right?
Okay.
So we are removing the burst part and just taking the average of the rest. If you want, we could try a different algorithm there as well, depending on these.
Siddharth. So
Yes, sir.
you are removing all the way from start to end of the flare to calculate background, right?
Yes.
So if you take the fifth flare here, you look at where is the flare ending.
1 second, sir. Fifth flare. 1, 2.
Go to the plot. I'll tell you.
Go to the plot.
See that red dot in the middle.
Yeah, right.
That is the end of the fifth flare, right?
Yes. Okay, that is
so
inaccurate.
When you calculate the background, you will be removing all the way up to here, that red color.
But sir, I don't think it should create much of a difference, because we have a lot of data other than the flares, because the flares are very few occurrences in the entire day.
But actually, you see in between, actually there is another small micro flare there.
Sir, okay, if we were to start finding those as well, there would be a lot more. And fine, I agree.
No, I'm not saying anything problem or anything. Just that your basic algorithm, you're looking at the local minima or the delta count to decide the end of the flare. That is why this is coming. There's nothing wrong in that. It's a very basic method.
We could have tried better methods, as you say, but we do not possess the data to do the same, right? So because we would need to have these values beforehand to be fed into the algorithm. Somebody has to manually annotate every single data point, and you can't just do it on 5 data points and say that the model will be able to learn, because machine learning requires good amount of data. So we would have to spend hundreds or thousands of man hours to actually be able to annotate so much data so that we get a better model than this, right? That is one limitation of our. I agree, sir.
Okay.
Any other clarifications?
Can you run it on some other file format like CDF or?
Sir, yes. The test file that you have given seems to have some issue with the date in the CDF format. But if you remember, you have given a sample file. In the CDF format, I will be running that. You can see this is the same file that we have been given as a sample, and this is in CDF format. So yeah, it should instantaneously generate the curve now. Yeah, 1 second. I'll change. Sometimes the legend might not load in time. I'll just change it back and yeah. Right. So now you can see that you will say that a lot of wrong things are being detected, but that's just because we have lowered the threshold so much that a lot of different kinds of wrong peaks are also being detected. So I guess that is something that the user can, we can add an implementation of the user being able to change the thresholds and the value of the ratio to detect start and end points and the peaks, and the based on how prominent that peak is as well, so that they get a better plot for what they're aiming for.
Okay, thank you.
Thank you so much, sir.
Sir, I hope there are no other questions.
Yeah, thank you so much.
Thank you, ma'am.
Thank you.
Yeah, we'll
Thank
go
you.
on to the next person. Thank you. Yeah.
Thank you.
Do we have the next presentation?
Yes. Team 4 members can raise their hands.
अबे कर ले अबे किया
Yeah, Team 4 can now begin their presentation.
okay. Yeah, just to confirm, am I audible?
Yes, you are audible.
Okay, thank you. I'll just share the screen. Okay, so good afternoon, everyone. So this is a presentation by Team 4 with respect to the Interactive Tech Meet 10.0 mid-prep event, that is ISRO's web-based automatic identification of solar burst in X-ray light curves. So the flow of the presentation is that we describe the solar flare and why should we actually study them. Then we explain our statistical model and then our web-based application. After which we'll go to the limitations and the possible enhancements of the model. So what exactly the solar flares? So they are basically short bursts of radiation from the solar surface. So the radiations come in is released throughout the electromagnetic spectrum, and it can be in the optical spectrum. It is seen as bright areas in the sun. So solar flares generally happen at the places where there are sunspots. The primary energy is for flares is the release of magnetic energy from connection of strong magnetic fields. So now, while solar flares are happening at the sun, why should we actually study them? So first, most importantly, solar flares, along with other solar activities, for example, coronal mass injection, help us to study the properties of the sun, the magnetic environment, the atmosphere of the sun. And if there are intense solar flares, the large ones, they can damage our telecommunications, electricity, telegraphs, and satellites. So when we are going for outer space missions, the human missions, the long duration spacecrafts. So these, if these fall in the way of a solar flare, it would really jeopardize our mission. So that is why it's important we study the solar flares. So generally, solar flares are classified into 5 categories. So like categories B and C are easier to observe, and they give us the information about the solar activities, while they not really affect us. While the large ones, the M and X, are very important for us as they might they're important for us as they might jeopardize, they might affect our telecommunications and communication satellites. Moving on to our statistical model. So firstly, an overview of how we approach the problem statement. So a solar flare, we could divide the solar flare into 3 parts. That is its rise, the peak, and the decay. So our model identifies the duration and time of the solar flare along with the peak flux. So, and then according to the value of the peak flux, we categorize it into 5 categories: A, B, C, M, and X. And there are further subdivisions too. We will come back to it on later. So firstly, the raw data. So the raw data that we got from Chandrayaan-2, the XSM. So it had the count rate versus time in seconds. So the count rate is the X-ray photons that are incident on the detector. So we found out that 80,000 counts per second corresponds to an M-type solar flare, which is 5 into 10 to the minus 5 watt per meter square solar flux. So that is how we converted count rate to flux. And secondly, the time was given in seconds, so which is the mission elapsed time. So we found out that the time, the number of seconds is the time elapsed since modern modified Julian day, that 57754, which in Gregorian calendar is 1st of January 2017, 00 hours. 120. Then we come to the noise reduction part. So basically the data has many points, so we need to reduce the noise for us to proceed further. So first we reduce the noise using Savgol filter. Then we split the data into clusters because we know that the data has multiple missing parts. So what happens is, so to avoid any detection of false flares, we divide the data into clusters, and then we check for solar flares in each cluster individually. The second part is then we find the peak. So after the noise reduction, the graph that we get, the maximas are the potential flare peaks, while the minimas are the potential decay points or the start points. So we find out the maximas that come out to be the potential flare peaks, and this when we have a small cutoff value of for the peak, that is 16 count per second, or that is 10 to the power minus 8 watt per meter square flux. So we have taken this minimum cutoff value because we have assumed that on our classification scale ABCMX, 10 to the power minus 8 watt per meter square is the minimum value of a solar flare. So anything below that would not be considered solar flare. That is this has been taken as a minimum cutoff value for filtering out the peaks. So after we have found the peaks, we go to the just previous local minima that we have, so that there's a monotonous increase from the peak from the start time to the peak, as is the mechanism of a solar flare. We have made sure that the monotonous increase for the solar flare is minimum 1 minute, so it is long enough to cover any instrument errors, and but short enough to not ignore a potential solar flare. After we have calculated the start time and the peak time, now comes to the flare end. So our algorithm has detected the endpoint of a solar flare as the point where the flux reaches the 50% of the peak flux. Where it reaches the 50% of the peak flux. It might happen. So as you can see in the orange rectangle here, there's a sharp increase in solar flux, as should be the case for a solar flare. But then there's a equally sharp decrease in solar flare, which generally in solar flux, which is not the case which solar flare happens. So this is possibly an instrument error, possibly in somewhere it did not count the incident photon. Something happened. So this is something we need to ignore. So that is why we have said the decay duration should be at least 4 minutes, and it should always be more than the duration between the start time and the peak time, because decay is always slow in a solar flare. So now that we have the start time, the peak time, and the end time, now it's time to classify the flare. So we take the peak flux to categorize the flare, and then we categorize into 5 parts on the order of what is the value of the peak flux. This is a logarithmic scale, so each classification is 10 times the previous value. And there are further subdivisions on a scale of 1 to 10. So basically, C 3.5 type solar flare would mean 3.5 into 10 to the power minus 6 watt per meter square. And M5 would mean 5 into 10 to the power minus 5 watt per meter square. Now, what is the case if there are two solar flares together? So this is a zoomed in graph of the previous graph that I was showing you. So if you see here, just right of the orange rectangle, we see a small peak and then a larger peak. So this is a case of coinciding solar flare. So what happens is, after a peak is reached, before the flux falls to 50% of the peak value, we might encounter another case of a solar flare, start of a solar flare. So we can assume that this is the case of two solar flares coinciding. So as you can see in this graph, the green line shows the point where the first solar flare ends and the second solar flare begins. So we take the start time of the second flare as the end time of the first flare. So this is how we considered the case of coinciding flares. Now Ankur would take over for the web application part.
All right, so coming to the web application. Web application namely is divided into two parts, the front end and the back end. So for the front end, we used Node, NPM, React.js, Material UI, React Charge.js 2. And for the back end, we used Python, Django, Django REST Framework, SQLite, and Fitsio. So this is the deployment guide of the front end and the back end, which will also be available within the application itself for further reference by the user. All right, so this is the landing page of our application. It has a side panel with two options: tools for uploading the file and help section for installation guide. Also at the bottom right corner, we have a UI configurator, which allows for changing the theme of the app for better user experience and comfort. The application takes input in .lc format. The files can either be dragged and dropped or selected through the window itself. So this is the results section. The results section has an interactive graph which allows for the user to hover over a point on the graph to get the flux at that instant. The graph also allows for zooming and panning by the user. The y-axis has a flux in the units of watt per millimeter square, and the x-axis has a time in GMT. Below the graph has a list of solar flares as shown here. At the top corner is a search bar which allows for the user to search for specific flare types. Below that is a download button for downloading a CSV file. And the tables showing all the flare data. So this is the CSV file that can be downloaded. The downloaded CSV file essentially has the same data as shown in the previous slide of the application. And this is the help section, which has the installation guide for the user to refer to. Now coming on to the enhancements. So we could have an ML algorithm to predict the missing data, due to which our algorithm might fail to detect some solar flares. Alternatively, we could use a data set with better time intervals, wherein there aren't missing solar flare data. Second, a type of solar flare are often lost in the background noise in our algorithm. We could work on our application to tackle that as well. And lastly, we could use the label data to fine-tune the parameters for better detection. With that, we can end the presentation. Open questions.
So can you go ahead with the demo?
Yes, sir. तो है ना शेयर नहीं कर सकता है अभय तो तुम्हारी तो है तो नहीं है excuse me, can you check if this Abhay Tiwari, one of our members, just left in between?
Hello?
Excuse me, the organizers, one of our members just left. Can you check if he has raised his hand? If you could add him.
Hello?
Yeah, is it going to take time? Apparently, if somebody can go through the question and answer, we may save some time.
Hello, sorry, I got disconnected. All the team members have been granted access. Kindly check.
I'm audible. Hello.
Yeah, yes.
Yes.
Please go ahead.
Hello, can the other team members ask, take the questions while they set it up for the demo run?
You're about the documentation which is provided. Hello? Yeah, that wasn't sufficient enough. Hello?
We can hear you, Rama.
ऊपर देख के आना, एक नीचे देख के आओ।
Can the other team members carry out the live demo?
क्वेश्चन आंसर कर लें। हाँ।
May I ask a question while you are actually trying to run the demo?
Sorry, so this is the dashboard section of our web application.
Rama, can I ask a question?
Go ahead, Girish.
Yeah. So my question is, there are too many dependencies which are not at all useful here. So like cryptography, crypto and others. So did you actually check all the dependencies? Why exactly you use so many unwanted libraries?
We can't hear. Are they answering?
So can you please repeat the question?
Yeah, go ahead, answer.
So can you please repeat the question once?
Yeah.
I see that there are too many unwanted libraries included in the your project. See, for example, cryptography. So I just wanted to know, did you actually go through the required libraries, or you simply added all of them?
For the front-end part, like we have used only like React libraries and React Chart.js. And for the backend part, like we have used Astro, Sitio, and all the basically and Django libraries only. It's very fun.
Sorry, can't hear you.
इसमें वॉल्यूम बढ़ा दो।
Can't hear you.
Hello?
Hello.
Seems like there are some connection issues. Hello?
Hello.
Push, am I audible?
Am I audible?
Yeah, you're audible.
Yes. So like
Kindly avoid any delays. Just yeah.
yeah. So like for the front end, like we have used like React and Material UI and like React chart JS for plotting part. And for the backend, like we have used only required libraries like Astropy, Fixio, and session management and Django.
Oh, so which library did you use for the fits file reading?
For fixed file reading, like we have used Fixio.
Sorry,
Fixio, sir.
your voice is not very clear. Can you speak a bit louder?
We have used Fixio to make fixed file.
Did you say fits view? We have used fits IO library.
We have used Fixio.
Uh,
Fits.io, he's saying.
Fits.io, okay. But Fits.io is deprecated. I'm not sure you can even install this. So we tried to deploy your code yesterday. Fits.io seems to be deprecated, and you have seemed to use Astropy's.io rather than Fits.io. So that was one major issue with deploying your code that we faced.
Let's go to them. Like we will upload the file here. After uploading the LC file, file will be uploaded and like we are processing the data. So the code is processing in the backend, so we will have the code soon.
तो माइक को पास लाके तेज बोल.
So like we have like plot. So we have figured from like these are the like flux. What
The voice is not very clear.
Hello.
Hello?
Am I audible now?
Yeah, your voice.
Can you speak closer to your mic? Come closer to the mic and speak.
Yes, am I audible now?
Yes. Go ahead.
So like this is the chart. So we have flux versus time plot.
Can you try it on the sample data that we provided?
Yeah, I will show that after this. So we have like classified layers like B class layer, C class layer, and like.
But please go ahead with the demo data.
This is the LC5. So like this is the chart of the given data, and like we have E type layers. So we have which type of flares are there: start time, end time, peak flux, and peak time.
How many flares are detected?
3 flares are detected.
Hello? Your voice is not audible. Hello?
3 flares are detected, ma'am. So we have
15.
3 flares. 3.
Three.
3. Okay.
3. Can you show the plot?
Yeah.
Oh, no, to download. Just to see which 3 are the ones. Which are the 3 detected?
Like, we are given start time like from at 30 September at 3 and at 7 and at 9. So we can check.
But this is not the data given by us, some different data.
This is the data.
I don't think it's the entire data because it's just part of data.
No, he has zoomed it in, I guess.
Yeah,
Oh,
yeah.
okay. You zoom out. Yeah. You might have a reset view, no? The option in that. Zoom out fully. We have plotted everything in watts per millimeters there.
Okay, tell me one thing. How does it detect the flare? What does it do? Hello? I'm not able to hear.
Am I audible?
Yes, you're audible.
First of all, our algorithm finds the maximas, which are the potential peaks for the solar flares. Then it finds the minima, which are the potential start and end points for a flare. So then it goes through all the maximas, and it takes the closest minima to the left as the starting point. Since from starting point, it's supposed to be monotonous increase in flux, so that's why the closest minima should be the starting point. After that, it goes to the data again and tries to find the point where the flux drops to approximately 50% of the peak flux, which is supposed to be the decay point. So this is how we find the start and endpoints. After that, we verify if the endpoint, if the decay time is less than is more than the rise time. Uh, 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 Once we verify that, we can classify the flares. Then there's the case of coinciding flares. So in that case, what we do is we take the start point of the second flare as the end point of the first flare, and based on that, we check the uh, start points and start time and end time for both the flares and classify the data.
Okay, so why isn't the other flares detected in this process?
Yes, ma'am. I can see the graph. Actually, as you can see in the graph, some of the points are such that the decay time is coming out to be less than the rise time. And we found some sources which cited that the uh, the decay time to be approximately 4 minutes, while the rise time to be approximately 1 minute. Based on that, we have uh, shortlisted the flares, but this can be very easily changed in our configuration as the minimum rise time and the minimum decay time, and that would fix things.
Okay. Okay, when you do the demo, can you load other formats of the file and check?
Ma'am, our format, our application only takes .lc files. We can convert other files to LC and then upload on the data. This is one point of improvement we can do on our application.
Both in your plots as well as in your classification, you are using watts per area. How are you converting these counts to watts per area?
Sir, we read a research paper where it counted at the Chandrayaan 2 uses a silicon drift detector. So there, 80,000 counts per second. The count rate of 80,000 corresponds to an M-type solar flare, which is 5 into 10 to the minus 5 watt per meter square. So, and we checked the on the Pradhan website the plots of the flux and also the plots you were getting from the count rate. So the pattern of the graphs was similar. So we concluded that they have a linear relation, and from that 80,000 count rates equaling to 5 into 10 to the minus 5 watt per meter square, we converted these count rate to flux. Right.
But you assumed it is linear.
So the graphs of both of them are similar. Like if the graph would have been different, if there would have been a non-linear relation. Similarly, for time in seconds, we changed it to. We again went through the research papers.
So whatever counts you are getting, you are multiplying with, dividing by 80,000 and multiplying with whatever watts.
Yeah, so it comes out to 6.25 into 10 to the minus 10. That is the conversion factor.
Okay, then any other questions? Shall we move on to the next? Okay, thank you so much. We'll have the next presentation. Yeah, thank you.
Team 5 members are requested to raise their hands. Yeah, you can now begin the presentation.
Okay, so I hope I am audible. So let's start. Good afternoon, respected judges. Just a second.
We are sharing the PPT. Just wait for a second.
So, good afternoon, respected judges and dear audience. Today, our Team ID 5 will be presenting to your application FlareWorks. It is an interactive tool for visualization of solar X-ray light curves with flare detections. The main motivation behind developing FlareWorks is to assist studies of sun and in X-rays, a key primary objective of Isro's Chandrayaan 2 mission. FlareWorks is designed to be interfaced X-ray solar module instrument for visualizing the light curves and detecting solar flares, which can contribute to the solar research and space weather prediction. Moving on, the user can explore these features in FlareWorks. We can visualize X-ray light curves with detected flares of a given uploaded file. We can easily navigate between flare chart and flare table and also perform a lot of dynamic operations. Our model gives maximum true detection with almost negligible false positives. It shows a table of identified flares and their extracted parameters and provides an option to download the flare graph as PNG and flare data table as CSV as well. It is available as both standalone tool for internal servers and a deployed web version for public use.
Now we will be providing a demo of our application and its features. Firstly, we will discuss the file upload section in our app. For file upload, the user clicks to select a file to be uploaded on the application by sending a post request to the server. It takes up a few seconds before rendering the final output to the end user with all the highlighted flares. Our application supports 4 different file formats of solar flare data, which are .fits, .txt, .csv, and .xls. Now moving to the interactive features present in the graph. On the right-hand side of the flare data graph, we have a settings drop-down button to toggle the available widgets. It supports multiple features like panning or dragging the graph to a particular time interval. Another key feature we have provided is the wheel zoom, which allows us to zoom into some finer time intervals of the graph. Toggling the available information about the flares and the data points, which is usually called the tooltip, is supported by the label icon. We can also customize the grid line support with the help of grid icon, as well as the data points, which denote the entry count value at a particular instant. Next comes the reset button, which resets any zoom or pan present in the graph. And finally, one can also export the graph in the PNG format as shown here, allowing us to save a copy for any further reference. Now moving to the interactive flare table present in the graph. Drag and zoom is one of the key interactive features of the graph with which we can zoom a particular region of the graph. The left button can help us to obtain the details of only those flares that are visible, while the right button helps us to obtain the details of all the flares detected. We can also jump to a particular flare by clicking on the jump button corresponding to that flare. With the help of the search filter, we can filter the flares corresponding to a particular flare type. Here we are filtering all the A9 flares. The download as CSV button downloads all the flares displayed in the table as a CSV file. There is also a print button. The print button allows us to directly print all the flares displayed in the table. We can also sort the table by a particular column. For example, here we are sorting by energy counts. We can also select the columns to be viewed in the table. We now look at the flow of data through our application. As soon as the user opens up the interface, the server loads the default data to the user. The user may then upload the file in the desired file format. As soon as the server receives the light curve file, it sends it to the flare detection module of the app. Once all the flares have been successfully detected, it returns a CSV file containing all the flare characteristics. The server, upon receiving the data from the flare detection module, sends it to the interface, which renders it in the form of charts and tables. Also, to provide the ease of access to our app, we have also deployed the web application at the domain name www.flarefox.in using an AWS EC2 instance. The EC2 instance is a T3.AX large instance with 16 GB system RAM and running on Ubuntu 20.04 version.
Coming to the backend, the pipeline runs to detect flares and extract features from the uploaded file. It begins by reading the file and it returns a flare counts versus time array. Then peak detection is performed to get the peak time and counts. A background count estimate is done for each peak, followed by estimating the flare window to get the flare start and end times. Now, assuming a flare profile, we extract the features like rise and decay parameters, energy from the flare. These parameters are then passed to classify it. All these parameters are appended into the flare data frame. These modules are performed by each step of the pipeline, as we will explain as follows. Once a light curve file comes from the server, the file reading module calls a respective function to read the file, depending upon one of the 4 supported file types. This function returns a single numpy array that goes into the chart and into the pipeline. The peak detection algorithm, just a second, I think the slides are not changing. Yeah. Yeah, just a second. Here's the sharing. Just a second. Sorry for the inconvenience. We are sharing the slides.
So while you load the slide, can I interrupt?
Yes. Yes.
How is the flare detection happening in this?
Okay, so we will explain it in once the slides are
Yeah,
done.
fine, continue. We can see the slides up here. Yeah.
Yes, please.
Continue your presentation.
Please go to the peak detection slide. Yes. So the peak detection algorithm consists of 3 steps. Now first we bin the light curve data into bins of size 6. Second, the light curve is smoothed to remove any local fluctuations using a convolution smoother function. Then the peak detection is performed by the local maximum method. It involves traversing all the data points until a local maximum is found. This maxima is considered only a candidate peak if it is above a certain critical value that exceeds its neighborhood. This value is dynamically set as 10% of the global maximum of the entire light curve. It is to ensure that there are no peaks detected by the small bumps on high background days. A sample of the data curve with the detected peaks is shown here. Next, we go to the background continuum and noise level estimation. It is crucial for the time window estimation as well as calculation, as we will see later. We first consider the early detected peaks and then exclude a time window of about 10 minutes around each peak where the continuum fit has to be made. Then we use the speculative library to treat the light curve as a dummy spectrum. The function then performs a Chebyshev polynomial fit along the Lavender-McQuad algorithm over the peak excluded region that gives a background continuum estimate. Noise level estimate is taken by taking the standard deviation of the data and subtracting the smoothened curve from the original data counts. We have shown a background fit with the orange line in this graph for this example. The next step is the time window estimation. Now, for each peak, we traverse in both directions and up to a value that lies a certain threshold above the estimated background counts as we have shown earlier. This threshold is dynamically set as 10% of the respective peak background, of the peak of the background counts. This creates a time window that encapsulates all the points around the peak that lie above this threshold. Note that in this method, any secondary peak that lies within this window would be identified as a single event. And another note is that if there are data points are missing, then no interpolation is performed. Instead, the next available data point satisfying this condition is taken to find the window. So in this graph, we have shown the time window which we have found by this algorithm in this graph. And from this graph, we can easily extract the start and end times of the flare.
Now, the flare profile can now be obtained from the previously determined time window and peaks, and every flare is now fitted to a model, which is chosen as the following composite function: a Gaussian curve from the start to the peak time, and an exponential decay from the peak to the end time. These two functions represent the energy release and dissipation process respectively. The parameters alpha and tau characterize this profile and are reported as rising and decay parameters. They can be interpreted as follows. Alpha is the variance of the Gaussian rise, and the more the magnitude, the slower the energy release. Tau gives us an estimate of how fast the dissipation has occurred, with a smaller magnitude giving a faster loss in energy. We also determine the energy counts by taking the sum of the values in the time window. It is to be noted that the fitting has been done such that the Gaussian function peak does not coincide with the peak of the flare, and this portrays the fact that the two processes are continuous near the peak. We propose two methods of classification for our flares. Our first method calculates the SNR of a flare using peak, background counts, and noise level. The SNR is estimated using the formula shown. We reject all flares having an SNR less than the threshold, which is set now as to 10. The remaining flares are classified using the following scheme, which is given in the table. The labels A, B, C, D are succeeded by a digit 1 to 9, which vary logarithmically within the class, so that a stronger flare has a higher number. A second method for classification is a novel one, using a clustering algorithm. The data used to build the model was obtained from 250 light curves provided by the XSM archive itself between the years of 2019 to 2021. We use 5 different parameters for our k-means clustering, namely peak counts, energy, duration, rise time, and decay time. Here we can look into the duration versus peak counts plot to visualize the clusters. We set k equals 4 different clusters with their respective centroids in white. The class for a new flare is determined from the nearest centroid of a cluster. As an efficiency measure of this method, we obtain a silhouette coefficient of 0.63. Now note that this scheme is not necessarily hierarchical in nature with respect to any physical attributes. In a further work and analysis, the tool has been made keeping in mind with live deployment alongside the XSM module itself. It can also serve as an analysis package for the scientific community as well. Its flexibility enables one to utilize it for other missions as well, and our entire product can not only work for live web tool, but also to be used to generate advanced solar flare catalogs using long-term data. One of our major challenges we faced was the lack of supervised data and also the lack of flares from the active period of the solar cycle. Well, this skews our data analyzed to low quality flares, a test which our peak detection algorithm passes, but a classification using clustering suffers and can be improved once more data is available. Well, thank you for your time. We can now move to the demonstration, if you please.
Yeah, please go ahead.
Yeah, just.
Yeah, Hardik, you can share your side. Yeah. Hardik, you might unmute yourself if you want to.
Okay. So, yeah, I'm running on the local version of the app. I'm firstly uploading the file, which is provided to us as a test data.
So here it takes a little bit of while to process our data because most of the processing time is taken in conversion of the numerical time that is given from mission elapsed time, and we have to convert it to UTC. So while traversing through this entire time series, that's the major step that takes our time. But that may not be a real issue because we don't intend for a live deployment as of now. Because if you're giving us one day entirety of data, we expect the next data to be in next 24 hours. So we have 24 hours in our hand to process it.
While that loads, why did you make that assumption you have 24 hours to process it?
Because all our data that we had for our like analysis and study were in one day light curves all. You can if you could give us a 5-minute window, even if it's a real time data, every 5 minutes the satellite server is sending us, it'll all anyways be faster. It won't take as much time. So here's a sample data that you provided.
So as you can see that from this particular file, our algorithm is detecting one particular flare, and you can see that these parameters are shown in the table.
Okay, is it done or is it continuing to search?
No, it's done. This is the final results.
So what about the other small flares which are seen in the data?
Yeah, so you can see that the peak count of the flare is actually less compared to, you can say, data which we were dealing with 2021 and all. This part of the file, I think it is in 2019. Can you show the date above? I think it shows, Hardik. No, here we also have a date option. Yeah, so it's 2019 30 September, which is the quiet phase of the sun where you won't expect a lot of flares. So we ourselves, while we were dealing with a whole range of data, we set a small threshold for our SNR as well, and as well as for our 100 counts above the peak. So if it's not 100 counts above the background continuum, it's not going to consider it as a flare peak candidate. That's another threshold we had. So
that's a limitation in the code, right?
It is a limitation. It can be tweaked for, let's say, if you want to analyze flares on the quiet part of the sun where very small flares are being detected. On the other hand, if you take a data from 2021, flare is like 1700 counts, 2000 counts high. So on these cases, we don't want to see those smaller flares.
No, let go of the other data sets. The one which is shared with you here, it's very obvious that there are many solar flares in the data. From the light curve, you can find it out.
In context to, let's say, active period of the cycle, I think this is very small.
Yeah, whatever be it. But here, indeed, there are a lot of solar flares seen in the data, meaning there are many flares ranging with different intensities. So, and all of this needs to be captured. So what would you do?
Our threshold, which we have set to 100, and as well as the SNR, we can just reduce it, and that would automatically incorporate all of them. In fact, our peak detection algorithm actually finds these as well.
Yeah, can you show that?
It's not part of our UI directly here right now, but our code, backend code is flexible for that. If you want, we can.
Yes.
No, actually, can you go to your presentation and you had shown some sample data as well? Can we?
Yeah. I can show that, of course.
Yeah.
You can go to the presentation.
Okay.
Arnab, can you present it again? Yeah.
So in that data we have taken from.
No, Hardik can actually view that data. The default data can be actually reloaded again.
You can show the sample which were used in our presentation as well, which is a good one where there are lots of flares.
Yeah, Hardik can share his screen once.
Should I share the app or the presentation?
App. In app, it by default. Okay, wait.
No, I would prefer if you share the slide, no, because the slide presentation is what the judges want to see.
Slide. Okay, I will.
You can take your time. app itself also loads the sample data just in case if you want to explore the features as well. So that's
Even that is fine. I mean, I'm
Mhm.
not particular about the presentation.
Oh,
Any of them will do.
any of them? Okay, Arnab is sharing.
Okay,
Yeah, Arnab.
we are showing the data which
Yeah, you
is
can go to
taken
the
for
background one itself.
This
Yeah.
one.
Yeah, even here, you don't consider the small scale flares as flares.
Uh, because our peak detection algorithm also has a dynamic range where it says the
Okay, so
flares
can
are
you put a number on the dynamic range? What is the
10% of the global maxima.
global, as in how global?
I mean the whole day
Whole
data.
days.
So every day, if a day has, let's say, smaller flares, then it might capture. But then the data which you have given are very small, where it's 100 threshold. Because we were also analyzing data from 2019, there was many spikes which I thought like they look like noise to us, so we had to cap it out somewhere to incorporate, let's say, this kind of data as well, where you can see
Because I
the
see
flares are
some
reaching.
small scale flares. I don't think you have captured them. So that seems like a limitation.
It's probably because here the best flare is around 3000 almost.
See,
So
there's a fundamental flaw in your assumption.
Mhm.
Because of taking this global maxima, what happens is during solar minimum also sometimes X-class flare happen.
Okay.
Suppose a day an X-class flare happen during minimum,
Mhm.
you will take that as a global maxima and keep a cutoff at 10%.
Okay.
Which means all the B-class, C-class flares which happens after that, you won't
Mhm.
capture it. Right.
Okay. So, but it is dynamic to that day's range as well.
That's what I'm
We had.
saying.
Uh-huh.
If one X-class flare happens on a day,
Oh,
a
okay. Yeah,
huge
yeah.
flare,
Then it won't capture the very small ones. Indeed. We can remove that threshold. Then we'll have. Actually, our peak detection does detect all of these peaks. It's just a question of tweaking those parameters. We tuned it for the entire 2 years, and
you could have
thinking.
given a slider on your UI
Okay.
to
Okay. All right.
adjust that.
Adjust that. Okay.
So if you were to change the threshold and run it, how long would it take?
It will take almost the same time. The real time taking which we found was actually conversion of time to UTC and the upload of data. Like reading the
But
entire
she's
data
asking
was.
now. That's what she's asking.
Now the demo data which is given for you.
Oh, so
can it be run and can we see that if it's picking up the other flares too? How long would it take?
So we have to change the code a bit and then run it. So I mean, is this acceptable for the organizing team?
It's the threshold which you said, right?
Yes.
It's in the code itself. It's in the.
It is just the threshold value which needs to be changed in the code, right?
We don't have it on a front end, but
Yeah,
we can
fine.
go to.
Yeah.
My question is, how long would it take?
Yeah, basically you want to change that what parameter can
I
come
think
in
less than 5 minutes. We can try it
Yeah.
at least.
Which parameter I had to change?
So meanwhile, I can
The
ask a
threshold.
question. If somebody try that, I'll just ask one or two questions.
Sure.
There was you are also using a lot of this, like this 10%. You are using many other hard-coded things like 2 minutes bin, for example. Then you are using 10 minutes on both sides of the peak as the as a window. Where do you get all these numbers from? Is it just
Our bins have been taken from a paper which was a flare characteristics paper. I think it was
Yes,
the Grishuk one where they had taken a bin.
you see, when you do that, you are immediately assuming that if a flare happens before next 10 minutes, there will be no flare. Which is not correct, right?
No, our bin is just 6 seconds. It's a six point size, right? So
No,
we are
no.
assuming 6.
No. Your document said
The 10-minute window which we are taking is for background estimation. So what we are saying is because background fitting is going to get severely affected if we have the peaks itself in the profile, like the data points. We want to remove those peaks. So we take a safe window of 10 minutes and we remove those peaks and then
yeah.
fit the background.
So for binning, you are using 1 second to 6 seconds.
6 seconds.
Right.
Yeah.
So is it like dynamically decided, or how do you decide which one? 1 second, 2 second, 3 second?
This was so the flare characteristics paper take ghost data, and ghost data had a 3 second sensitivity, and where they had taken a bin of I think 10, so we took 1 to 6 basically.
So
Like
which one you are using for when you run the code?
We're using
1
6.
or 6?
6.
You're using 6 always.
So for fitting parameters for any form of calculation, we are taking the raw data itself. But only for peak detection, we are taking a 6.
Yeah. So after that, for smoothing, you're using 2-minute window, right?
2-minute Blackman window, yeah.
Yeah. So if any flare, if there is any flare which has a rise time 1 minute, for example, your smoothing window will kill it, right? Yeah, in case example, I'm saying it's okay.
Yeah, but the convolution smoother will not actually make it like a flat. It's going to take that rise with the long.
It will become like a little hilly type. Okay. And then for background estimation, you are using a 10 minutes window from the peak. Okay. And your code reads all CSV, ASCII, fits everything, XLX. Whole team disappeared.
Hello. We lost Abbas. Yeah. You can wait just a second while he rejoins. Organizing team, can you just let Abbas in? He's trying to be the speaker.
Yeah, he's been granted.
Thank you. So, what was your question again, sir? Can you repeat? I'm sorry for the connection loss.
No, I was just saying that you are using 2 minutes to smoothen and another 10 minutes away from the flare is always taken as background.
Yeah, that is it.
So if a flare is not decaying within 10 minutes, your background count may show up as very large because of fixing these numbers.
10-minute is a safe window, I guess, for background.
On the rise side, no, you cannot say that. Even decay side definitely 10 minutes is not a safe window, I would say. But rising phase will be okay. Right, Abhilash?
But can we expect the background to also increase during a flare because of an high flare X-ray event, high count event?
No, the background, flare and background is different only. Background is determined by overall solar phase. Okay, I'm done. Anybody else have any questions?
Okay, then I doubt you'll be able to do it so quick by different threshold.
Can we just wait for 2 more minutes? Like we are on it.
Yeah, you can present if you want while you can show.
Yeah, okay.
Yeah.
I think Arnav needs to stop the screen sharing.
So our duration is actually estimated from a, you can see.
I think it has, we have got the.
Yeah, you can see the modified result here where the peaks are being detected.
How much is the threshold now?
Like we change it from 100 to 50.
50.
Yeah.
Minimum 50 above the background.
And how many flares have you detected?
We are detecting 6 flares.
6. Thank
you.
Go back to the plot.
Yeah.
Go back, yeah.
So, just show the plot. Okay.
So all those double peaks are detected as one flare.
Yeah, they are taken as one event. So our time duration is estimated when it drops to like 10% of the peak value itself. That's a definition we picked.
What if you go much lower in the threshold? What do you expect? I mean, do you expect some false detections? Have you tried very low thresholds on this other datasets when you were writing the code?
The problem is to actually tell apart a false detection from a from like we don't have a reference exactly which one would be a flare, because sometimes the background itself is very fluctuating. There are instances where there is no data in between and suddenly the background has rose above. So then it can also
Okay, did you try going for lower thresholds and find what the code is doing? Meaning, for you to say that there could be false detections, have you tried with very low thresholds?
Himadri, would you want to answer this?
Yes, we have tried that, but that is very much dependent on what kind of data we have, because there are some data transformation which Avas has said, and also when we do for a very low threshold, there might be instances when there would be very long duration flares which is detecting, like our code is detecting. So definitely, like we are expecting like something like an exponential Gaussian rise and exponential decay, but when we like visually inspect those flares, they are not following that pattern. So from there we get an idea that okay, that threshold has to be like somewhat higher, and we have actually like one of the references we have used is the goals data. They have a catalog of players, and we have like checked that okay, at this particular instance of time if there is a player or not. So from there we
So the problem with ghost data is that it's not as sensitive as Chandra and XSM is. But one thing is because our duration.
So what?
Yes,
So
ma'am.
one option which can be given is in the GUI itself, user-defined threshold can be set, meaning user can define the threshold and run the code.
Yeah,
That
sure.
option can be given, right?
Yeah,
So once you go lower as much low as possible as you want to detect the lowest flare, and then you find that okay, if it is not suiting, then increase the threshold. So it's completely left to the user to decide that. So, yeah,
I do
that
agree
can
that.
be done in this. Okay.
Yeah.
Okay then. Thanks so much.
I'll just ask
Yeah.
one standard question.
Yes.
Sure.
Does
Yes.
all the other file types work on this? XLS, CDF?
We have made functions working for all these files. It's just a matter that what's inside the files exactly. For example, I think we had a txt file where the time given was already UTC. So we are making a conversion from Mission elapsed time to UTC, which clashes. So if the data format inside the files are consistent, we can easily read all the files.
And here you are not doing any fitting with any model and all, no? You are not doing any such things.
We are fitting the flares, of course. We are fitting a Gaussian rise and a exponential decay to the flares themselves. We are reporting those parameters as well.
You are just reporting. You are not using that parameter for anything else.
No. So we tried for the classification, the clustering one, but
Okay, fine. But
it
now
didn't
you are
work.
not using anything, right?
No,
You are just
right now we're not using.
Okay, fine.
Okay. Thank you. So
Thank you, ma'am.
we'll move on to the next. Yeah. Thanks.
Team 19 members kindly raise their hands. I'll make them presenters.
Team 3.
Hello, am I audible?
Yes, you're audible.
Can you let the other two team members onto the stage?
Yes, they have been granted the access. So total of 3 members are now presenters. You may present your.
मेरा साउंड क्यों बंद हो गया? तेरे को सुनाई दे रहा है?
I have a video on. Okay. We are audible and visible, right? So we'll just start with the presentation. Okay.
Yes, please go
Yeah.
ahead.
My screen is visible, right?
Yes.
Okay. Yeah. So this is the presentation for our flare detector. The program accepts, as per the problem statement, it accepts the various file formats like FITS, ASCII, XLS, and we output a visual representation of the identified solar flare. And for each flare, we also provide some additional information about their characteristics like rise time, fall time, and peak duration, and also the peak flux. Our code is the workflow. The code flow is divided into four parts. First is the input. So when you first see the landing page of the front end, it is a file upload dialog box, and then you upload the file. The second step is our file approval, which in which the backend attempts to open the file, and then if the format is fine and the file is consistent, it returns a proper output, and if it's not consistent, it returns an error. The core of the algorithm is the main statistical model that actually detects the peaks in the light curve, and we'll delve into this core in the next slide. And the output is the final part of the code where it outputs a visual representation of the flares. So we divide the core of our code into three parts. First is the curve completion. So when we see the .sa or the sun angles file, we see that for angles apart from beyond 35 degrees, the solar flare is not present in the timestamps. But what if we have a void during which a solar flare is actually happening? This is crucial information. That is why we attempt to complete the curve. That is, we fill the voids based on interpolating between the nearest data available. That is so that we get a continuous series of timestamps instead of broken segments. The second is our error smoothing, in which we see that there's a lot of background radiation in our XSM files, and that is why we try to remove the high frequency noise from the data so that we are able to detect the peaks that are actually solar flares instead of detecting numerous false alarms. And the last and final part is the peak detection, in which we use sophisticated algorithms and very fine-tuned fit parameters to identify flares. One property of our algorithm is that it misses almost no flares because we prioritized finding even rarely our algorithm even identifies the noise as flares, but it never identifies it almost in the test data it never identified a negative alarm. Yeah. So in our presentation, we included a demo video, but we'll not be playing it now because we'll be doing a live demo with the front end guys. And yeah, we can even demo the standalone app. Um, yeah. So a few caveats. So as I already said, because our algorithm doesn't miss a real solar flare, it sometimes classifies shallow hills as peaks. And the second thing is the installation part. So our installation requires a properly set up environment in which Python 3 and pip are required for the standalone app, and a dedicated uploads folder has to be created for the web version. If these requirements are met, our installation script runs smoothly. When we look at the future scope, so the backend, which is the primary peak detector, we can use it for identifying peaks in various other things apart from X-rays like infrared or any other thing. And also, the one thing that we thought about implementing is to make a real-time peak detector which can accept a continuous stream of data directly from Chandrayaan-2 and set out public service alarms whenever it detects a high-intensity radiation that has the possibility of causing disruptions to public life. Yeah, that brings us to the end of the presentation. Thank you. Should we continue with the demo?
Yes, please go ahead.
Yeah, Gautam, if you can share your screen.
Hello, is my screen visible?
Yes, please go ahead.
Alright, so I will be going with the web version. So this is the first page that the user is going to see. So it basically describes what are we doing, and if you want to view the documentation, you can click here, and then there is a UI interface for file upload where you can drop a file in this area, or you can click to upload the file. So I'm going to go ahead and choose a file. So I'm going to choose this file, and I'm going to specify the file format of the file that I have chosen, and then I'm going to submit it. So you can see here that there is a description of how the file should look like. Like if the file matches the syntax that is shown here, it will show correct results. So I have clicked on submit. Now my backend code will run and it will display in few seconds. So as you can see, like I have shown here in the graph, that there are 5 flare regions that are there, and for each flare region I am specifying various characteristics for that flare, like peak position, rise time, decay time, duration, and peak flux. So as you can see, this is the flare 1, flare 2, flare 3, 4, and 5. So as you can see, like in the first graph, like it appears that there are only 4 regions, but actually what is happening is there is a smaller flare happening in presence of a larger duration flare. So as I can show you that our code accepts three types of formats: FITS, ASCII, and XLS. So I'm going to show them one by one. So first I'm going to show ASCII. So here you can see that there are 3 flares that are detected. And now I'm going to show FITS data. So yeah, so now we are going to show our standalone application.
So I will be showing the standalone application. I will now present my screen. Can everybody see my screen? Is my screen visible?
Yes, yes, please go ahead.
So this is the UI. This is the graph area. For a file upload, you will have to go here, see the supported formats. This is FATES, and this is some information regarding the FATES data file we accept. Then ASCII and XLS respectively. So first I'll open the FATES file, the .lc file here. And as you can see, it has seen it will plot the whole curve, and then it will mark the ranges where the flare was detected. As you can see, there is an overlap, and we can clearly see that overlap as well. To see the ranges, to see each particular flare specifically, we can go here, click on this drop down menu, and then here we can see a list of the flares that has been detected. First of all, you can select any one of the flare to see them, to make it plot, and then specific parameters regarding the flare has also been displayed here, like the peak position, rise time, decay time, flux, and the duration of the flare. For each of the individual flare, it has been detected. It has been shown. Similarly, we can go to the ASCII. So for that, here it is an ASCII file. So the ASCII file has been opened here, and as you can see, this is the ASCII value. This is the graph of the ASCII file that has been uploaded. And here is the list of the ranges that our code has detected, ranges that is the solar flares that it has detected, and this is the plots, the respective plots. Similarly, we can select an XLS file as well. And as you can see, the XLS file also, it is the same plot, because the same data has been encoded in different formats, like in XLS and ASCII. And so similarly, and it also accepts the data in XLS format. If you want to see the documentation, you can just click here and it will open the documentation here. Okay.
Okay, so the FITS file which you have just tried extracting the flares, can you go to that plot?
Yes. This is the plot.
So how many flares are detected here and what are the parameters of the flare?
The 5 flares has been detected. Here is the list, like this is the first flare, and the parameters here are the peak position, rise time, decay time, flux, and the duration. The peak position is 70814.
So this double peak is taken as one flare.
Yes, it is taken as one.
Okay, fine. So go back to the full plot.
I have one question. Is this the same code as you had submitted on the 18th March?
Yeah, but there we submitted this code, and after that, since there were some compatibility issues, for example, they sent a test file with integer timestamps, but in the sample file they sent something with UTC timestamps. We had to edit this code once so that this format will be accepted. So it is not exactly that code; it's just modification of that code.
Are there any, I mean, from the coding point of view, from the algorithm point of view, is there any changes? Are there any changes?
There are no major changes. We just parameterize one value. For example, in the peak threshold detection, we parameterize the value instead of hard coding it. We in our future plan, we are planning to include that in the user choice
Yeah,
rather than hard code.
could you just show the previous version, please? Then we can go to the next version.
So you want to see that from the front end, right?
Yeah, so whichever code you had submitted, can you show that?
Yeah,
instead of-
can you just revert it back to that commit branch?
Yeah.
Yeah. Bottom, can you just revert it back and present?
So while that is done,
Yeah.
this plot which you had tried extracting 5 flares,
Yes.
from the plot you can make out that there are other flares too in the data, correct?
Yes, yes.
So why are those not detected?
You mean these smaller flares on the left side, right?
Yeah, correct. Smaller flares.
Yeah. So we are like when we are fine tuning the fit parameters. Okay, so this is actually written in one of our documentation as why we are using some flares but discounting other flares. So in the width, we are taking the width to be a minimum of 60 seconds. So the flare has to last at least 60 seconds for us to classify that as a flare, and the flare intensity has to be sufficiently maximum so that we are classifying that. Else, we are classifying that as a false positive.
So if you lower the threshold, would it be picked?
If we lower the threshold, it will be picked.
So you're just conscious, basically, not to get false detections. You're just trying to have
Yeah.
it as,
Yeah,
as
what we actually did was we downloaded several XSM files and then we ran this model on many of them and then accordingly chose the fit parameters so that we get the most accurate predictions. But since the test data is a bit different from the ones that we like fit the model on, therefore there are discrepancies. But if we try it on real world data or the data that we are about to expect, then I think we can improve the fit parameters to classify what we want.
Okay.
No,
So,
your case, sorry, go ahead, Rama.
Depending on the intensities, have you gone ahead classifying the flares?
We have not bucketed the flares into classifications, but we
Okay.
do print out the peak flux for each. We can just divide it into like we can
Okay.
that's just a one step further.
Okay. Yeah, Srijit, go ahead.
Yeah, so you are also doing taking a maximum of the day and taking 50% of that as a cutoff, right?
No, what we are doing is
Average to peak by 2, right? That's what you're doing, right?
yeah. That's what we were doing. But after we parameterized, we actually used the how much noise there is in the data, and then we are calculating what our threshold should be.
So this change you made after that recently.
Hmm.
Okay. And
We thought that
also,
would be more like informative for the user.
correct, obviously, because just like we told earlier, if you take the maximum and the average, you'll always miss all the small flares.
Exactly.
If one big flare happens in a day, all the small flares.
Yeah, exactly.
Yeah. And similarly, the width also you are just taking 1 minute. It's also very, hard-coded value.
Yes.
It not be 1 minute all the time. Also, you are doing some multiplying 90% of the maximum as a relative height.
Mm, no, that 95%. Wait, was that 95 or was that 90?
90, right? 0.9 you
Yeah.
are multiplying with.
No, that's not a multiplication. What we are doing is we are saying that like we identify a peak, we identify the peak flux and the peak point, and when we have to detect the edges of that peak, we are saying that 95% of the area of the curve should be classified as the peak. So the edges,
So
yeah, not
you're
95,
taking
it is
area,
90. Yeah.
taking
It's
total area and then taking 90% of that.
yeah.
Okay, okay.
That's the
You are not
prominence
doing
value
any
actually.
fitting or anything here, no?
Since the data was not labeled, we are not doing any chaining. What we are doing is making a statistical model that can give the best predictions.
But no fitting involved here, no
No
model.
fitting is involved here.
Yeah. Uh, okay. Also, it works on all ASCII and all the CDF and
It
it's
currently does not support CDF because CDF requires a C backend installation. But it like
okay.
file acceptance is just one thing that we can always implement later. It accepts the other file formats like Excel, ASCII, text, or FITS.
Will this work on Linux?
Actually, we have a mixed development environment. I worked on Windows. One of the front end guys works on Linux.
Because we yesterday noticed that some you are using Windows type slashes, not Linux type slashes.
Yeah. Yeah, exactly. So our primary development is on Linux because it was mentioned in the problem statement.
Okay.
Okay, then. Thank you so much. We will move on to the next.
Okay, bye.
Bye. Can we have the next presentation? Hello? Hello? Hello, can you hear me?
Yeah, I can hear you.
Okay. Are there other people? Avanti?
I think she.
Which team is next one?
T3. Hello?
I think the host has to give permission to team 3.
Yeah,
I think
correct.
she dropped off or something, I think.
Yeah, correct.
Yeah, Yuvraj, you have the access.
Hello, am I audible?
Yeah.
Yes.
Hello, good afternoon, everybody. Am I audible?
Yeah,
Yes.
you're audible.
Please go ahead. Hello?
Hello, Yuvraj. Are there any other members joining in? Okay, we have.
Hello.
Yeah, sure. You can go on your presentation.
Am I audible?
Yeah, you're audible.
Raj, you can hear me? There is an echo somewhere. Yeah, Viraj, you are presenting? Okay. Is there an issue? Yuvraj, I can present if you want.
Yeah. No, audible, right?
Yeah.
Okay. So, you see my screen? My screen does not. It just signals that. Yeah. So this goes up.
Hello, you can begin your presentation.
Yeah, I think I've presented my screen, but it's not visible for some reason. Just a second. I
can present.
Yeah, so it's visible, right?
Not to me.
Not yet.
Okay. Okay, Janan, you present.
Sure. Is it visible now?
Yes.
All right. Okay. So yeah, hello everyone, and we are team 3, and today we shall be giving a presentation for our solar X-ray burst detector. Yeah, so this is our agenda for today's presentation. We'll be going through in this order. First, we'll be discussing the data organization, preprocessing, the feature extraction, ML model, and finally the limitations and feature scope, and we'll go through the web application. Yeah, so starting with the data organization, we have used this following libraries to allow us to read all these different file formats, whether it be FITS, ASCII, or XLS. And these are for the calibrated files. Since we had some raw files as well, so to convert them into calibrated files, we have described the procedure in this as shown here on the website in Pradhan. Yeah. Moving on to the data preprocessing part, there were mainly 3 attributes, which was the time, the count rate, and the error in the flux. But of course, since error is not really important by plotting, so this is a plot of the count rate versus the time, which is the primary part. And the gaps in the data which we are saying is due to the absence of due to the good time intervals and the bad time intervals. So where there is an absence of data, we do not see any data points. So first of all, obviously, the main challenge was we needed to smoothen the curve because of the very many variations in the data, and hence we would find too many maximas and minimas in our data. So we first of all decided to smoothen it so that only the prominent peaks would remain in the data. And for this, we first of all tried the boxcar method, which was simply convoluting with an averaging kernel. But again, that had a high influence from the noise in the data, and particularly from the gaps which were present between the good time intervals. So that was giving some flat lines, which would be detected as false peaks. So to counter this, first of all, we thought of the naive method of interpolation. But Then we thought that the simple method of Gaussian convolution should work, and hence we tried it, and that gave us much better results. And hence, for our final code, we used a Gaussian kernel method. So yeah, this is the comparison of the two kernels, and this but on zooming in on the peaks, you will find that the box on the peak near the peaks in the box kernel method, you will see many flat lines, whereas in the Gaussian kernel, it is a much smoother peak. So it gives a particular distinct point as the peak rather than giving a flat line on a series of points. So that is why we were using the Gaussian kernel. Yeah.
Thanks a lot, Janan. Respected judges, permit me now to explain you the procedure we followed to extract the features from the given data for creating a data set to train our machine learning model. The task for us was to find the peaks of the burst, rise and decay time of the burst. We simply use the functions of an open source library like SciPy. We use the functions find peaks and peak prominences of that SciPy library to detect all the required bursts. Let's see how this find peaks work. Find peak function gives us all the peaks of the curve, whether it is of a burst or of a noise. Yeah, that was a flaw in that function. So we use the peak prominence function to detect only the peaks of the required burst. Let's see how this peak prominence function work. Yeah. This peak prominence function is to filter all the actual burst peaks from the noisy ones. How it works is simple. We define a line as the average of the maximum and minimum peak detected by that peak function, we find peak function, and we consider all the peak above that line only. That is all about the detection of the peaks. And for the duration of the burst, to determine the duration of the burst, we use the peak width function. How it works is chooses a particular baseline for each peak and simply finds the intersecting point in nearest to that particular peak and consider them as the left and right bases, meaning the start and the end time for the peak. Since there is a lot of noise in the data, we shifted this this width by 20% to mitigate this effect that might cause the peak to be shown lower than the supposed width. So hence we choose the relative height 0.8 parameter in this function. And for the rise and decay, we again use that peak width function. The algorithm of that peak width function gave us the left and right bases, which correspond to the start and end time of the burst respectively, and that is the code that we use to find the rise and decay time.
Right. So once we have extracted the decay time, the rise time, the maximum peak flux, we now converted that into a data frame with 4 columns, and then we considered the k-means clustering algorithm, which is an unsupervised classification algorithm, to cluster the data according to the set parameters. Once we did that, we then used the elbow curve method, which is a pretty standard way of determining the optimal number of clusters for the given data set. And so by utilizing this algorithm, we came up with about 3 to 4 clusters for the X-ray bursts. And because the magnitudes of the X-rays are significantly far apart in some instances, we use the logarithmic scale to take that effect into account. So that's how the ML model was made. And then now finally onto the limitations and future scope for this model. So the first thing that is really obvious is that there are large variations in the magnitudes of the peak fluxes in different data files. And then a lot of them don't follow the same behavioral trends and are also affected by noise. So the idea is that it's very difficult to apply the same standard approach that you have, let's say, on the example plots we showed you on the earlier slides to all kinds of data sets. So what you need is some sort of a approach which targets specific behavioral trends and addresses and takes their behavior into account to then determine the maximum peak flux in that particular example. So that's one limitation that can be improved upon. The second thing is that so Khushagar talked about setting up this baseline, which is then used to detect the start times and the end times. But the issue currently is that let's say there are 2 flares, and the minima between them lies above this set threshold value. What then ends up happening is that the start time and the end time for both the flares end up being the same out of the algorithm. So this is again one limitation that needs further consideration and can be improved upon in the future models. Lastly, for now, because we're processing this from Windows, there's one code snippet that we were not able to include in to convert the raw data files to the calibrated files, though we do know like the code that needs to be put in the Linux file to be able to do that. So just for that reason, it's a bit computationally slow. But again, it's not a big issue because once we have access to a Linux operating system, this can be easily addressed. Now, for the future scope of the model, so obviously the feature extraction is the main component here. If we're able to do that efficiently, we pretty much can make a very efficient ML model because the parameters are now more reliable. And so this is one area where we can try to come up with more optimal algorithms given particular data files and how they behave. Second is this multiple thresholding technique. So what happens is, let's say you have one file where you have a peak flux, which is much greater in magnitude than, let's say, another flare in the same data file. So what ends up happening is that the algorithm detects the first maximum peak flux, and then it leaves out the other one. So how the way this problem can be solved is you go with the procedure we just mentioned. You find the first maximum peak flux, then remove all those data points, and you again carry out a second threshold, again set a second threshold value. And this time, because you've removed the maximum peak flux magnitude or anything that was there in the previous case, you now have a new threshold value above which lies the second flare, which we had not considered earlier. So by using these multiple thresholding techniques, we can detect all the data, peak fluxes in a given data file. So this is how this particular issue can be addressed. And lastly, what we can also do is, so I just mentioned the multiple thresholding techniques. So what you can do is you can combine all the time series data into one big data file, and then carry out this multiple data thresholding procedure such that you have all the flare peak flux values with a less computationally extensive algorithm, so that you can have the answer in a fewer number of steps. That's the idea. Yeah. So
Okay.
and then
And
we
you
have
can continue with the demo.
no. So we have one more part there. So I think Janet's see this. Sure.
So after Jen presents the screen again, I'll just take a minute to explain the last part of the agenda in our presentation, which was about the web application and the UI that we designed for it.
Yeah, so I think, is it visible?
Yeah, okay.
Okay, great.
Not
I'll
yet.
just skip to the file.
Yes.
Yeah, web application, visible, right?
Yes.
Yes. So the web app was designed in Python and Flask due to the similarity in language with many of the libraries we use for computational physics. And the graphing library we used was Digraphs for performance specifically. So this was about the architecture. And the web app itself has essentially 3 separate pages. The home page where you upload the files and set some metadata if required, a user guide with detailed documentation on how to use it and what kind of input files it can parse and accept and how it parses them out of all the different formats possible. And the third is a results page where it shows the graph with identified bursts and everything else. Move to the next slide, please. So all of this is contained in 3 logical parts of the code. One is the web server itself. Additionally, there were the statistical and ML models implemented separately. And then there was a file parsers module, which is designed to read and write from all the different formats which were required, which communicates between the server, taking receipt files, passing them to the model, and getting the data back out. And these 3 work together to perform the whole thing. And it's designed to be very easily extensible. You can write a new module for any new type of format or so that's not there. And So that is essentially it. How to use the app is upload a file on the result page. It generates a UUID for it, and the data is stored. It goes through the server, and the client side will query the process data back as soon as it's ready and plot it on the page, making it visible. And this is a list of all the libraries used if required. There are instructions with the requirements and everything. Additionally, we also had a spec file to generate a standalone executable, though that's not submitted with our code, but it's the template to do it can be done. That brings us to the end of a presentation.
Yeah, so we'll now move on to the demo.
May I share my screen for this? Sorry, this will just a minute. I am having a permission issue.
Just 1 second, we'll use some other laptop to present because this one is having some permission issues. Just give us 1 minute. Apologize for the inconvenience.
Hi, sorry for the delay. This is Gautam. I'll present the screen now. Is it visible?
Yes.
Okay, great. So
Yes.
I have started the web application here. The process for doing that was as described in our README, uh, essentially from the command line. And here is the sample data that was given, 3 files. So this is the UI of the server, and you can choose a file and select one from the file system, or you can even drag and drop. So I will do that with first the text file. So there are many assumptions we made about the format. Some files will work and some won't. If they don't, it will tell you exactly why. Like for instance here, if we opened this file with this one didn't work. If we opened it with CSV, I did that just before, and we detect based on column names. So I will try another one now. This is the second LC fits file. I have uploaded it and it's processing. And this is the graph with, it has plotted all of it and it's detected one peak here highlighted in blue. And all the details of the peak for each peak will be listed in the table below. And you can download the list in any format that you like as well. 4 formats are provided currently. You can zoom into the graph and zoom out into subranges. So, and if you see the user guide, this explains how and why it processes which types of files. So what all these metadata options on the homepage you saw. But the problem here was there was a lot of ambiguity in the kind of input that could be accepted, almost anything. So we made a lot of assumptions about which data to use and how to use it. All that is explained here in detail. I will, yes.
So I think we can take the questions now.
Did you also try in CDF format, the CDF file? You are muted.
Sorry, no, as you can see in the guide, we have not implemented CDF yet. I can upload it anyway, but.
Okay, you throw an error. Okay.
Yes, it will show that the file is not supported,
Yeah.
unrecognized.
Okay, can you show the results for the XSM Leica file again? Yeah,
These were the results.
Yeah, so why do you think the rest of the flares did not get identified?
Yes. So we use the SciPy library, and reason why is that, as I said, we need to have these multiple thresholding techniques so that we can detect all the peaks. So in this case, so Kushagra talked about how we determined this baseline. So probably this baseline falls at about between 50 and 100 here, which is why it only detects peaks above that threshold baseline as detected by the SciPy library. So one way to solve this problem is what you can do is, so you have this peak. Gautam, can you just present that screen? Yeah. So you have this peak. So you remove all the information around. So you remove all these values where the peak has been detected, and that can be easily done because we know the start and the end times. So we know what data points between what two times need to be removed. And once you removed all these data points, we again run the algorithm on this. And this time, the next baseline is going to be at about right next to the peak that was just detected. So these three peaks that we see on the screen at about 2000, and 2200. And so then once we detect these, again, we remove these points and we detect the ones at about 1200 and 1400. So that's the procedure we have in mind.
See, I can tell you immediately why it didn't detect, because you are also using the very same mistake which some others did previously. You also take the global peak of the day and take 50% of that, right? So immediately that makes sure that all the smaller ones are not detected. You are taking threshold value as 0.5 times the sum of minimum and maximum local peaks, right?
Yes.
So here you just look at it. Here maximum is around 325. So you'll take a half of that almost. Okay, minimum will be somewhere here. So everything below say 150 you will not detect here for sure.
Yes, sir. So that's why what we said was that we needed multiple thresholding for this procedure, because if
Yeah.
we cut it off, then only how most of the peaks will disappear, right? So for example, for this one peak we detected, what we will need to do
Understood.
after
I
this is
understood what he was explaining that.
yeah,
Or better way would have been ignore the global peak, only look at the background and take some decision based on that.
yes. So actually we tried that, just seeing the background, but unfortunately in the data that we took, which was the XSM data, there was a lack of many of the points because of there were good time intervals and bad time intervals. So there was a lot of data lacking around those peaks. For example, one peak started in the bad time interval, so there was no rise time at all. So in those cases, this procedure was giving a problem, and also there was a lot of noise in this data, right? So this gaps were basically causing the whole algorithm to malfunction. So that was why we tried this, and yeah.
And also your start time and end time, I think you simply used SciPy's peak width function and whatever width it gives, you took that as the beginning and end, right?
Yes.
I think that also was like too easy going decision because you can see here also your start time is somewhere in the middle of the flare and again somewhere in the middle of the flare it is showing us end time. Obviously that is not correct, right?
Uh,
So
so actually, this the highlighted region. So that whole region is considered as the width of the peak, right? So the space. Rather than this, can you zoom in on that part on the peak?
yeah, if you can zoom in, you will see that. See, look where the starting is coming and ending is coming.
Yeah, so this was, as I said, due to the point 0.8 which we took here, because for the smaller peaks, this was giving a lot of gap in the. So for example, some peaks were starting below even the below the time which it should have started. So that's why this was actually a trial and error method by which we took the 80%. Yeah, in this case, it is not. It is giving a bit higher than what it should have.
Okay, did you try any? You tried fitting with that Gaussian and exponential decay, right? Initially,
Yes.
uh, and what you did with those fit parameters, A, B, C, D, E, or whatever.
Yes. So what happened was during the fitting, because of the again in the gaps on the interval, we couldn't find a method to interpolate the data points in between. So that's
Okay.
why if we would have plotted it, then it was getting some flat lines, and those were getting these were being detected as peaks because that whole region was flat between the gaps and the good time intervals. So we
Okay.
couldn't figure out what to do with that.
So you didn't finally end up doing the fitting.
No, so we just smoothened the curve using these parameters. We did not
Okay.
go for fitting the
Gaussian.
parameters because we were lacking the interpolating points. Yeah.
So what parameters do you estimate for every flare detected?
Yes, for this flare, the parameters here are shown as
Okay, fine.
follows.
Yeah, okay, fine. Okay, any more questions?
Yeah, that's all from me.
Okay. Okay, then thank you.
Okay, okay.
We'll go on to the next.
All right, thanks.
Thank you.
Yeah.
Thank you.
Team 12 members can please raise their hands. Team 12 members. Yeah, sure. Bhargavi. Any more members are there from Team 12?
Hello.
Yeah, I think all the panelists, presenters are given the access. Yeah, you can begin.
Thank you. Interesting. I hope the presentation is visible.
And I hope I'm audible.
I'll just mute myself.
Speaker.
I hope I'm audible.
Yes, please go ahead.
Okay.
Yes, yes, yes.
Starting with the presentation, first about the data. So, as given the problem statement, the data set we've taken up from the science data archive from the Isro website, and the data set are clearly the light curves, X-ray light curves. So what, as a part of this project, what we did was we have inputted a light curve, and for that light curve, we first did a fast Fourier transform to get a power series spectrum. And in that power series spectrum, we looked for the QPOs or the burst or the peaks in that series spectrum, and that's what we did. Initially, for a given light curve, we applied an algorithm called fast Fourier transform. An FFT algorithm is used to convert a digital signal from a time domain into a signal in a frequency domain. And coming to backslide. Okay, the previous one. Okay, so while I'll just define what the power series thing is. A power spectrum of a time series describes the distribution of power into frequency components composing that signal. And according to the Fourier analysis, any physical signal can be decomposed into a number of discrete frequencies or a spectrum of frequencies over a continuous range. A power spectrum can be obtained by using an FFT or a fast Fourier transform algorithm. And coming to the QPOs, QPOs are a quasi-periodic oscillation. Okay, just a second. Yeah, a quasi-periodic signal is a signal that, having a repetitive recognizable periodic pattern, has variations in period and amplitude. So a typical QPO is obtained by performing a power spectrum of a time series of an X-ray light curve.
Finish off.
And coming to QPOs are further classified into low frequency and high frequency QPOs.
Leave it.
And the low frequency further classified into type A, B, C, as shown there. And as I said, after we've applied Power's FFT algorithm on a light curve to get the power spectrum, we have fitted the light curve using two distributions, namely power law distribution and the next being the Lorentzian distribution right here. And we've used we've fitted with this, and the parameters that we get out of these distributions are used to obtain the flux from a particular light curve. And here's the definition of power spectral density that I've already explained.
No, I hope I'm still audible and the PPT is still visible.
Yes.
Yeah, so I'll talk about the web app. So for our group, what we did is we generated a normal web app. Through the web app, you can visualize the power spectral density and then look at the power, like the curves of the Lorentzian distribution plus the power law distribution. So for the web app is it's divided into two parts: the front end and the back end. And the front end is the user interface. Back end is written in Python, and front end we use JavaScript. So here we have used React, which is very popular, and out of that we used this open source library called Material UI, which makes it easier to build this. So even however, the one thing that was mentioned is that we needed to run it on like a standalone web app, like standalone application. For that, there is a command and we can set it up, and like it won't. We haven't submitted the standalone like shell script which can convert this into a PW and then basically a binary executable, like an executable file, but like it can be done. The reason we didn't do that is because the JavaScript will get minified, so and no one can decipher what is written in the front end. So we wanted to make the code like readable for the submission purpose, hence we just submitted the raw code. But it's possible to like run a few commands and come up with a standalone app. Backend, we use Python again. So Python has a lot of third-party libraries such as AstroPy and NumPy, SciPy. So AstroPy especially was very useful to read the fits data and apply some of the transformations. For the transformations, we use NumPy and SciPy. So the web apps workflow is divided into 4 parts. So the first part is the user input. This is like the first page. I have a screenshot on the next slide. So whenever he sees opens the app, he's asked to upload like a light curve, and there you can select a file format. Now, when the file is uploaded, we send it to the backend, where the backend acknowledges it and gives a unique identifier. Like it creates an identifier, and that identifier is passed on to the front end. By this identifier, you can like look up a particular light curve, and if you pass a different identifier, it will retrieve that particular light curve from its storage. Like we just store the light curve as this identifier in the raw file storage, so it will recover that particular light curve. Now coming to the formats, now we had allowed for fits, ASCII, and CDF, but currently only like the fits format is implemented. The required background work for ASCII and CDF is done, but we had some confusion regarding the data format for an ASCII or a CDF file. So due to data inconsistency and some other issues, we did not implement it. However, the front end actually sends the file format recognized, so it won't take a lot of time to implement it later on. And we did not implement it because like there was code free, so we did not change any of the code that was submitted. So similarly, there's a raw curve analysis, and as mentioned, given a raw curve, so this screenshot is a bit outdated, but like these images are a bit bigger. So once like giving the output file, we kind of make a plot of this and then do the power spectral density as was explained by Bhargavi earlier. So and we give both of these to the user, where the user can like see these curves. Once we do that, we are supposed to analyze the flares from these two. So we are doing so we pass again, both of these have a unique identifier which the front end receives, and that is the general theme of communication between the front end and the back end. Now when we go to burst analysis, like where we are, this is basically flare analysis. So we are supposed to be fitting on the both of these curves, a power law and some like for these detecting these flares, some sort of a Lorentzian or a Cauchy distribution, so that like we can detect these flares. So we tried first fitting it on the spectral density itself, but like that didn't work out very nicely, as you can see here. And the other thing is like while doing it on the other one, we could not integrate it properly to like, display it on the front end either. So I'll just go to the web. So after this, when we so this is some start time end time which was supposed to be there, but since it couldn't get integrated, we haven't really completed that. Once we go on to that, the inference details, we can then, given the identifier, we could similarly download the log files. So I'll just show you a web demo of how it works. So I hope my screen is still visible. Am I still audible? No.
Yes, go ahead.
Okay, thank you. So we can just upload this .lc file, and this will now process in the backend. Okay. So like sorry, sir. Let me just switch on the backend. So now like this. So we read the fits file through AstroPy and then like plot the curve. So it takes a bit of time, but once that is done, yeah. So like this is the curve, and like this is the power spectral density that we get. So like this curve can actually be made a bit bigger, but like in the front end we've kind of squished it so that the user can like visualize it in one single page. And then when we click analyze, we're supposed to get a proper, like this kind of shows the frequencies that are present. But like we tried to fit a power law onto this, but it didn't properly work. Fitting it onto the Lorentzian kind of gave okay results, but like we reverted that commit because like it was done after the deadline, and we do not have that code. Like,
That is all for our presentation.
I'm sorry. So how many flares detected? That wasn't clear.
So like in our code, currently we detect only one. So we use this function from NumPy called numpy.argtal extrema. So that kind of gives us the extrema. From that extrema, we kind of detect the flares. And currently we take the global maxima and then use a threshold, like first take out the global maxima and then remove that and take a mean of the remaining. And out of that, we do a thresholding of that and do it. So in this curve, it shows like we are actually detecting one curve, but like we're not showing it on the front end because we couldn't implement it in time. So sorry for that. Like we're haven't implemented in time. So we actually mentioned this in our future challenges as well, like possible improvements, because we only fit a particular number of layers and the fit is not accurate, and we haven't integrated in the backend. So that has been mentioned in the submitted slides as well.
Rama, while they go for demo, can I ask a question?
Yeah, please.
So they okay. The team members mentioned that they have detected one flare, but
Yes,
I see that the flare, that whatever the x-axis, wherever you show that flare, that's in frequency, right?
Yes, sir. So we are detecting the frequency of like, so this you could say this curve. So we were actually doing two plots, but in this thing we'll just concentrate on this now. So
my question is, so to get something as a peak in any time series, so there should be some correlation. Why do you expect any correlation between different bursts?
Sir, so basically what we were trying to think is that given a burst, we would have mostly similar frequencies of like the flare. So we would be like those like solar flare, we would see which packet had the highest frequency, and we would use that. But that did not work out as expected.
No, but the highest frequency from what? A single burst or multiple bursts? Because
from a single burst.
From single burst. So my
Yes,
question, another question is like you are talking about 10 to 0.1 hertz, right? 1 to 0.1 hertz.
Yes,
so
sir. 0.1 to 1 hertz.
What is the bin time you have used here?
Yes, sir. Like, let me confirm. I think we use a bin time of around, what was it? 0.1? Yeah, I think 1 second actually. Like, that was the default bin.
But you were looking for some 30 hertz to 40 hertz QPO, right?
Yes, sir.
How do you actually detect 30 hertz QPO from 1 second binning?
So we probably missed them. Yeah, you're correct, sir. We probably missed them.
Thank you.
Can you please go ahead with the demo?
We showed the demo. Like we showed the burst analysis, like the app.
So what happens when you have gap in the data, say bad time intervals or something? How do you calculate frequencies?
Yeah, so initially for the first light curve that we got, we had a lot of gaps in between. So we faced a lot of difficulty while applying fast Fourier transform, because a lot of data points were getting missed while we were looking at the range. So that's the reason why we actually kind of reduced, or like we did some changes to the bin time and we reduced it so that we can take small pieces at once, so we don't really have a very huge loss of the data points. And then we like that we did the power spectrum, and we were like computing the other parameters.
So how many flares were detected in that? Can you show that plot where the demo data?
Okay, yes, ma'am. One second, please.
Yeah.
One minute, this will, yeah, please give us like 1 second. Just
Sure. Sorry, yeah, your voice is breaking. Yeah, please repeat it.
So you can see the curve. You can see the plot of the raw
Curve.
data here, and then
Yes, yes. You're still speaking? Hello?
hello.
Okay. Yeah, fine. Okay then.
Hello.
Any other questions? Yeah. Hello?
Yes, ma'am. You're audible now. I think we missed your question. Just completely missed.
Yeah, so just explain the one on the right side, the light curve on the left and the power density spectrum on the right. So how do you detect the burst? How does it indicate that?
So given this, now what we're supposed to do is we are supposed to from this power spectral density, we are supposed to like discard some of the frequencies, and from then we are supposed to take the maximas, and from the maximas we're supposed to like retrace it back and then use those frequencies for the burst.
Have you gone further, or you're just saying this is the idea?
This was the idea. So we actually like the fit that we tried to do with a Kochi plus power fit. It did not really work out as expected. So we weren't really getting a peak that was very high,
Yeah,
given the
okay.
data set that we had.
Okay then. Yeah. Okay then. If not, any other questions?
I just have a piece of advice. It was wrong for you to start with assuming solar flares are periodic or quasi-periodic.
All right, sir. Yes, sir.
Okay, that's all.
Okay then. Okay then. Yeah, thank you so much.
Thank you.
Yeah, thank you. We'll move on to the next.
Are there any more joining in? Yeah.
Yes, we are here and we can be given access to present. Okay, we'll be presenting the.
Are there only two presenters?
Yes, it will be two of us.
Okay, sure. You can begin your presentations
Okay, I hope it's visible.
now.
Okay, so hello everyone. This is Team 13, and in this presentation, we will be going through the brief intro of our problem statement, the approach we took, our implementation, and realization. So, Solar X-ray Monitor is a scientific instrument on board the orbiter of Chandrayaan-2 mission. It is designed to carry out spectroscopic observation of the sun with stable spectral performance over a wide range of solar intensities, which will help to explore the unexplored south pole of the moon. So, for this project, we had to create a statistical model or a machine learning model and a standalone app or a web app to recognize and categorize X-ray bursts using open source technologies. So, what is a solar flare? A solar flare is an intense eruption in the electromagnetic radiation in the sun's atmosphere. A solar flare occurs when magnetic energy that is built up in the solar atmosphere is released suddenly. The radiation is emitted across virtually the entire electromagnetic spectrum from radio waves at the long end through optical emission to X rays and gamma rays at the short wavelength end. Now, solar flares are classified
classified according to their strength. The modern classification system uses the letters A, B, C, M, and X according to the peak flux in watts per meter square of soft X-rays. The smallest ones are A class, followed by B, C, M, and X is the largest. So, we receive data in encoded formats of FITS, ASCII, CDF, etc. The plot given in this slide is the visual representation of the light curve, that is temporal variation of count rate as seen by the XSM package on Chandrayaan-2. Let's have a sneak peek into our approach in analyzing this data. We know that the package transmits data with a frequency corresponding to half orbital period. This is the region in the graph where you will be able to see rapid fluctuations in the count rate. If the solar flare occurs in this interval of orbital period, that is when transmission takes place, we see a sharp rise in amplitude of the count rate. Now, however, we see another different regions with straight lines. These are the regions when the XSM on board the Chandrayaan-2 was not in the visibility of the sun. And we are not really sure if there was a solar burst in this region, and the fluctuation that we get just after that blanket band is a noise or was the decay of a solar flare. So problem statement as well as various reference papers indicates that there exist 5 parameters that are of high relevance in categorization of solar flares. These different 5 parameters were then extracted from the light curve and are summarized here as peak flux or the peak count rate, the rise time, the start time, the decay time, and the end time. So light curve given to us contained information in the following format as we can see here. It contains count rate, time, etc., etc. We know solar flares are categorized on the basis of peak flux into different categories. However, the data that we got from the Pradhan website, it had light curves in terms of count rate and time. Hence, we required a mathematical mapping of count rate and flux in order to classify the solar flares from the given data. So for that, while going through literature and doing further exploration about the count rate, we came across this mapping, which is referenced from the paper written specifically on the X-ray monitor on board Chandrayaan-2. Using this mapping, we categorize solar flares on the basis of count rates into 5 categories as shown in the table, A, B, C, M, and X, and their corresponding count rates in Hertz. So the mapping that we are following is the one with the green line, as the monitor on board Chandrayaan-2 does not have a beryllium filter. Moving on next, after getting familiarized with the parameters of the solar flare, here we would like to elaborate how and why these specific definitions were chosen. Talking about the start time, which was chosen to be the time when the counted is 5% of the peak rate. This was done intentionally so as to exclude the pre-flare heating and also to ensure that if there had been another peak prior to the flare of interest, it can be ignored safely. Similarly, following the convention as above, end time was chosen to be the time when the count rate drops to 50% of the peak count rate. Now, moving on to the next one, as we know that XSM data also contains noise as well as discontinuity in the data recorded. In order to prevent false predictions, we decided to set the minimum flare duration to be set to be around 2 minutes. And we further made some assumption of overlapping flares, so that if there are 2 flares which are overlapping, since the data is not multispectral, they are going to be considered as one. Now, prepared with the understanding of physics and what the problem statement demands from us, we can jump to the implementation part. Based on the analysis so far, we realized that problem has a very solid mathematical ground truth and decided to theorize a statistical model to do the classification and reduction. Based on the mapping previously decided, we made a model that takes the light curve data, approximates it using rigid decision boundaries, while the maxima of the approximated curve gives us the category of the burst, the instance of the first rise of the pulse, and the fall of the final pulse give us the ROI, as you can see in the graphs here. But with this initial approach, we faced the problem. What was it? Fluctuations in the data near the decision boundary can give successive rise and fall of the pulses within a short span of time, as you can see in the plot. As the noise is in close agreement with the count rate of category A burst, this can lead to false prediction. To deal this, we reference to a paper which again is specifically designed for soft X-ray flares. It gives us the mean flare times of different category of burst. That is, B lasts at least this many minutes, C lasts at least this many minutes, but we couldn't get any data for A category flare. So on further analysis, we made an assumption that if the flare duration is less than 2 minutes, It is not a flare, but noise and can be ignored safely. So connecting all these different dots, we prepared a model which takes the light curve data in FITS format and returns a Python dictionary with all the necessary information of our predicted flares. So basically, our Python dictionary will have all these outputs. T start is the start time of the ROIs of the predicted solar burst. Similarly, T end. Then all these are different lists of the information that we want. And if the data was given, the rise time is given by the purple line, the peak count rate is at the instance of the red line, and the end of the flare is at the green line. Using this background logic, we made an app, and here is a demonstration to set it up. We first head to the GitHub repo and clone it locally. As the app is very lightweight, this happens rather quickly. After this is done, we open a terminal inside the folder and run the next command from a README file to satisfy the dependencies of our app. And with the next command, our app executes and it looks like this. Now we can upload files which is processed by our model and we get a visualization and a table with all our predicted flares. Let's upload another file. And as we can see that this data file is giving us presence of at least 10 bursts, their category, their peak count rate, their rise time, and their decay time. This data can now be exported and saved in JSON format, and the image plot can be saved too. Okay, coming to limitations of our app or our model. As we saw from the category mapping, the range of each burst gets larger with more powerful bursts. Since we're using the same instrument for detection of every type of the flare, it can suffer some systematic error. Further, the range of noise is in close agreement with category A flare, and with the range of category A flare already so narrow, we are going to have some false predictions. To prevent this, we made a decision to ignore the classification of A category bursts. So after making the final submission, we pondered over this limitation of ours and what more could be done from our side if given the opportunity. So right now, our model ensures classification of high count rate bursts. For category A and other low count rate bursts, special smoothing techniques such as lowest smoothing or maybe doing more studying of research papers and setting better thresholds can be done. Further, a model can be refined to subcategorize the classifications. Like category B burst can further be classified from B1 till B9, and same goes for C, X, and M categories. So these are the references of different papers that we went through in making our model and a project. And that was it from the team 13. Thank you.
Okay, can you please go ahead with the demo of this?
I'm sure. I hope the screen is visible now.
Yes.
Okay. Okay, so as we said earlier, that the threshold that we set to avoid false predictions, we made sure that we are not going to detect A-class flares, as the data of XSM was noisy. But this is a very neat data, and we can change the threshold so as to detect A-class flares as well. But currently, our app is not going to do that. We can change the threshold of the ground app of a ground logic, and it can detect the flares. So the threshold that we set was that if the count rate is less than 800, it is noise. But the data that you guys gave us, the count rate varies from 100 till a maximum of 300. So we change the threshold and we are able to detect at least 2 bursts at the end of the flare.
This is after changing the threshold, is it?
Yes, we changed the threshold in a collab file, but we couldn't change it in an app. We can do that, but it can take some time.
Oh, no problem. Two threshold, two flares, as in the last end of it, you just found out the start of the flare?
Yes, we could only find the start of the flare.
Okay, but not
The
the rest of it.
ROIs, yes.
Okay. You don't find any peak times as well? Peak of the flare?
In this, we have to change a bit more, but the data that we get from XSM, we can find that in that. Can we use our data to show that?
Yeah, sure.
Okay, please. So here we detected only one flare, and the data that we got from it is given. It's a category C verse with the peak count rate, the rise period, and the decay period. And we can upload one more file. And here it is.
So is there any classification methodology you tried apart from just Cohen's classification, ABCD?
No, we basically did A, B, C, D, A, B, C, D, M, and X. That's it.
Okay, yeah, sure.
Yeah.
Thank you.
Okay.
So just to understand, what you're doing is you're looking at the background, and if it goes above some 5%, you're saying a flare is starting, right? Is that
Yes,
what
sir.
you're doing?
Yes, sir.
And then till then you'll find the peak, and then 50% of the peak you're saying flare is ending.
Yes, sir.
But here, whenever in the plot we are showing, it is not 50%, it is much later your end time.
Okay, sir. The plot that is shown here is the only the ROI. We are just taking the region of interest. It's not actually showing us the
Start time
start
and
and the
time.
end of the flare. Yes, sir.
So ROI, how you are defining? It's not ROI, it's R of time, or the
R
good
of
time
time.
interval.
Okay.
Yeah.
Yes, sir. So for R of time, we basically took the
Time of
threshold.
interest, you should say.
Time of interest. For time of
Yeah.
interest, we took thresholds that if the maximum threshold, maxima is above certain threshold, then we're going to
And this 5% is 5% of what?
of the peak count rate.
But peak, how did you find? Your maximum you took of the whole day.
No, not the of the whole day. We are actually approximating each of the different bursts that we have with
But how you are finding the burst first of all?
sir, okay, can we go back to Canva? Just show it here. Yeah. And previous slide. Previous. Okay. Okay, sir, this is it. We are approximating it using setting certain thresholds. And if it is above a certain threshold, we are saying, okay, we can be sure that this is a burst.
What is the threshold you're setting? Is it a value or is it some?
It is a value, sir. It is a value. If it
Some
is,
number.
it is some number. If it is between 600 to 5,000, as you can see in the table, it is category
600
A.
is what? 600
600
counts.
62, yes, sir, count rate.
Oh, that's dangerous now because different instrument will have different count rates.
Yes, sir, exactly. But we reference this from the paper that was written based on the Chandrayaan 2 model.
No. But if you say take 600, how are you getting 10 place in that?
No, sir. That is only for the category. If the maxima lies between 600 to 5,000, it is category B. If greater than 5,000, category C. If it is greater than the set value M, X, and so on and so forth.
No. You just go to the next slide where you have listed all the flares detected.
Okay. Show
The
the
first
app.
one is a M class flare.
Yes, sir.
Yeah. So if you see here, two things. One, can you actually show the plot of this first plate?
Zoom. Can you zoom in?
That one.
Yes, here it is.
So, but you say that the rise period is almost twice than the decay period. I'm not seeing that unless and until you are starting it somewhere earlier.
Okay, so what we faced the issue was that it could happen that the 5%, it is easier to reach 50% of the peak. This is because of our assumptions, the definition that we took. The reason is that. So because it will be reaching 50% of the maxima earlier than it reaches 5% on both sides of the maxima.
Okay, thank you.
Okay, any further questions? If not, thank you. We'll move on to the next.
Just one question, Rama.
Yes,
you
yes.
are not fitting any model or anything, right, in this?
No, sir, we're not fitting any model.
And whether it works for FITS, ASCII, all the different formats, file formats, CDF.
No, sir. For the time being, it only works for FITS format only.
And this works in Linux, right, or Windows?
This works
or
in
both?
Linux. In Linux.
Okay, fine.
Okay, thank you, sir.
Thank you. Okay, let's have the next team. Can we have the next team? Hello?
Rama, that will be T14, right?
Yeah, T14, yes. I think T6 isn't presenting, correct? Yeah, fine. Okay.
Yes, ma'am.
Yeah, it's
Team
not.
6 isn't presenting. I'll just share the rights to Team 14. Team 14 members, please raise their hands. This is the last presentation we'll be having for today. So, yeah. Team 14. Just 1 minute, ma'am.
Yeah, sure.
I have sent invite to Prakhar. Preeti is now a presenter. Are there any more presenters joining in?
Yes, actually, Anmol and Pratyush are joining. Yeah, Pratyush is joining.
Okay, sure. Anmol, can you please raise your hand?
भैया
Team 14, please confirm if Anmol is present in Air Meet link. Okay.
Yeah,
Anmol,
he's
I have sent an invitation to you. Kindly join the stage. Okay, I think all of you are in. So now you guys can begin your presentation. Yeah, Team 14, you can begin your presentation.
presentation. I can see the black slide.
Let me check.
No, just. Start now.
Preeti, your voice is breaking. Can you please check?
Can I start now?
Yeah, you
Can
can
we
begin.
start with the presentation now?
Yes, you can begin.
Okay. Hi, good evening. This is Preeti Sarva. I'm from Team 14 and I'll be
Just
presenting
1 second. Your screen is not visible.
It is visible
Yeah,
right
now
now.
it's fine.
Okay. Okay. So, hi, good evening. This is Preeti Sarva from Team 14 and I'll be presenting a solar burst detection technique that will automatically detect solar flares, extract their characterized features and classify them. Sun is the closest star from the Earth and hence the best possible celestial body to study the mechanics and the dynamics of a star. The surface temperature of the Sun is about 6000 Kelvin, thus it has electrically charged gases at the surface that generate areas of powerful fields. Due to the differential rotation of the Sun, gases in it are continuously moving, tangling, stretching, and twisting the magnetic fields. This movement produces huge activity on the Sun's surface. A solar flare is an intense burst of radiation coming from the release of magnetic energy associated with the sunspots. When the tangled magnetic fields are twisted extensively, they release energy when they break. Solar flares are visible because of the light they emit at nearly every wavelength of the spectrum. Thus, this event we have employed the light curve of solar data in the X-ray areas to identify solar flares autonomously. Solar flares occur when magnetic energy accumulates in the solar atmosphere and must be released. There are 3 steps involved in a typical flare release. The first stage is the precursor stage. The release of magnetic energy is triggered, that is, the gradual onset of the flare. The emission is observed mostly in the soft X-ray. The second stage is the impulse stage. Electrons and protons are excited to energy significantly. And this step results in the emission of hard X-ray, radio waves, and gamma rays. In this technique, using the X-ray to predict the flare. The third and the final stage is called the decay stage. The soft X-rays are identified stage. So identified during this stage due to their progressive accumulation and length. A solar flare has some features like the starting time of the flare, its ending time, peak flux, duration, and the type. To extract these features, we have implemented a model with several steps. The first step includes pre-processing, which have steps like rebinning the data, minimum flare detection, and much more. So the first of all, we are binning the entire time series data into steps of 60 seconds by the median value of the flux, as it provides a better central tendency metric for data having a lot of outliers. Sun has events of different energy release during different stages of its cycle during the quotient period between the median of fluxes to find the noise level. For this event, it was of 2019. The minimum flare duration is assumed to be greater than that of the 60-second, hence the peaks and troughs shorter than the bin size are assumed as potential noises and hence are removed. For smoothing the curve, we rebin the entire light curve with a boxcar convolution of 10 cluster points. This helps us to smooth the noise significantly. Now, we identify local minima and maxima of the curves. You can see all the minima and maxima of the curves in this light curve. Based on the solar feature extractions, flare events are defined when they fulfill the certain conditions. First step is when we calculate the background flux. For this, we first identify the start time and the end time of a mean value of the flux preceding 90 seconds from the start of a flare. Now, here a problem arises that there may be the case when the particular flare is already preceding by some flares, especially when the solar activity is high. So here, taking median will give the median of fluxes of preceding flare instead of the background. So to solve this issue, we put a condition that if the median of the flux is more than the certain times of preceding background flux, then we take the background flux of this flare as that of the previous background flux. The ending time of the solar flare occurs when the flux drops below the background flux. Now, here too, in this case, when some of the flare occurring when a solar flare is ending, then the flux level is not touching the background flux. So in this case, we extrapolate the decay and the rising of the subsequent flare to find the ending and rising time of the next flare. The peak flux value will occur in the intermediate time. To find the flare peaks, our algorithm searches for consecutive increases of 4 points such that the count rate of the fourth point is greater than or equal to a particular threshold. Then we search for 3 consecutive decreasing points after the fourth point. Then the peak flux of the flare is calculated by taking the global maxima of these points. Actually, the peak flux value is subtracted from the background flux, that is the actual flare data minus the flux of background value. Then we have extrapolated the curves for the starting and ending of the flare. We extrapolate the curve at the beginning and the end of the flare of the F for the background flux level, in this case preceding or followed by some other flare. Also, we know that the observed burst has a fast rate and slow decay pattern. So the fast rise follows the straight line while the slow decay shape follows the power law function, that is fx equals to a t to the power minus k. We have fitted the function according to the given data and find out the parameters of these two forms for every flare, and then we find out the rise and decay times by extrapolating the curves. Here you can see all the starting and ending time of the flares. Also, the peaks have been colored with a different color so that you can differentiate them from the background variations. Next is solar flare classification. Basically, solar flare classification can be done in two ways. The first one is with respect to the background flux. This is a classification on the basis of peak flux with respect to the background flux. And the second classification technique is on the basis of energy that is released by the solar flare. In this technique, we have used the technique classification on the basis of energy release. If the background subtracted peak flux is in the order of 10 to the power minus 8 or less, then it comes under the A class of the flare. Similarly, for B class, the exponential term is 10 to the power minus 7. Similarly, for C, it's 10 to the power minus 6. For M, it is 10 to the power minus 5. And for X, it is 10 to the power minus 4. Now, we have tried to further subclassify these classes with an additional digit. For example, if the peak flux value is 3 into 10 to the power minus 6, then it will come under the 3C class. Now, in this curve, you can see there are multiple color used for detecting the flare minima and for each flare. So the black dashed line is indicating no flare region. The green color is indicating the A class flux. The red one is indicating the B class. Orange color is indicating C, and blue color is indicating the M class flares, and the magenta color is representing the X class flare. Yeah, this is the one. Now comes the web-based application. In this application, we have mentioned the 3 articles through which the user can get familiar with the solar flares and what all mechanics and dynamics takes place under this event. And then we have provided a submit button where the user can upload their light curve data and get insights on the same. Here are some insights where the user can check for the classes of the flare individually and see what all flares are detected. Here is the zoomed version of the same, and you can see the classification on the right hand side. Also, in this classification techniques, we are able to identify the micro flares as well. So the false negatives are minimized. Thank you. Can we move forward to the live demo?
Yeah, please
Yes,
go ahead.
go ahead.
Okay, sure. Prakar, you can start presenting the UI.
So solar flares go through several stages, and there is no correct way to forecast their strength or duration. Each of these stages might last anywhere from a few seconds and an hour. Here we developed an automated flare detection algorithm that allows us to analyze the time series data of the light curve. We have given some links to the articles for further reading. We can now, to use this application, we will have to upload a file. This can be any type of file like ASCII, FIT, CDF, CSV, or a light curve. Now, we can click here or drag and drop a file to upload. So now we'll upload the file. As you can see, it is accepted, and it has given the total size of the file. Now I'll click on upload. Now this data is sent to the backend, and which processes the data and feeds it into a machine learning model, which then returns back all the data to the client, which is then rendered beautifully into a dashboard, which shows all the charts and the phase distributions for the flares. A light curve is a graph that depicts an object's brightness over the time. The light curve is a basic but important tool for scientists studying objects that alter their brightness over time, such as a novae, supernovae, or variable stars.
So while it is loading, can I ask a question?
Yes.
Yeah. Yeah. So what machine?
Oh, yeah.
I'll pause.
So
Let's go on.
Shall I go ahead?
Yes, please.
Okay. So now it has churned out the data. As we can see, this is the main chart, which shows all of the fluxes, all of the types of flares in a single graph with different colors. The legend is given over here: flux A, flux B, flux C. As we can see that if I hover over a particular point, it will give me all the details about what are the values for the different fluxes and what is the date and the time for that flux. This pie chart shows the distribution for the different types of flares. In this graph, in this line chart, we can see the individual types of flares. Now, if I click on type B, it will show me the line chart for only type B type of flare. If I hover over it, it will show me the details like what's the rise time, peak time, decay time, peak flux, background flux, and the type. Along with it, we display an image which shows a more accurate version of flux versus time, as it reduces the background noise. And we can also download the result in a CSV format. so that further the scientists can analyze this data. Now it has downloaded. Let me open it. Okay. So this is the data in the CSV format. Now I will hand over to Pratyush.
So how many flyers you found? 50, 20, how many? That Excel file just show now how many. Can you just show that Excel file?
Okay.
28 flyers you
Yeah.
found.
Yeah.
There
So
was 2 M class flyers also.
28.
Out of that, there is a 2 M2, M and.
So it's 27 actually. The first one is for the header.
So that is first one is class, no? Whatever you written M class and all. Type.
Yes, sir. It's for class.
What was your definition of class? Can you just okay? Let me just check. I might have it.
So for classification, we have used the
So M
background
class
subtracted
is
flux peak.
okay. So M class is as per your document, it is 10 power minus 5 watts per meter square, right?
Yes, sir.
So in the given data, you are finding 2 of them above that value, right?
Yes, sir.
And how did you convert these counts to watts per meter square?
So for that, we have assumed that the data given was in the watts per meter square and in the ranges of 10 to the power minus 7 watts per meter square.
What is it? What is 10 power minus 7 watts per meter square?
So the peak value is given to us.
There is an echo. Probably one of you can mute.
Yes, sure.
No, no. What I'm saying is, obviously there is something wrong in your conversion because in the given data there is no M class flare or anything. That is at best maybe B class only. So whereas you got some M class flare and all. So definitely there is some problem in conversion. That's why I asked you, how did you convert counts to watts per meter square?
So for that, we have assumed that the peak rate value that was given was in watts per meter square, and through that we have calculated the mean background fluxes, and by subtracting it and taking its in what range it is, we have classified it in different types.
Okay. So in some given data, you had watts per meter square. You found the count and you divided that and took a linear relation. For every count, this is a watts per meter square. Right?
No,
That's what you did.
not exactly the linear relation. We have evaluated the peak flux through the maxima minimas and the background values through medians, and have subtracted them to evaluate the background subtracted flux, and through that we have classified them.
And so here to find the peak, whichever is above background you are considering is a flare, right?
No, sir. For evaluation of a peak region, we have first taken 4
Not the peak
increasing
location, the
points.
flare start time. That I understood. I'm saying
Yes, sir.
flare
And for
start time.
uh, the flare start time is actually calculated through the linear fitting of the rise data from the peak value and the initial starting points. We have fitted a linear curve, and the point where it curted its previous background flux, that it's taken as the rise start time.
Yeah, I was going to ask this fitting thing next. So you have considered a straight line for rise time and a
Actually,
exponential decay for a.
yes, sir, because it in the most of the fluxes the rise is very much steeper. So using the linear fitting, the error is actually very less in the start time.
Yeah. So you used it together. My question was that did you make a model with a linear plus exponential decay, or you separately fitted it, rise time and the decay time?
We have separately fitted it for the rise time. We have
fitted from the start point to the peak point, and for the decay fitting, for evaluating the end time, we have fitted from peak point to the end point, where the minima is received.
Okay. Okay. That's all from me. Rama, somebody else?
No, that's fine. Yeah. So
How do you account for the time gaps, data gaps?
Sorry, sir.
How do you account for data gaps?
So we have uniformed it, and also because the data gaps was not actually uh, lose have any haven't any gave any error in the flux, and the flow was not
So actually, we have replaced the missing data values with the value of the entire data set.
Sorry, I didn't get you. Can you repeat?
The floor value, sir, the minimum flux value. We have replaced all the missing data gaps with the floor value.
Which is?
Sorry?
Which is?
It's according to the. So actually,
the
it's according to the.
Floor of the day.
Yeah.
That particular day.
Yes, sir.
Sure. Okay. Yeah, that's all from me. Thank you.
Did you try? Sorry, did you try other files as input, like CDF file or ASCII files?
Sorry, sir.
I mean, your
voice
input.
was.
Your input. Did you try inputting CDF file or ASCII file, whichever was supplied today?
Yes, sir.
What did you get?
So we have used the LC file.
Yeah, only LC file you have used, no? Apart from that, we had two other files. Did you try those?
Sir, actually, hello.
Yeah, go ahead.
Am I audible?
Yes, please.
Okay. So, sir, actually, our algorithm isn't including the LC files. It's not supporting LC or TXT files, but rather it's accepting the ASCII files, TREX files, and the CDX files.
I see. So, but the input what you have given is LC files, no? Whatever you have run in the demo.
Yes, sir.
So
So
you
actually, before actually we have converted the LC files to CSV files, and then we have imported this thing, because in the problem statement it was mentioned that ASCII files, fixed file, or the CDF files, and etc. So we tried for those three files only, and for now we have converted the LC file to CSV, and then we have tried the test.
Yeah. So when you convert the LC files into CSV files, did you also convert the header information? Which file has
Sorry?
its header? LC files have header information.
Yes, sir. We have.
Yes.
Yes, sir. We have converted them to also.
So if you have converted, you should know what is the unit of the data, right? In the header of LC file provides the unit of the data. Which unit the data is provided?
So actually, the previous data that we have used to build the model, there wasn't like it was a zip file, and it was mentioned in some other file mentioned there, like the PH or GTI files. But here we are provided with only LC files. So we took according to that LC files, and then we have built the entire data.
Yeah, but this LC file also has header information. That
Okay.
header has the knowledge of the unit which is provided, because that is important.
Yes, for example, the header file had the information. So, like the rate header had the unit of count, and the so the
Right.
time was the MET mission elapsed time, and then there was phrase XP and the error.
Yeah. So the units you said, it's in counts, no, not in flux. The same question what Srijit asked about M class flare, correct? The unit is in counts, not in flux as you guys have assumed it. So I mean, what I'm trying to convey.
So we have used a method to convert.
So what is the
Convert
conversion
those.
factor which you used? I mean, can you tell us a bit more on that? How did you convert it? That is what Srijit was asking.
Okay.
Sir, actually, we had assumed it to be the rate values to be of 10 to the power minus 8 W per m square, sir. So
I mean,
we took a linear relation.
no, from where? From where? I mean, it is just you assume some number, or you got this number from somewhere, some paper or some references.
Yes, like we actually read the activated solar flare detection paper with the GOES data, and yeah, so we referred
Okay.
it from the same.
Okay. So just to caution you, the area of GOES and the XSM and the sensitivity of GOES and XSM will not be same. So if you have assumed that, then the numbers can go wrong. That is what would have happened.
Okay, sir.
Okay. Thank you. Yeah. That's all, Rama.
Okay then. So we
Yes. Yeah. So we are at the end of the presentations. We have completed presentations from 14 teams today. So yeah, I thank all the participating teams to like participate in this ISRO mid prep event, and I thank all the judges to like devote this much time to evaluate all the teams. Yeah, so this is a message for all the participating teams that mid evaluation scores and final presentation scores will be made available to all the participating teams at the end of the event, which will be 27 March. And yeah, this marks the end of the event. So
Avanti,
participate.
just
Yeah,
a
yeah.
minute. So,
Yeah, sure.
just to just want to convey my happy feeling that when we announced this, I thought we will not get much interested people, but when I saw such a huge number of teams, we got really excited because the missions carried out by ISRO is not for ISRO; it is for the younger generations and people of the country. So the exercise what we have carried out, though it is mostly carried out for the XSM on Chandrayaan-2, this will go a long way to help our upcoming mission called Aditya L1. So one of these codes, if is suitable, we would be more than happy to interact with the people and develop this code to a level where we can utilize it for the science outcome from one of our missions. So I'll be very happy to interact with you guys, and I hope we will be able to select one best codes from here and interact with you guys to make it useful for our upcoming mission. So we would look forward for more such interactions and opportunities with young people like you who can meaningfully and successfully provide some of these short-term exercises, which leads to a lot of successful scientific papers out of many of our missions. So I thank all of them and your organizations for allowing you to work on these particular projects, and all of them have done fantastically well because they're not in this particular field or particular area, and capturing the problem statement, attacking at the right line of attack, and also providing a solution is not an easy task in 2 weeks time, and that is what the time is given, and which many of us usually take. These are the problems actually for a PhD. So PhD usually takes 2 to 3 years, and you guys are trying to attempt it in 2 weeks. So given that such a short time, you guys have done excellent job, and I congratulate all of you. So don't think that if one or two gets the winner trophy, doesn't mean that others are the losers. Your contribution is always important to Isro and the country. Thank you all.
Thank you, sir. Yeah, I'll just end the session now. So yeah, thank you all.
Thank you.